Okay, hello everybody. So we are back on dress code school. So today is the Rust day and the VULKAN day also.
And so also the Julia day.
Also the Julia day at the end, but it's your day. A bit of Julia at the end with Nabil, but mainly it's your day. So if you want to know all the weird stuff of VULKAN, all the weird stuff that we are hiding you with CUDA or with stuff like this, you will see that the GPU is much more complicated than you might think at the first time. So Adrien, it's yours.
Yeah. So welcome to this talk where I will show you that CUDA is a high-level programming environment, contrary to what the conspiracy would have you think. First, I always like to start my, stupidity to be fixed. All right. I always like to start my talks with something that has nothing to do with the talk. So let me tell you that it's actually really hard to write a course about a technology that works really well with no problems. Because you write a one-page tutorial, it's easy, people do the stuff works, and then it's boring, right? Thankfully, I do not know of any such technology in computing. And all my courses have been inspired by bad feelings of some sort. It may be fear, like I know I'm someone who makes a lot of mistakes. I want to have development practices that will catch my mistakes before I push them in production. And I say maybe it's useful for other people, so I teach them too. It may be anger, like I see people, they had all they needed to do the perfect thing, and they did something else instead. Can be disgust. They did not even try to do the right thing. They went for the wrong thing right away. Sadness. I wish more people use this, but I know exactly why they don't. Or it can be contempt. This is, I don't know why people are using this, but I have been forced to use this, so I'm going to write a course in the most passive-aggressive way possible. Today's course is inspired by a different kind of feeling, which is pain. I will explain in a minute. We'll see how that goes. You tell me at the end. And if all goes well, next time I'll try the NV-based course where I beat Sebastian's code with much better code, obviously. So, flashback time. You may not know, but the first edition of the precursor of this school was back in 2016. It was called Parallel Programming for Heterogeneous Architecture. At the time, only French. It was in LLR at the Polytechnic School near Paris. And I was freshly recruited at what was then called LAL. It later became IGC Lab. And so I was young and naive, and someone called me and said, yeah, you are going to show how it's easy to do portability with a great technology called OpenCL. And I did. But because I'm a bit, a fearful person, I did test my code. And I found out that all the OpenCL implementations that I had access to were broken. Like I could establish that it was not a problem in my code, but in the implementation. And they were all broken in a completely different way, which made for a very nice debugging nightmare. And I was, at the time, was thinking, OK, this is going to be a hard sell, to the students. But I did what every good teacher does, and I swept the stuff under the rug, put all the right workaround in my code so that it works, and call it a day. At some point, people do try the technology that we teach, and they discover that we have been lying to them all around. And most of the time, what they do is they give up, and they sell their soul to the empire, NVIDIA in this case. Sometimes they sell their brain too, and then they forget that not everything NVIDIA marketing says is the truth. And at some point, we get paradoxical situation, like people claiming their code is portable, but when you actually look at it, basically it works on NVIDIA, and everything else is to do make it work on something else someday. This is not my vision of what taxpayer money should be funding, so I try to do it in a different way. And one thing I do is I try to ask myself, how could GPU code portability go so wrong, right? What is it that all these frameworks try to do that causes all these problems? In my opinion, there are 4 basic sins of GPU portability that everyone, it's a trap that everyone falls into at some point. The first one is when a framework leaves portability as a to-do for too long. The problem here is that basically when you do this, you will, consciously or not, build your abstractions around CUDA, because that's the only thing you know. And at some point, you will have a CUDA code base, and you will discover that every hardware manufacturer has an API which is not CUDA, which is almost like CUDA, but different in sufficient many ways to turn your life into hell. So first mistake, portability is something that you should tackle early on, otherwise you will suffer when you do actually try it. Second mistake, this is an opinion, I accept people to react violently in the chat. I think frameworks which try to have portable code across CPU and GPU are also making a mistake. Yes, I hear the chat screaming, that's perfect. And the reason why I think this is that anytime I have tried a framework that tried this, the complexity in terms of programming model that you expose to user was huge by CPU programming standards. The ergonomics were quite bad for both CPU and GPU because you try to accommodate the need of both and they are quite different hardware. And ultimately, even if you suffered those APIs long enough to get something working on both platforms, you would find out that the results are disappointing in at least one target platform, CPU or GPU. So in my opinion, this is too big of a problem. We've been trying for decades, we don't manage. And what we should instead aim for is to make GPU easier and use the time we save to write a good CPU version if we need it. A mistake which is related to the first one that many portability APIs make as well is to imitate CUDA. This may sound like a good thing because everyone is familiar with CUDA. The problem, however, is that now you are not in control of your API anymore. NVIDIA is. Which means that anytime NVIDIA pushes a new CUDA release, your portability framework will support these CUDA features long before you support them on any other hardware, because for other hardware, you need to do the plumbing work of making it work. So people get the message. If you want something that's up to date, get NVIDIA hardware. Maybe not the message you wanted to send. And second, if you are targeting hardware which has features that NVIDIA doesn't have, obviously NVIDIA will not do the work of integrating them into CUDA, so you're on your own. And finally, the fourth sin of portability APIs, in my opinion, is to rely on hardware manufacturer goodwill to have something which only works if the manufacturer does exactly the right thing. And this is a very big one for OpenCL, as we've seen. The problem here is that you may not know, but actually the high-performance computing community is relatively small compared to the general market of GPU applications, you know, games, CAD, machine learning. And this means that because hardware manufacturers are rational economic agents, they will not give us that much of their time. So if we have something that requires a lot of work for the manufacturer before it works, which is work specific to HPC, the work won't be done. Or it will be done badly. And this is especially true for smaller hardware vendors who have less developers and thus less time to care about this sort of minor use cases. Enter VULKAN. VULKAN, initially, is an API whose intent is to replace OpenGL, which I will talk about in a minute, which is an API for programming GPUs that has existed since before GPU hardware as we know it even existed. It targets graphics developers who want well-optimized code. So the idea is that when you use VULKAN, you should have access to all the features of your hardware. If there's a feature you do not have access to, it's a bug that should be fixed in the spec. It's OK to use an abstraction layer to make things easier, but there should always be an escape hatch to the low-level layer in case you encounter some problem that can only be resolved with the horrible low-level stuff. VULKAN targets people who care about portability. You know, if you are, I don't know, Ubisoft, you have games that should run on PlayStation 3, which is the weirdest hardware you will have ever encountered. PlayStation 4, PlayStation 5, which is almost like a PC, but you don't want to know the difference. Xbox, same story. Then you have all the myriad of PC hardware, each creative in their own way. And you have the cell phones too, and so on. And the goal of VULKAN is that you should be able to write an app that works on all of that with minimal hardware specific work. You also want implementations that are high quality and mature, by which I mean you do not get stuff like you send the DPU compiler a program to compile and eventually execute, and the DPU driver does an infinite stack recursion and crashes, which is what the Intel OpenCL implementation did at the time I did the school. So we don't want that. We want something that's easy to set up, ideally already set up on user's machine for the runtime environment. It should be not that much work to get a working developer environment as well. We don't want bugs. We don't want compiler errors. And also for production applications, we don't want the API to change in a way that breaks our code every 6 months. And the price you pay for all this is that you are really to tolerate API ergonomics at the VULKAN level that are much worse than anything you've ever seen, under the premise that, you know, once you've gotten the hang of it, you will be able to hopefully build a higher level abstraction that hides this stuff under the rug. This is what programmers do, right? Why am I talking about graphics APIs? Again, they are designed to get the most of GPU hardware. That's what they were made for. They were there before all the other APIs. So they have all the features you would expect from a compute API and then some. They have a larger audience, which means that you have a larger base of unpaid testing engineers. So all the bugs have been found by other people. You get something that's easy to set up, very stable at runtime. That's great. You also get good tooling, but with a footnote, which is that all the tooling you will find has been designed for people who write real-time rendering application. And sometimes this assumption will be hard-coded so deeply that you will not be able to use it, and that's a pain. And one thing that has been done well in graphics APIs, which in my opinion has been done less well in compute-centric APIs, is that some graphics APIs have been designed with the goal, explicit goal of portability across operating system and hardware in such a way that, you know, you only have 5% of code that's specific to particular platforms for optimization purpose, and most of the code is common. And because, again, the audience is huge, you do not rely on manufacturer goodwill. The GPU manufacturer can afford to have a terrible OpenCL implementation because nobody uses OpenCL. They cannot afford to have a bad VULKAN implementation because all the games and soon all the CAD engines use VULKAN. I've been talking about OpenGL a lot. Why do I not discuss the specific API? Because, in my opinion, it's obsolete. The problem with OpenGL is that it was designed by SDI in the 90s, at a time where GPUs, as we know them, did not really exist. The hardware was completely different when you had hardware at all. Many times it was implemented on CPU. And so there are many design decisions in OpenGL that do not really make sense on modern hardware, like, you know, commands that allow you to draw one line on screen per command, for example. You don't want that on a modern GPU. The communication costs to draw that line are so enormous, you won't imagine. And the problem is OpenGL cannot evolve into something that's better suited to modern hardware due to the constraint I mentioned earlier of backwards compatibility. They tried. Back when they designed OpenGL 3, there was something called White Peaks, if I remember, where the goal was to say, OK, we throw away all the stuff we know is a bad idea on modern hardware. It was a disaster. Application vendors pushed back hard, say, we absolutely need these features. There's no way we are ever going to rewrite our code. Tomatoes were thrown at the Kronos committee, and in the end decided, okay, we are not doing this, right? And this is the day where OpenGL effectively died from an innovation point of view. And it took the only way forward left, which was to have many different ways to do something where all but one way are a bad idea. And because the design of OpenGL is not great for modern hardware, what OpenGL implementation had to do is to be clever. They started to do things like, you know, the API says, when this command is called, we should draw a line, but maybe the user won't notice if we don't draw the line right away. We start buffering a bunch of lines somewhere. At some point, we're going to send them in the hardware. We don't tell you when. You can imagine how that goes. We are here talking about hardware vendors who are notorious for their excellent attention to software quality being clever. That's not a good mix. Another option I could have discussed is WebGPU, which is the most recent of graphics APIs that I'm familiar with. And basically, it was designed after 3 other APIs called VULKAN, Metal, and Direct3D 12, which are essentially VULKAN, Apple VULKAN, and Microsoft VULKAN. And the idea is that you should write a WebGPU application, and then it's portable to the native apps of APIs of Windows and macOS, which means that you can use native development tools for Direct3D or Metal. And while we are at it, let's make it work in web pages too, because people have been stuck with WebGL for too long. And that's great. And also because this API is designed to be so simple that a web developer can use it, you get an API that's less, let's say, detailed in terms of low-level access, and that exposes much fewer opportunities for undefined behavior because you don't want random code from the internet to trigger undefined behavior on your machine. The problem is, maybe this will be my recommendation tomorrow, but not today because it's too young. It's missing quite a few access to quite a few important hardware features. The gap is closing, but it's still there. And it's evolving quite quickly, which means that if you write a web GPU app today and you want to switch to an implementation of the latest web GPU norm in 1 year, you probably have quite a bit of code rewrite to do. They're still tuning it up. So maybe let's zoom out and take a higher level view. So if I try to compare the APIs that you might want to use to program GPUs, and I will do across a few axes. One axis is there built-in support for a particular operating system, how easy or hard it is to set up? Does it support a particular brand of GPUs? If so, is it official support for the manufacturer, or is it third-party support that another hardware manufacturer does when they have time? Or volunteers, even. And in terms of general API, is it easy to use, and does it give you access to all the hardware features? So CUDA works on Windows easily. On Linux, it's harder because anything GPU related is hard on Linux. And on macOS, it doesn't work. So GPU vendor support is easy. This is NVIDIA and only NVIDIA. And on the good side, it's easy to use, and you get full hardware access for NVIDIA hardware. HIP is AMD trying to copy NVIDIA's API because they have not listened to my previous slide. Because this is AMD software, it's a bit difficult to get working on both Windows and Linux, but eventually, with a bit of luck, you can manage. First-party support from AMD, obviously. For NVIDIA, it's AMD providing support for NVIDIA hardware, which is not great. And the trade-off overall for AMD hardware is the same as with CUDA. And then you have SYCL, which is, it tries to be a better CUDA. So again, setup on Windows is easy. macOS, no way. Linux, difficult. And there is basically only Intel supporting it, for providing first-party support. For everyone else, it's either Intel or volunteers contributing support for other hardware. Not great. But once you get it, it's an easy API. I would argue a bit easier than CUDA in a few ways. But because it tries to abstract over many hardware and does so using a least common denominator approach, you lose a bit of expressive power. There are some things the hardware can do that you won't be able to do in SYCL. We have OpenCL. As I mentioned, it's difficult to get working on any operating system and any hardware. It used to have first-party support on macOS. These days, it's deprecated because Apple wants you to use their proprietary Metal API instead. And even if NVIDIA claim official support, when you look at it, essentially what happens is they stop caring back in the OpenCL 2 days. They stuck forever at OpenCL 1.2. At some point, their users took notice and say, come on, this is terrible. Why are you not supporting newer OpenCL versions? And then NVIDIA did what every monopoly would do. They got an employee of them hired at the head of the OpenCL committee, who voted a new OpenCL release saying that all features since OpenCL 1.2 were now optional. Release that as OpenCL 3, and now NVIDIA can claim OpenCL 3 support. So in my eyes, OpenCL support on NVIDIA is dead. You may disagree. It's not that easy to use because it's a C API, so it aims to be usable from all programming languages. And because we are stuck in the past, since if we care about the biggest GPU manufacturer, we are stuck in the OpenCL 1.2 days. The expressive power is not great. We are starting to miss more and more important hardware features. So let's say, I mentioned graphics APIs earlier. Let's try them. OK, we have 3 main graphics APIs, or at least we used to have until recently. We have Direct3D, which is the Microsoft proprietary API. Works great on Windows, obviously. Doesn't work on macOS, obviously. On Linux, people care about being able to run their Windows game. So there is a third-party support from certain companies to emulate Direct3D on Linux, which I've heard works reasonably well, actually. Because Microsoft have enough political power to twist everyone's arm, the hardware support for all manufacturers is great. In terms of ease of use, as I mentioned earlier, graphics APIs are harder to use, and Direct3D in its 12 release took the same path as VULKAN of exposing all the hardware nastiness to developers. So Direct3D 12 is not for the faint of the heart, but in exchange, complete expressive power. Then you get Metal, which is the Apple API. Works on macOS, works on no other operating system, supports no hardware you care about. And it's closer to OpenGL, so it's a bit easier to use, still not as easy as something like CUDA. But it has full control of Apple hardware. And OpenGL used to be the way to get graphics app that work everywhere. Works great on Windows, used to work great on macOS. Today it's deprecated and they're going to drop support at some point. And works great on Linux, where forever it has been the only graphics API with broad support. Supports all the hardware manufacturers. A bit harder to use than CUDA, but not awful. And it's lagging a bit behind the newer hardware because it's effectively being replaced by VULKAN. VULKAN, what it brings you is you still get great Windows support. You can get it to work on macOS by layering it on top of Metal. So third-party implementation with all the caveats that this gives you. And you can get it to work on Linux. Actually, these days, it would be my main recommendation for any kind of rendering work on Linux. Supports all the hardware, harder to use than other graphics API because it's lower level, but full control. And wet DPU. Let's layer on top of everything. This day, we get full support, well, kind of full support everywhere. All the OSs, all the hardware. The ease of use is OpenGL-like, so easier than VULKAN, harder than CUDA. And in terms of expressive power, as I mentioned, it's a bit too new to support all the cool hardware features. No tensor cores, for example. Okay, yeah.
Adrien, just now you can use tensor cores with VULKAN.
That's why VULKAN has the green check mark.
Yeah,
and it's not now. It has supported them last year already. You just learned about it.
Yeah, but it was announced this year. So.
Yeah.
Will it be possible to use macOS with VULKAN for the Rust?
Yeah. Okay. The idea is that you should install a layer called Molten VK, which basically layers on top of Metal and pretends that Metal is VULKAN, and with a few caveats, it works.
Is it already on the container? In the container?
It's not in the container because you need to install it on the host.
Okay.
That's the tricky part. And finally, an update that I've been wanting to make for 2 years of this school now. So I mentioned earlier that the intent of VULKAN is that you should be able to plug a higher level layer on top of it. You know, do not use the low level API all the time. Use a high level layer when you can and switch to the low level when you need. So how is the Rust support? There was this cool project called kernel, which tries to provide a CUDA-like user experience where you write your kernels in Rust and you write stuff like iterator-based for loops and magic happens. Unfortunately, there has been no commit in the past year, and in my opinion, it's not in a state where you can call it finished. So I have some support concerns. I would not recommend using it right now. kubectl is a much newer project which does something beautiful and terrible. They basically implemented their own compiler as a plugin to the Rust compiler so that you can Rust code, you can still write Rust code, but now it's compiled at runtime, so you can do all sorts of fancy stuff to tweak the generated code right until runtime. The problem is, as any kind of project that does this sort of crazy code generation, the documentation is terrible. You could have well say it doesn't exist. And even the authors do not pretend it's ready for production yet. So maybe not. And one last stuff I mentioned in my previous talk is LLVM offload. The idea here is that, you know, the LLVM people took a great pain to get OpenMP4 sort of working. Rust uses LLVM as a backend. Can you use that? Well, right now, there is a project to get there, but it's not even in the official compiler repository yet. It's in a fork, and it's not finished at all, so not ready. Which means I will stick with the technology I've been presenting in previous years, which is Volcano, which is more, you know, let's use VULKAN explicitly. We do not hide it's VULKAN, so it's not CUDA-like, but let's try to ease a bit the most difficult part. So overall, my conclusion for this talk is, in my opinion, VULKAN does a better job than anything else I've experienced at providing a solid backend to get code that's portable across all hardware. Beautiful hardware support, excellent driver stability, never gotten a driver bug in VULKAN so far. I wish I could say the same about OpenGL before that, or OpenCL. But in exchange, it's super low level, hard to use, undefined behavior everywhere. And it so happens, you know, we have this language, it's called Rust. The idea is, well, when we are doing system programming, we are used to having undefined behavior everywhere. And there are some tricks that programmers have studied for years to work around that. We can have a static analysis based on the compiler, dynamic analysis where static analysis doesn't work. So it looks like these two communities could do something together. Let's give it a try. And by the way, just to silence the naysayers. Some people say that visualization doesn't matter because they cannot do it. But I will show you that it looks extremely cool, and having an API that lets you do it, it's important to have. The command line is a bit long because I did not save it, sorry. And there you go. So this is the same Grayscott computation you've been studying for a bit of time now, running on GPU. And the cool thing about it is that every time it renders a new image, instead of saving it to an SDF5 file, it just displays it on the screen so that you can see what's going on without waiting for several minutes to the computation to complete. It's much better for debugging, and it's also great to show off. And with that, let's move to the practical part of this presentation, this course. Do we have any questions so far? Right. Yeah. Nothing on Discord so far in the room, perhaps, or elsewhere in satellite sats? If not, the course material is at a location I have posted on Discord before, in a vain attempt to try to get you to set up your environment before the course. Because as you will see, if you have not done so yet, GPU environment setup can be a bit of a pain. Assuming you did set up your environment, I will put in the Rust channel the instructions that you need to update to the latest version of the course material. And once you've done with that, you can go to the next page and start working on the course proper. I will leave you a bit of time to do that and start, studying the material. As before, because I don't know which background you're coming from, this is a self-paced course, right? Some of you will have an easier time with the Rust part, with the VULKAN part. Some of you with neither. Good luck. And if you have any issue or any question, please let me know. And maybe half an hour, I'll start walking you through the material as I did before for the CPU course. Window management. As usual, I will leave the sound on to get this notification from outside the room. And by the way, regarding the molten decay stuff, you may want to check in the environment setup instruction. There are two parts. One is how you set up your local system to get local GPU access. The other part is how you set up a container or a local development environment, depending on which you prefer. And the first part explains how you get VULKAN working on macOS. Regarde ça.
C'est pas grave si ça marche pas parce que j'ai le compteur. Mais quand je run ta commande pour tester l'installation,
Ouais.
à la toute fin de la compilation. J'ai ce problème avec les shaders de compte.
Oui, mais ça, c'est bizarre parce que normalement, c'est censé être une dépendance.
Non,
Que se
j'ai mal
passe-t-il?
fait le truc avant.
Non, non, mais je sais pas. Attends, on va voir.
Si. Container, normalement, ça marche.
Ouais.
C'est bon.
Non, mais on va y aller doucement, on va voir ce qu'il fait. Donc, on est où? Est-ce que c'est... Non, c'est pas comme ça que ça marche, celui-là. Comment on vide la commande en cours? Ah, ok. Ok, donc on est là. Et ma question, ça va être... Ça, c'est très bizarre ce qui se passe. Parce que lui, tu vois, il est censé être là. C'est ça qui ne va pas. Pourquoi il ne le voit pas? Au cas où. On vérifie. On fait repartir du début, on ne sait jamais. Et c'est sur quel binaire que je te vais lancer? C'est sur Square, je crois.
Square, ça va afficher ça.
Ah bah, info déjà, avant ça, ouais. Puis en fait, on n'a pas besoin d'avoir en release, c'est plus quand on n'est pas en release. Alors, on repart de zéro, bien sûr qu'on a tout. Le piano pense à vie à compiler, c'est ce qu'il fait. Il faudrait vraiment qu'ils apprennent à modulariser en plusieurs secrètes. Et tu vois, ça, ce qui me perturbe, c'est que là, il l'a compilé. Là, il ne la trouve pas.
C'est un problème de chemin, parce que j'ai vu que tu avais un endroit dans ton explication où tu dis qu'il fallait faire attention. Je vais récupérer le fichier.
Alors ça, c'est dans un conteneur ou...
Non, là, je suis en local.
En local.
Ça que
Alors... On va le cogner comme ça. Est-ce que ça sent les bêtises, genre les variables d'environnement, ça?
Ouais, c'est ce que
je savais même pas que c'est variable d'environnement, ça c'est rigolo.
dans le ciné, quoi.
Ok, c'est binôme.
Je pense que c'est ça qu'on avait déjà installé.
Ouais, ça va servir à compiler les programmes GPU. Si c'est dans normalement. Ça c'est bizarre, mais pourquoi pas.
Ouais. Il n'y a pas de...
Ça me choque pas. C'est pour les conteneurs que j'avais besoin de faire une bidouille. Parce qu'en fait, alors ça c'est une connerie avec le pilote NVIDIA. Le pilote NVIDIA, il a deux implanes VULKAN. Une pour X11, une pour Wayland. Voilà, NVIDIA. Et il se trouve que la logique qui sélectionne le bon backend, elle est pétée. Et elle ne sait pas se rendre compte que quand X11 n'est pas là, il n'est pas là. Et seulement sur un conteneur en local, il y avait. Et du coup, je vais pas trouver exactement pourquoi la logique de sélection automatique se plante. Mais ce que j'ai trouvé, c'est qu'en modifiant une variable d'environnement au bon endroit, tu peux dire non, mais tu veux utiliser le backend qui marche avec en l'occurrence, Wayland ou en headless. Et moi, je suis en headless, et après, ça marche. Donc ça, normalement, tu as un peu besoin en local, parce qu'en local, il est moins bon. Mais ouais. Ça me plaît pas. Qu'est-ce qui peut se passer d'autre?
Peut-être par mon... C'est ça. J'ai dit que tu peux variable comme ça.
Mais ce serait normal, non? Je sais pas. Ou alors un fichier de config. Est-ce qu'on peut lui demander un peu plus d'infos, des fois qu'il nous raconte des choses? Alors, qu'est-ce qu'il fabrique?
Tu vas
tiers. Et là, il y a un lead Volcano Shaders. Donc ça. C'est vraiment bizarre, quoi. Et tu sens qu'il y arrive presque, mais pas tout à fait.
Je regardais un peu sur le lead, j'ai vu le mec qui avait le même problème. Il avait essayé de changer le cargo toi-même. En faisant, j'ai pas réussi à résoudre.
On est sur une release qui date de hier.
Ouais.
Est-ce que ce serait pas une connerie avec un bug de la release qui date d'hier? Enfin, non, qui date du début de l'école.
Ouais, ça, c'est pour qu'il y a quelques jours. Non, non, ça serait bizarre. Après, tu l'as pas mis à jour.
Peut-être que moi, je l'ai pas mis à jour.
Ouais, ouais.
Bah, on va tester, hein, de toute façon, c'est comme ça qu'on sait. Hein. Ça, c'est moche. Normalement, il essaie de les détecter, les releases pétées quand même. Mais bon.
6.3, ouais, c'est mieux.
Parce que j'ai pas eu accès à une connexion Windows Phone depuis que je suis à l'école. Bon, j'aurais peut-être pu enlever Gerbose.
Ouais.
Volcano prend sa vie, c'est ce qu'il fait. Il faudrait vraiment qu'il le prenne plusieurs crates, c'est un problème. Bah en fait, c'est le truc que tu prends quand tu essaies de débugger ce qui se passe. Quoi. Non, ça marche toujours pas, donc c'est pas ça. Ok. Les fichiers de config, est-ce qu'on en a ici? Non, on en a pas.
Est-ce que c'est pas une fois con le changement de nom? Parce que là, il arrive à voir chez eux, il n'arrive pas à trouver le nom de facture.
Bah, ce qui est bizarre, c'est que tu vois, le truc, c'est qu'il y a une crate, il a vu qu'il y avait une crate, il l'a mis en dépendance, il l'a compilé, et après, il la trouve pas, et ça, c'est vraiment spooky. J'aimerais bien savoir qu'est-ce que c'est que ça. Qu'est-ce que ça peut être? Sinon, au pire, il est conteneur. Mais là, il y a un truc bien fichi, là.
Là, le code de test est tourné. Trop de messages d'erreur. Après l'avoir en local.
Bah oui, je comprends. Hein. Ouais, bien sûr, mais là, ouais, ça va prendre un moment. Je veux bien en revenir dessus à la pause. Mais ça, ouais, ça va me demander plus de 10 minutes de debug. Ouais. Le dossier exercice, vous le téléchargez en fait. Je vous donne des commandes curl pour récupérer une archive dans laquelle il est et l'extraire. L'idée, c'est comme ça que vous avez toujours la dernière version, c'est séparé du conteneur en fait. Parce que le conteneur, bah, c'est 1 giga de download, alors que le fichier exercice, c'est quelques kilooctets. Donc, vous avez tous vu comment la connexion ici s'en sort bien quand on se met tous sur des images. J'ai essayé d'éviter ce scénario. Je vais te parler de Must pour te dire que je suis extrêmement satisfait. Parce qu'il y a quelqu'un qui a essayé hier, qui, en suivant les instructions à la lettre, a vu les devices dans un conteneur sur Must. Et ça, c'est magnifique. Ça devrait être illégal, un environnement GPU qui marche aussi. Quoi? Ouais, bah, je peux leur faire un peu le topo Must. So,
If you would like to follow this course on the must cluster rather than on your own computer, you have two options. You can use the Kubernetes platform that you have used before. It will be as easy as before. However, you will not have access to a real hardware GPU because the Kubernetes cluster doesn't have GPU hardware, so we cannot expose what is on there. What you will have access to is a CPU emulation of a GPU, which I will argue is enough to understand the general logic of the API, even if you will not get any kind of realistic performance numbers. But if you want a real GPU and you are ready to work for it, then you can go to the LAPP UI, the SSH interface, and there you will be able to run containers almost as you did for other courses, except because the NVIDIA driver is the NVIDIA driver, and like the French, it doesn't do stuff like everyone else does. You will need a few extra arguments when you run your container, which are explained in the environment setup, Linux containers. It's this pair of arguments. Actually, do they use Docker, Podman, or Aptainer on Must? Aptainer? Okay. Then you will need these two arguments. So the thing is, the NVIDIA driver, because it doesn't know anything like anyone else, is made of two related software components. One is a kernel module, the Linux kernel, that does the low-level hardware interfacing. And one is a bunch of libraries and random files inside /USR and so on, which handle the high-level aspects. These components are tightly coupled. If you try to use one version of this thing with another version of the kernel module, you will have problems. This basically breaks the whole concept of Linux containers. Because the idea of a container is you keep the same kernel and you change all the files. As you can see, this cannot work. So there is a hack sponsored by NVIDIA, which allows you to work around this by taking all the relevant files from the host and mounting them inside the container. And for CUDA, the hack works perfectly. But for VULKAN, there is one problem, which is that it's selecting the wrong VULKAN implementation, because yes, there are two VULKAN implementations in the NVIDIA driver, obviously. And so you need this environment variable to hint it in the right direction. And when you do these two things, you should see your GPUs inside of Aptainer on Must. Yeah. Ouais. Donc c'est quoi ton hardware? Ok. T'as installé le driver comment? Il y a une petite chance que tu l'aies installé via le paquet CUDA, qui contient un driver, mais juste de mémoire les bouts pour que le CUDA fonctionne et pas les bouts pour que VULKAN fonctionne. Si c'est le cas, la solution, en fait, c'est, en tout cas sous Ubuntu, CUDA, il est packagé de deux façons. Tu as un paquet qui s'appelle CUDA qui ramène son propre driver, et tu as un paquet qui s'appelle, je crois que c'est CUDA-toolkit de mémoire, mais tu trouveras ça avec NVIDIA, qui ne contient pas le driver. Une fois que tu as installé ça, tu peux installer le driver comme tu veux, et là, tu installes le paquet driver complet avec la méthode que tu préfères en 36 000, et à la fin, tu devrais avoir un driver qui marche pour du VULKAN aussi. Ouais. Donc du coup, c'est peut-être au niveau de l'install driver qu'il y a un truc. Essayez NVIDIA SMI déjà pour voir si le driver il fonctionne. Ça, c'est pas bon qu'il mette un peu de temps, mais c'est bon. OK, il est parti. Donc ouais, le driver, il a l'air OK. Donc c'est pas ça. On est sur quel genre de hardware? Déjà, on le fait marcher en local avant de toucher à Aptainer. Parce que si tu ne le vois pas en local, tu ne le verras pas non plus dans Aptainer. En fait, ça rajoute une complexité par-dessus. Donc du coup, bon, de toute façon, tu as le VPU Intel au pire. Mais on est sous Ubuntu. Ouais. Normalement,
Là, il y a un truc qui s'appelle pilote propriétaire, comme ça. Je vais te dire, on a 36 000 versions de driver, parce qu'une seule, ce serait trop. Et pour ton hardware, en fait, pour tous les nouveaux hardware, le driver open, c'est devenu la recommandation. L'idée, en fait, c'est que NVIDIA, ils ne veulent pas faire des pilotes open source, c'est pas leur genre. Et le problème, c'est que les développeurs de Linux, ils ne veulent pas non plus avoir des API stables. Parce que eux, leur idée, c'est qu'on veut pouvoir changer nos API quand on découvre qu'elles sont cassées. Et du coup, bah, ces deux entités politiques étant en conflit, tu as des problèmes techniques qui en émergent. Le NVIDIA Open, en fait, c'est la dernière tentative d'NVIDIA d'avoir une solution technique un peu meilleure à ce problème humain. Où en gros, l'idée, c'est qu'ils ont dit, bah, on va vous sortir un tout petit bout de code en open source, qui derrière est une télécommande pour le vrai driver, qui lui tourne sur un CPU caché dans le GPU, auquel vous n'avez pas accès. C'est un hack dégueulasse, mais l'avantage, c'est que du coup, bah, comme c'est sur une vraie licence open source, les distributions ont le droit de le mettre dans leur dépôt, et donc ça a moins de chances de péter à chaque mise à jour kernel, parce que bah, c'est maintenu synchrone avec le kernel.
Ok, c'est juste ce qu'il faut pour pouvoir manipuler.
Tout ça pour dire que normalement, en mettant ce paquet-là et en rebootant, ça devrait passer. Je voudrais juste vérifier que c'est ça d'abord. Enfin, donc, en tout cas, sur le long terme, il faudrait que tu passes à celui-là, mais c'est peut-être pas forcément besoin maintenant si celui-là il marche.
Après, je pourrais avec les étapes.
Mais est-ce qu'on peut voir s'il n'y a pas une autre arnaque? Je ne sais plus si l'arriveur de base, quand il installe, il te ramène le truc dont tu as besoin pour faire du VULKAN. Il faut en plus faire ça. NVIDIA, c'est vraiment un truc que tu n'as pas envie de regarder sous le capot. C'est vraiment l'illustration de la phrase de Bismarck sur comment est faite la saucisse, le pilote NVIDIA. Ok, ça marche, mais à quel prix? J'essaie de me rappeler. On va supposer que c'est à la fin de la liste, sinon il faudra un petit laisse. Hein.
Une centaine.
Peut-être tous les drivers de tous les temps. Ouais. Sites. J'ai galéré pour, c'est un peu la définition de l'installation de cette NVIDIA sous Linux, malheureusement. Mais... on n'est pas aidé. Ça, c'est pas ce qu'on veut, on veut un écran. C'est bien les écrans. Sinon, il y a peut-être une autre connerie, mais j'espère que c'est pas ça. C'est, tu sais, Optimus. Le fait que tu aies deux GPU. Je sais pas si la façon dont ils l'ont fait, ça cache même pour VULKAN, ça me surprendrait. Mais... si c'est le cas, il faudra peut-être regarder un peu. Des fois, ce soit au début de la liste. Tiens. Le problème, c'est que je suis pas sûr du mot-clé complètement. La recherche, ça marche quand tu es sûr de ton mot-clé. Visual Tool, j'ai pas besoin de faire un pratique quantique, même s'ils ont un pilote quantique qui marche pas selon les jours. Ouais.
Il marche de façon quantique.
C'est ça. Moi, à un moment, ils m'ont fait chier une fois de trop, voilà. Et j'aimerais bien qu'on essaye d'installer ça si ça ne l'est pas déjà, parce qu'il y a peut-être moyen que ça fasse le boulot. Des fois que des sagouins, ils pourraient leur appeler VULKAN dans leur appel OpenVL, et ça a l'air d'être le cas. Parfait. Et on a dit qu'on était sur quelle version, d'ailleurs?
560.
Et donc là, il y en a un qui, j'ai l'impression, est censé être là, mais qui du coup ne marche pas. Intéressant. Donc il te dit que t'en as déjà un qui a un 133 et c'est pas 158. Soit ils sont pas compatibles entre eux, ça ce serait moche. Bon, ça pareil. Bon, je le garde pour la pause, c'est pas le truc que je vais débugger en 10 minutes. Bah, ça a été un peu confusion à l'époque, après avoir débugué une fois de trop un pilote NVIDIA qui était mort à une mise à jour kernel, c'est je vais en fait plus jamais être de plus NVIDIA dans mes machines et ça va être mieux. Ok. Donc,
NVIDIA card is not easily supported.
I'm so sorry.
No problem. I still have the Intel one.
Are you going to try to use the LLVM pipe?
I love debugging GPU.
Use the container with
So,
the Intel one. That's okay.
I know that for some of you, as expected, environment setup is going to involve a bit of a pain. This is going to be the perfect occasion to remind you that in case you give up and want to see the rest of the course after the environment setup, CPU emulation is available. It will not give you a native performance, but it's easy to get working. Your choice. So, for now on, let me a bit do a live explanation of the beginning of this tutorial. The whole idea of VULKAN is that compared to other GPU APIs, it hides less things from you. It gives you a more complete view of your system, and it gives you more explicit control about everything. With this great power comes the great responsibility of setting everything up correctly. Because direct VULKAN usage, as I mentioned, can be a bit of a pain, I propose that you use Volcano, which is a slightly higher level layer. It does not hide that many VULKAN concepts, but it does, by default, automate a few aspects of VULKAN that are particularly tricky to get right in order to give you an API which is type, memory, and thread safe by default in Rust edition. In the spirit of VULKAN, if you ever encounter a situation where the high-level layer does not do what you want, it's not fast enough, it does not let you do something you want to do, there is always a way to drop lower level when you need. Volcano has been set up as a dependency in a particular way in the example code base, because by default, it imports the required libraries for X11 support, which means that it requires the host system to have X11 libraries installed, which means that now I need to add to the container all the X11 stack, and that adds a bit of weight. And you know, containers are a bit like, let's say that fashion magazine, they always want to lose weight. So I disabled the X11 support because we are not going to do rendering today. And then I can, in my application, start my Volcano journey by calling the constructor of a first Volcano object called Vulkan library. What this will do is it will look for the default Vulkan library on your system, which will typically be some variant of /usr, /lib, /lib vulkan.so.something on Linux. And it may fail. That's the thing with GPU, anything you do may fail. In this particular case, it may fail because you do not have a Vulkan library installed, for example. This means that we now need to handle errors. The way we handle most errors in Rust is using the result type, which is a variant type that can contain values of two types, either correct results or
another type which signals an error and explains what kind of error was encountered. This is a great thing to have when you are writing libraries, because you can have tailor-made error types that can describe the various error case of your libraries, and then this serves as documentation for your user. But here we are going to put ourselves not in the shoes of the library developer, but in the shoes of the application developer. And as an application developer, when you encounter an error, many times we have two choices. Either we try again or we give up. Which means that we can go with a much more blunt tool, which is to use the box din error type as an error type, which is basically compiler black magic that can store any concrete error type into a heap allocated location. The heap allocation only occurs when you have an error, so no performance penalty in normal application execution. But you have convenience that you can return any error type to your function. It will be automatically turned into this thing, and you don't need to care about it. And at the end, you still get the proper error report. Sorry, this doesn't work. Once we have a VULKAN library, we can do stuff with it. We can check which version of the VULKAN specification it supports. I mentioned that VULKAN is backwards compatible, but it's adding features. So if you want to use a newer VULKAN feature, you may care about having a new enough VULKAN version. It tells you which extensions are supported. This is a mechanism you need because there are some things you may want to do in VULKAN that do not make sense on all machines. I mentioned X11 earlier, for example. It's nice to be able to create an X11 window and start rendering to it. But if you are on Windows, it doesn't really make sense, right? So all the windowing system integration is one example of a VULKAN extension. It's available in case you need it. It may or may not be there on your system. Your application should know how to use the right extension for the right job. In the particular case of windowing, there is a good abstraction around it called WinIt, which I will not cover in this course because I'm not doing real-time rendering. And then we have a third thing we can check in the VULKAN library, and that thing is layers. Layers are something new in Kronos API. They did not exist in previous APIs from the same author like OpenGL and OpenCL. The general idea of a layer is that you can say now, when the user calls a particular function of the VULKAN library, I want to be able to intercept this call and do something other than the default implementation that may involve calling the default implementation at some point. This is very convenient for stuff like optional debugging functionality that you want to enable to do a more thorough checking of your debug builds, then disable in release build for better performance. As you can see, the first thing we see when we get exposed to VULKAN is optional features. And as you may guess, this means that we need to say which optional features we want. And this exposes us to a first example of a pattern that is highly prevalent in the VULKAN API, which is that we start with an object that describes what is there. We say what we want, and we get an object which represents an initialized version of the stuff we queried earlier. In this case, the initialized version of the VULKAN library is called the API instance. To set up an instance, we will use a pattern which is inherited from the VULKAN side of things, but a bit adapted by Vulcano, which is the info struct. The idea of the info struct, it has a bunch of fields. You can fill them however you want, and they have a sensible default value when you don't care. This can combine really well with a Rust feature called the functional struct update syntax, quite a mouthful, which looks like this. So the idea is you say, I want to create a struct. This member must have this value. This member must have this value. For every other member, take it from this other copy of the struct. In this example, we are using it to set the flags field of the instance creation info to say that we want to enable an optional VULKAN feature, which is the enumeration of portability devices. What is that? When VULKAN was designed, we are in the 2010s, the idea was to be an API for the next 40 years and not get encumbered by the past. So they set the base hardware requirements to what they thought was the sensible minimal hardware of the days. And then they needed to support macOS, and they realized that the macOS GPUs were even below their intended supported subset. And another thing that happened is that they wanted to be able to layer VULKAN on top of OpenGL for compatibility reasons, and then obviously it doesn't apply anymore, right? So they introduced this escape hatch, which is to say, okay, you can opt out of the default device requirements. If you do, be careful. You cannot assume that what is written in the spec about minimal device requirements is true anymore. You need to check. Or let your application crash if the device you pick does not meet the requirements. And then we use the struct updates syntax to use a Volcano feature, which is that normally when you create a VULKAN instance, you tell the VULKAN API, by the way, my application is called like that. It's this version. It has, it uses this engine if you're a game. And this is intended so that later GPU drivers can do horrible hacks by fixing your bugs on the driver side so that your application works better on their driver than the competitors. The realm of GPU hardware is fantastic. Anyway, if you want to support this dreadful practice and be a good VULKAN citizen, what you can do is at least not repeat information that you have already written in your Rust project metadata, and Volcano has a feature for that. There are a few things that we would like to enable as well. There is something, as I mentioned briefly, called the validation layer. The idea is this. When you do GPU development, you can end up making many calls to the GPU API. In OpenGL, each of these calls had to check if the parameters to the call are correct. And if not, signal an error and so on. And there were some real-world applications that were bottlenecked by the error checking. So VULKAN did a terrible thing here. They said, OK, we do no error checking by default. Invalid parameters are undefined behavior. Be careful. That may be nice for performance, not so much for correctness and debugging, which is why you have this optional layer that you can use, which brings back basically the checks from OpenGL that you use the API correctly. And because now it's optional, it's actually even more thorough than it was in OpenGL. It checks things that the OpenGL drivers did not use to check, like, are you doing multi-threading correctly, for example, that sort of stuff. And there's more than this. You also have the best practices. The best practices are basically a linter for your VULKAN usage, like the compiler warnings. Except this time it's a runtime, so it knows the full state of your application. And it can make comments based on that, like, oh, you are doing this, but in this particular context, maybe you should be doing this instead. So it's not necessarily an error, it's more of an advice. A typical VULKAN application may want to do things in this particular way. And there is a third feature in the validation layer, which is probably the #1 reason why real-world people use it, which is that now you can do printf inside of your GPU code for debugging, obviously. You would not leave that in production. The performance is horrible. And also, let's say the implementations are not top quality in terms of stability. There is a second thing that you will really want to enable, and the validation layer, because of the performance impact, I would say enable them in debug builds, maybe leave them out in release builds. Debug utils, I would leave on all the time, even if the validation layers will tell you not to. What this does is it lets you get log messages from your VULKAN implementation. So now you can get some information about the process it went through during initialization, any errors that were encountered, suspicious behavior, warnings. And this is invaluable when you are trying to debug an application which seems to start but then doesn't work. So how do we enable these things? First of all, because they are all optional features, we need to check if they are there. This will be easier to do if we move away from the struct update syntax that I mentioned earlier. Unfortunately, this time it's not a good use case for it. We will use a more imperative style. So we start with a mutable variable at a certain value, and we will modify its fields using the mute feature. We check if we are in a debug build, if the validation layer is available. If it is, then we enable it. And back in the VULKAN 1 days, 1.0, that would have been it. But people got greedy. They say, yes, but you know, validation, it's not a black and white thing. Sometimes full validation has too much overhead, and we want a smaller validation, and so they made it granular with fine-grained configuration. And this means that, no, we need to take care of this. This is an example of a code that enables almost all the optional features you may enable, with the exception of one. Unfortunately, I had to leave it out, printf. And the reason is printf is incompatible with another validation layer feature, which checks what you are doing on the GPU side automatically, and which I think is more important. But if you disagree, just change this. So we put it all together. We have validation layer configuration done. How about logging now? So here we are going to use a VULKAN extension called debug utils. And this is configured as usual in VULKAN with an info struct, where you will need to specify first which message severities you want to handle. If you've been using any kind of production-grade logging system, like maybe Log4j after they patched it, you may know about the notion of having a minimal logging level and printing everything which is a higher priority than that. Interestingly enough, VULKAN does not work this way and decided to do something which is completely different from everyone else. Instead, you get a bit field where you choose which severities you want to enable one by one. I'm sure someone at Ubisoft will tell you that it's very important that you are able to send errors through one communication channel and warnings through different communication channels. For the rest of us, it's a pain, but a pain we have to deal with because the decision has already been made. Then we have message types. For our purpose, we don't care. We enable all of them. We want to see all the messages. Again, we don't want to treat them in different ways. And finally, we need to specify what happens when a new API log comes in. Here we need to be careful. This is one of the few places where Volcano did not manage to save you completely from yourself as a Rust programmer. There is one very important rule about your debug utils messenger callback that you need to remember by heart. You must not make any VULKAN API call inside of this callback. The reason why that is the case is that this callback may have been called by a VULKAN API call. And the VULKAN API call you make can, in turn, generate more logging messages. And hopefully you can see where this is going. So don't do it. We are not going for the full fanciness of production-grade loggers like Prometheus, syslog. That's way too much for us. We will just send our logs to stdr like a good Unix program. And what we will find is that actually there is some, it's not just a message, it's more of a structured logging. You have some detailed information in a machine-readable manner. I will just give you the example at the end, but you can ask me more about it if you want. Altogether, we have some optional features. It's not nice to hard code in which optional feature we are going to enable. So we are going to expose a few of them as command line arguments, as we usually do. One thing we will expose as a command line argument is portability devices, because remember, these may not behave like your normal Vulkan device. There may be surprises. So you may not want your application to search them by default. You may want that to be an explicit user action, and then the user accepts the consequences. And another thing I do is I enable the warning and error messages by default, but not the info and verbose message, because the verbosity is enormous and then you cannot see your normal application logs anymore. So I want to have them around because sometimes they are useful for debugging, but not by default. And I handle this the way Unix programs do with a minus lowercase v flag that you can specify multiple times to get more and more verbosity if you need it. So it looks like this. We say by default, we enable messages for errors and warnings. If we have one verbose flag, we enable info2. If we have two verbose flags, we enable verbose2. We enable all the message types always. We have our user callback, which is not safety checked because unfortunately, Vulkan does not have divine power of knowing whether your code is calling the Vulkan API or not. So we, as programmers, tell Vulkan that we've been careful and there is no Vulkan API call to see here. And then we format any optional part. Sorry about this. Maybe I will just cut this for now because it's for live debugging. Yeah. Let's cut this. Okay, so we have some optional structured parts, like a standardized name for the message. If we have it, we print it. And then we format that into some nice way. This is not all the metadata you have, but it's the one you will need most of the time. Finally, we put that all together in the debug utils info struct. Same logic as usual. You spell the message severity, the type, and the rest is given by a constructor that only takes the callback, which is a parameter that you always need to give. Now we have our validation layer configuration or logger configuration. We can start creating our instance. So we assume that the user has somehow set up a Vulkan library. We set up some basic info. We enable portability devices if the user has said that they're ready for the trouble. We enable validation layers if they are present, as discussed before. We configure logging if the implementation supports it. And now you may ask, why would my Vulkan implementation not support logging? When you have a stupid question like this, usually the answer is embedded. So embedded. They managed to save a few kilobytes of their Vulkan implementation by not having logging support. Then you set up an instance, and then you set up logging. And now, if you are careful by looking at this code, you may notice that I set up logging twice. That's, let's say, interesting Vulkan API decision, where you set up logging in a different way before your instance is initialized, and during initialization, and after initialization. And I don't know why they did it that way, and to be frank, I don't want to know. But in any case, we can copy and paste the same config. And the only thing we need to take care of then is that the runtime logger is an RIII object. So it will log while it's live, and when it goes out of scope, it stops logging. We obviously wanted to keep logging, otherwise we don't get log messages anymore. And the way I propose to handle this is to have a struct which is composed of our instance in this case, and a logger if we have one. And this way, we know that the logger will be live until we drop the instance. And later, when we build more Vulkan objects, we will use a fancier variation of the same idea. with this, we have enough tools to build an instance, and we have enough tools to build our little clone, a limited clone of the standard VULKAN info utility. So that's exactly what I did. I wrote a little binary that probes the properties of your VULKAN library, prints them. Well, it can print them in the right configuration. And then, once you have an instance, you can enumerate all available VULKAN devices, all your GPUs and so on, and you can see their properties as well. And the idea is that, unlike VULKAN info, this program has sensible defaults. So by default, it prints a small amount of information, and if you want more information, you ask for it. And this allows you to play a bit with your system, understand more your devices, and so on. And that's what I propose to do as an exercise, is to play a bit with it. And then look at the source code and see how it's done. I think that will be it because we are close to the coffee break. So I'm going to look at the Discord comments. I'm totally watching the stream live right now. I'm part of it even. Someone appreciates my snarky comments in the practical text. Thank you, John. This is just David closing polls automatically, and here I think we have nothing. Okay. So no question on Discord. Do we have any question in the room now? Yes?
In the logging instance, if you didn't need to use the library, could you use like those fancy schmancy things like phantom data so you can like pin the lifetime to something?
Can you speak a bit louder or I get closer?
Yeah, do you actually need to use the library in the logging instance that you created? In the struct that where you define the logging?
Yes. So which one? Let's take this big format again. Tell me when we reach the right one.
Where is
Below, above?
below, I think. It was
This
like
one?
the last thing you talked about.
This one?
No, it's where you had
After the
this.
instance
Oh,
setup?
there. Do you in there? Do you actually use in that struct the library a little bit above there?
Okay, yeah, the thing with the two members.
Mm-hmm. You said that you create this struct so that it stays like alive during the lifetime of instance. Do you actually use instance, or could you do
No,
something?
I don't use it, and that's why I'm going to eventually replace this struct with a different one that keeps the logging member. But from an API design point of view, it was here to show you, we build the instance, we are done with that, and then we will build something else on top of it.
Okay.
That's actually, something which is a bit of a Vulcano-specific design decision. Normally in Vulkan, when you build an object of type A that's based on a different object of type B, you are responsible for keeping the object of type B alive until the object of type A is destroyed. Otherwise, you get undefined behavior. Because Vulcano aims to be memory safe by default, it doesn't work like that. So the high-level API instead uses reference counting so that you don't need to care about it. You can keep your object of type B, and it will keep the object of type A, and it will keep the underlying object alive as long as necessary to avoid undefined behavior.
Could you alternatively then use fancy things like phantom data to like pin the lifetime without actually storing it?
Sounds like something that could end badly, but if that's your kink.
Mm-hmm.
Any other question? If not, I propose we take the coffee break, and then I will fix a few setups if they did not magically start working again in the meantime.
shares. I thought you were also working.
All right, we're back. So as before, in the in the CPU course, nice pun. I will start this new session again by going through another part of the course. So in the previous part, we saw how we can load the system's VULKAN library, and we can proceed to configure it by saying which optional feature we want to enable until we get something that's called an instance. And then, as an exercise, you saw how we can query this instance in order to know which device we can manipulate using VULKAN and what are their properties. The next step is actually a bunch of steps, but which I group together because in most applications, you will want to always do it in the same way, and they are not that difficult individually. And I will call that, in a true graphics programming tradition, a context. So what do we need? First of all, we have potentially many VULKAN devices. On my laptop, for example, I have 4 of them. Unless you are ready for multi-GPU programming, which you may think you are, but you are not, you will want to pick one of them for now and get something working with one, and then we can think about using multiple ones. So what do? We could do what OpenGL basically did back in the day, which is we take the list of available devices, we pick the first one, and hopefully it will be the right one. If you ever had one of those laptops with an integrated GPU and a separated high-performance GPU on the motherboard, you know that this may not go so well. We could interactively ask the user, which GPU do you want to use? But if you've ever used one of those, played one of those video games where every time you start the game, it asks you to pick which resolution you want, you know that this gets annoying really quickly. So we don't want to do that either. Or we can do what good system programmers do, and we can guess. And the way we are going to guess is we are going to check some properties of the device and pick one that hopefully has the right property for us. The problem is guessing is difficult, and this is a one-day course, so we do not have the time to implement production-grade guessing. So we are going to do a guess that's not perfect. It's going to pick the wrong device sometimes. So to compensate for this, we will use actually a mixture of 2 strategies. One strategy will be to, if the user specifies no parameter, we guess. And strategy number 2, if the user wants a specific device, then they can ask for it via the command line. And this gives us a kind of best of both worlds at a relatively low development cost. So it looks like this. We have a new command line parameter called the device index, which lets us optionally specify as a user, I want device number something, where the something is the position in the list of VULKAN devices. And if the user tells us which device they want, then we will take the device list from the instance. We will look for the nth element of this list. And if there is none, if there is some, we will do a bit of printing to tell the user, I picked this device because your system device list, the VULKAN device list may change depending on configuration details, which means that device number 0 may not be what you think it is. It may change from one to another. So it's a good idea, you know, it doesn't change on its own, but it can change based on something you do. So it's a good idea to remember the user what they are using so that they do not use the wrong device by mistake. And if we find no device, we say, sorry, you're wrong. You asked for device number something. There is no device number something. Try again. And if the user does not tell us which device we want to use, then we guess using a particular device property, which has been in all Khronos APIs since at least OpenCL. I'm not sure if it was in OpenGL before that, which is the device type. And that's a broad categorization of device, which says this is a discrete GPU. So it has its own cooling system, it's a dedicated chip on the motherboard, or it's a separate PCI Express card. Or this is a virtual GPU. So we are a virtual machine. Someone mounted a GPU into our virtual machine through a PCI pass-through, and we don't know what it is. Because people who run virtual machines tend to have production servers with discrete GPUs, we will guess that this is hopefully a discrete GPU. As I mentioned, this is guessing. It's not, precise. Then our next priority tier is we have an integrated GPU, so the kind of stuff you find next to your CPU cores. So this is usually much lower performance than the discrete GPU if there is one, but it uses less energy, which is why it's there, and it's better than nothing. Where nothing in this case means the next device tier, which is we don't really have a GPU, so we are going to take a CPU program that pretends it's a GPU and hope for the best. And then you have the other category, which is I have no idea. And you have the category which VULKAN has not defined yet, but Volcano planned for, which I have even less idea what it is. So we put those at low priority because we don't know what it is, and it's probably a bad thing. So we sort devices by these device types based on our preferences. And we pick the device type that has the lowest index as defined by the mapping above. And among all the devices that have the same type, we don't care, we pick one. Actually, technically, the way this is defined, it will always pick the last one. But really, what we should do if we cared about multiple devices within a single type is if we cared about this, we would need to add more selection criteria, which we don't do right now. Again, it's a good idea to tell your user what you picked, because sometimes the guessing logic can be surprising. And if you find no VULKAN device at all, it's also a good idea to tell your user with a nice error message. There is one last thing with this function, which is we added this nasty quiet Boolean parameter. And what it does is it suppresses all the useful printouts which tell you which GPU we have been selecting. We don't want to do that in the final simulation, but we will definitely want to do that if we ever benchmark device creation, context creation. Otherwise, our context creation benchmark is going to spam stdr with thousands of logs saying, I pick device something, I pick device something, I pick device something. You don't want that. That's why it's there. Now that we know which device we want to use, we see again a VULKAN pattern that we have seen before, which is that we can query the properties of our device, but before we can use it, we must configure it by telling VULKAN which optional features we want to use. VULKAN handles this by having physical devices, which is the stuff you can query, versus devices, which is what happens after configuration. I don't quite like the physical device name because it may not be a physical piece of hardware, but you know they had to pick different names, right? And naming is hard, so forgiven. The interesting thing is that actually at this stage, we will not set up only a device. We will set up both a device and one or more things called queues. Here, VULKAN tries to innovate with respect to previous GPU APIs like OpenGL by exposing the fact that GPU hardware actually exposes multiple hardware channels for sending commands. You have these command processing units that can work in parallel. They have many names. I think on NVIDIA, it's a giga-thread engine. On AMD, it's an asynchronous command engine, something like that. Every hardware manufacturer has their name. It's horrible. And in VULKAN, we call them queues. The reason why you would want to use several submission interface is twofold. First of all, multi-threading. If your application has multiple GPU processing threads and you funnel all of this through a single submission interface, you create a bottleneck that doesn't actually exist in hardware. And the second reason is that GPUs often have specialized command processing units that are independent from the other ones and can operate in parallel. One particularly frequent special purpose unit in modern GPU is the DMA engine, which is the hardware unit that is able to transfer data from main memory to GPU memory and back. Your GPU is able to do memory transfer in parallel with compute work. If you had a single command submission interface, then the GPU would need to scan through the command list arbitrarily far to find commands that can operate in parallel with the other ones. Hardware manufacturers don't like this weird trick. So instead, what we do is we have a separate interface where we can submit our commands that can operate in parallel, much cleaner in hardware. And as long as you do the right thing in software, it works. One warning. VULKAN calls these queues because they operate in a mostly first in, first out fashion. But modern hardware is, as I mentioned in an earlier presentation, out of order, superscalar, whatever, pipelines. So your commands in the queue may actually execute concurrently. And if you are doing pure VULKAN, your code should account for this. You should not just have a compute shader execution that depends on the result of the previous one without some barrier in the middle to tell the hardware, please wait for the previous job to be finished before starting the next one. Otherwise, you will get wrong results. I will get back to this. All this to say, if you want to get the highest performance with VULKAN, you should be using several of these hardware queues. As using multiple GPUs, this is hard. So what we will do for our first program is to use only one. And if I find the time in another version of this course, I will explain how to use multiple ones. Unfortunately, I didn't manage to do it for this edition. And what do we do then? We take the device, physical device, remember, we have not configured it yet. We enumerate the available queue families, which are a bunch of hardware queues with similar properties. We look for the first family in the list that supports compute operation, because the VULKAN specification tells us that if you support compute, you also support data transfers. And we pick that. And hopefully there will be one. If you look at the exact VULKAN specification text, what it actually says is if you have a queue that supports graphics, then you have a queue that supports compute. I have yet to find a VULKAN device that does not support graphics rendering. So even if it's not spec guaranteed, I have hope that crashing when a device is like that is okay. Then I know how many queues I want. One, I know from which hardware queue family I want to allocate them, the one that supports compute, the first one. So I can set up my device creation info and get my device and the set of queues that I have ordered, which in this case is only a single queue. I know it's a single queue. I get it out, assuming there is a single queue, because the VULKAN API implementation is not lying to me and giving me 0 queues and I ask for 1. And then I get, in the end, a device initialized, ready to use, and a queue. And from now on, basically, we will use the queue when we want to submit commands to the GPU. And we will use the device for basically anything else, memory allocation, program compilation, this sort of stuff. VULKAN is about configurability, among other things. We could configure more stuff when we set up a device. It's written in the text. Read it if you care. We are not going to use it because for now we want to run on all the devices. The next concern we are going to take care of is pipeline caching. As you may know, even if you are using here a language that is compiled ahead of time, in this case Rust, but it could be C, C++, Fortran, same idea everywhere, your GPU code is not compiled ahead of time because it cannot be. If it were, you would need to have one build per hardware architecture with an incompatible instruction set in existence before your program is truly portable across hardware. That's too many builds, especially since GPU hardware takes no care in having compatible instruction set across different hardware generation. And supporting hardware from the future is hard. So instead what we do is we do what Java and C# do, and we use just-in-time compilation. We have some GPU program, and at runtime, we ask the GPU driver, please turn this GPU program into a binary that's appropriate for the hardware I'm targeting. But if you've ever been using Julia, Java, or C#, you know that there is a price to pay for this, which is latency. The first time you run your application, now you need to do some compilation work. And so for a while, your application will be twiddling its thumbs, waiting for the GPU program compilation to finish. That's not nice, which is why for many years, GPU drivers has been trying to make this process faster, and in many cases, make it disappear completely. Two techniques have been used. One, at the API level, was to stop using high-level programming languages as driver input. Instead, we now use something called an intermediate representation. Pierre mentioned it in his compilation course. You can think of it as a higher-level assembly, basically. And we send that to the GPU driver, and then it has less work to do to translate that into binary for the device. The second part used to be fully implemented at the driver level. And the driver tried to do some catching, where if it sees the same program multiple times, it tries to keep around the binary and give it back to you. Now, there are problems with this, because this is GPU. There are always problems. One problem is that GPU driver manufacturers are not good compiler authors. So the part of translating high-level programs to GPU binaries was an enormous source of bugs, and still is for people that use CUDA and such. This was also fixed by moving to intermediate representation. So you can see that the Kronos people can be clever when they want to. And the second thing is that because they are not compiler authors, they are also not very good at caching. And in particular, one thing that GPU drivers turn not to be very good at is cache invalidation, because that's a hard computing problem. You know, one of the two hard problems along with naming things and out of bounds. So the way they fixed this issue in VULKAN was the same as they fixed many other GPU driver issues in VULKAN, is by saying we don't want this to be the responsibility of the GPU driver, so we move it to the application developer. So now in VULKAN, you are responsible for maintaining your own cache. And the good thing about it is you can invalidate it when you want, when you think the hardware did something wrong, or you guessed through some heuristics. You know, invalidating it is fine. It will just cause a bit of compilation time. It's better than taking a binary that is wrong. And the second thing you do is, if you are Ubisoft, you can prepare pipeline caches for all hardware in common use, distribute all of them with your application, and then they don't get any latency even on the first startup because they have a build that already works for them. But this only works if you're Ubisoft. And basically, VULKAN only gives you the tool to keep a pipeline cache in memory. Saving it to disk and loading it back is your responsibility. I give you a small abstraction to do it. It's not very interesting. It's just saving stuff to disk and loading it back, so I will not describe it further. Next thing is memory allocation. I have bad news here. You thought that CPU memory allocators are bad. They have nothing against GPU memory allocators. It's the slowest memory allocators you will have ever used. You can benchmark them. It's horrible. And this means that GPU developers who need to suffer through all this broken infrastructure have learned to deal with this for a while. And what they essentially decide is we don't trust the driver allocator. We will just ask it for a big block of memory, maybe 256 megabytes, something big. And then we handle it on our own with a custom memory allocator inside of our application. Because VULKAN is VULKAN, we actually have not one kind of memory resources, but three. We have the stuff that you may be thinking about when you think about memory resources, stuff like buffers that you can write into, images, textures. Then we have descriptor sets, which I will get into in a future chapter. But basically, it's a way to group resources into packages so that you can bind all of them to your GPU program as once. And then we have command buffers, which are the stuff that we will eventually send to our queues in order to submit commands to the GPU. The later two use a different kind of allocators because GPU hardware is a mess, and they may be allocated from a different memory pool that you don't want to know about. So this is an opaque thing. But it's still a GPU driver allocator, so you still want to have your own application side allocator on top of it to avoid calling it too frequently. Volcano provides some. They are okay. I never had a bottleneck linked to them in my code. So I propose we just set them up in their default configuration, and for our purposes, we work fine. Finally, we put it all together. What are we going to need in the next chapters? We are going to need a device, which, as you may remember, is the initialized version of the physical device that you could query earlier, which you can use to do things like allocate memory, for example. When we set up a device, we also set up queues that we will later use to submit commands. For now, we will only set up a single one because this is easier. To avoid waiting for GPU compilation on every program startup, we set up a cache that will save it to disk and reload it every time we restart the application if the application has not changed. Because GPU driver allocators are terrible, we are going to set up our own. And finally, we still have one thing that we set up previously that we need to keep around, which is our logger. We are not done yet using VULKAN. We still want to get warning and error messages if something goes wrong. So if we manage to set up logging earlier, we want to keep it. Together, these form what I will call the context, which is basically the VULKAN setup that's generic enough that you can share it across many different applications, provided you're willing to, from time to time, add a feature or two to make something customizable, like maybe allow to have multiple queues, that sort of stuff. So at the end of this chapter, you have the part of VULKAN that you will only need to write once. And then we'll see the part that you need to write once per program. And there it looks like this. So we put together all our command line parameters, those that pertain to instance and the other ones. that let us select our device. We put everything together in a big struct that has all the stuff we are going to need later on, with a constructor that calls all the code we have been mentioning earlier. And this is a dirty trick to handle the fact that I need to save the pipeline cache to disk, but you don't need to care about it. So I give you an accessor that gives you a pipeline cache in memory, and you don't need to know that I'm saving it to disk another. I will stop here and let you work on it a little bit, maybe a quarter of an hour, and then I will conclude on this chapter because we are already close to the first half of the day. Yeah, typos. It should be Ninja. It shouldn't be Ninja because I didn't want to assume that people use it, but then I did. So yes, indeed, I need to change this. This is what happens when you write multiple versions of something and then you figure out that, make is fine, except on Windows where Windows is not fine, so make is not fine, and you need to use a Google product to work around it. That this means I need to fix other setup instructions as well, because now I need to tell you to install Ninja, so I will put this on my to-do list. And fix it during the next quarter of an hour. So, what do we have? David closing polls. Okay, and nothing else. Perfect. Are there questions in the room? Outside of the room? If not, I let you proceed. And meanwhile, I will fix my Ninja setup instructions because environment is a pain, but it's a pain we must all face alone.
jamais t'en détail de problème d'installation.
J'ai 10 minutes. On va voir si ça se fait en 10 minutes.
Vas-y, lequel tu veux. Les deux.
Ok.
J'ai un local à gauche, le permis que tu as vu tout à l'heure. Et en conteneur, il n'arrive pas à lire le fichier JSON que tu as mis sur la vidéo.
T'es sur quel genre de hardware?
En carrière.
Ouais. Et en local info, ça marche?
L'erreur que j'ai, c'est que local info, il n'y a que celui de Steam qui faut.
Ah ouais, mais non, ça c'est bon.
Et
Parce que du coup, c'est dans un snap et on ne sait pas si ça dit la vérité en local, quoi.
exactement. Je pense que les erreurs que j'ai sont liées à ça.
Ouais.
Et local info
Donc,
n'est
lui,
pas connu.
on va juste. Ton conteneur, tu l'as lancé avec quelle option aussi? Parce que c'est un autre truc qui est important en conteneur. Alors, ça, c'est pas. Ouais. Du coup, il s'appelle comment le conteneur?
J'ai copié celui que tu as mis pour le CPU, j'ai juste ajouté GPU all et M qui
Ok.
existe en local.
Il ne l'a pas monté ce petit con.
Ouais, c'est ça. C'est ça le plus bien.
Alors ça, ce que ça pourrait être comme problème, c'est que soit ta version de Docker, soit ta version de driver NVIDIA ou de je sais pas quoi que fait Docker quand tu fais GPU All est trop vieille et qu'il n'a pas encore pris l'habitude de monter le truc. Et dans ce cas-là, le hack dégueulasse à faire, bah, c'est de rajouter un -v qu'il monte toi-même à la main puisqu'il n'est pas fichu de le faire lui-même. Ouais. Enfin, on va hacker, c'est ce qu'on fait chaque fois qu'on fait du GPU. Je peux le fermer du coup?
Là, tu vas faire le conteneur.
Ouais.
Ouais,
Ok. Du coup, il n'est pas content. Tu peux le remettre dans la bonne fenêtre. Bah, si tu cliques sur la petite icône GitLab en haut à droite, tu vas la voir là. Mais voilà, il y a tout là-dedans. Il y a le source des exercices. Donc, du coup, si on fait ça, et que maintenant on dit que le truc il est con, il faut qu'on lui tienne la main parce que c'est ce qu'on fait tout le temps en GPU. Et que du coup, maintenant, bah, tu vas prendre ça en local, petit débile, et tu vas le monter dans le conteneur, comme ça. Et si maintenant, on applique ma demande, est-ce que ça marche? Ça a l'air un peu bizarre. Ça a l'air de faire des trucs très bizarres. Mais c'est pas du HTTPS et ce ne sera jamais du HTTPS. Okay. Du moment que l'environnement est correct, moi ça me va. Donc maintenant, on fait un VULKAN info. Est-ce que maintenant ça marche? Et donc du coup, bah, ça, c'est pas monté non plus. Donc va falloir. Comment c'est possible d'être aussi incompétent, bordel?
Et ça, c'est un problème d'installation locale.
Je pense qu'en fait, soit ton Docker est un peu vieux, soit le Docker il sous-traite un machin NVIDIA qui est un peu vieux. Il y a un des deux qui est un peu vieux, et c'est pour ça qu'il galère.
Je crois que le driver, je l'ai appelé le week-end dernier. Le Docker, je l'ai installé il y a 2 semaines.
Mais du coup, est-ce que c'est pas une arnaque comme quoi tu es Ubuntu 22 ou je sais pas quoi, et du coup le Docker est plus vieux? Ouais, donc c'est pas ça.
Normalement.
Bah, éternelle question d'environnement, pourquoi chez moi ça marche?
Ouais, mais c'est le problème.
Mais ça, ouais, bon, bah, en gros, tu vois un peu le fil de l'Ariane. De toute façon, si tu as envie de t'amuser, hein, faut que tu trouves la lib où est-ce qu'elle est, tu la montes aussi. Je sais pas si tu as le droit de monter des fichiers, parce que j'ai peur que la lib elle sorte dans un dossier où il y a d'autres fichiers que tu veux pas monter dans le conteneur. Donc,
bah, je pense qu'on peut, parce qu'on a créé la lib fichier JSON. Ah non, c'est le.
Non, c'est une variable d'environnement.
Ah,
Donc, je sais pas si tu as le droit de monter un fichier avec mon AV. J'ai jamais essayé. Faire le test, on va voir. Mais du coup, bah, tu fais un find pour trouver le libegl machin, tu lui mets, et puis on va bien voir s'il arrive à se démerder maintenant. Mais c'est très bizarre, parce que ouais, mon Docker, moi, il sait faire ça, quoi. Je sais pas pourquoi le tien, il n'y arrive pas. Pourquoi il est méchant avec toi? Ouais.
Est-ce qu'il y a un fichier où il y a tous les dependencies?
C'est pas un fichier, mais les recettes de CI sous forme de Dockerfile contiennent les instructions que j'utilise pour installer ça par-dessus un Ubuntu 22. Donc ça peut être un bon point de départ si c'est sur Ubuntu.
Si je fais un conteneur, il admet que mon GPU, c'est un CPU.
Il te montre que le CPU, ça veut dire qu'il n'a pas réussi à
Ouais.
monter le GPU en conteneur,
Ouais.
je pense.
Mais sur mon installation, j'arrive à le voir.
À mon avis, ce qui se passe, c'est qu'il y a un problème. Tu sais, je ne sais pas si tu sais comment ça marche, Docker sous Mac.
Non, pas exactement.
En fait, Docker, c'est une techno Linux. C'est basé sur l'idée que tu gardes un kernel Linux constant et que tu mets différents user space par-dessus. Et donc, du coup, pour marcher sous Mac, ce qu'ils font, c'est qu'ils créent une VM Linux.
Ouais.
Et dans cette VM Linux, après, ils exécutent des conteneurs. Et ce que je me demande, c'est est-ce qu'il n'y a pas une arnaque au moment de la création de la VM où en fait, il n'expose pas à la VM le GPU et c'est pour ça qu'il y a des problèmes. Ça, c'est un des trucs que j'anticipais et c'est pour ça que je dis aux gens, je préfère que vous fassiez des installs locales, même si c'est souvent plus difficile, pour éviter ce problème-là.
Mais du
Les instructions install locales, j'ai essayé d'en mettre pour tous les OS. Donc, il faut faire celle du CPU puis celle du GPU, du coup. C'est un peu chiant.
Locales, c'est l'installation.
Voilà. Et donc, ça dépend de celle du CPU. Donc, il faudra aussi que tu fasses celle-là.
Les deux.
Ouais, d'abord celle du CPU, puis celle de...
Là. Et je fais ça et.
Donc ça installe Homebrew, si tu l'as déjà, c'est pas la peine.
Déjà. Donc
Tu as le brew install les dépendances. Bon, tu vois l'idée, quoi, après.
Ok, on vérifie, on fait l'installation.
Ouais.
Ok. Et du coup, c'est system-wide que je fais, non?
Non, local, ça suffit.
Okay.
Alors, system-wide, c'est pour les gens qui ont des centrages PC et qui veulent le mettre pour tout le monde.
Ah, ok.
Mais du coup, comme Rostop n'a pas été prévu pour ça, c'est un peu dégueulasse, donc je ne recommande pas si tu peux faire ça.
Ok, merci.
Yeah. So I would like to, but I did that for the first version of the course. And every time I did a course update, I was so short on time that I didn't manage to port this particular chapter.
Okay.
So maybe next version of the course. Sorry.
Sounds good. I was just wondering.
Also, if I want to do this, I may need to start thinking about horrible things like how do we make X11 work inside of a container. And I expect that this is going to cause me great pain. Yeah. Yeah. Yeah, I use the first version of the course's source code every time I show this because, again, time budget. All right. As usual, sorry for rushing you. I have no time. That's my defining characteristic. So let me then tell you a bit about what happens after we have set up the common VULKAN setup. Remember, the central design goal of VULKAN was to give the middle finger to GPU manufacturers and tell them, okay, we've been putting up with your broken drivers long enough. You clearly don't know how to do software. We will make sure you have as little software to do as possible and take everything we can on the application side. Every time developers try to solve a human problem with a technical solution, it has consequences. Here's the consequence is that compiling a GPU program is going to be, let's say, a bit more difficult than it is in other GPU APIs. Let me introduce you to compute pipelines. First of all, as I mentioned, VULKAN gave up on the idea of making GPU driver authors write correct compilers. They tried to make it as easy for them as they can by starting from intermediate representation. And so they defined VULKAN in terms of this intermediate representation, which, as a reminder, is assembly-like. But as developers, we don't want to write assembly-like code. So what do? We need to pick one of the many languages that will transpile to this SPIR-V intermediate representation. And here I could have picked several options. I could have stuck with GLSL, the traditional Kronos programming language. I could have used one of the newer languages designed for GPU programming, like Slang. Or I could have gone for more experimental stuff, like the Rust GPU compiler, which can take Rust kernels and compile them to SPIR-V. I decided to stick with GLSL for this edition of the course, for a few reasons. First, the Chronos group, which maintain the VULKAN specification and the SPIR-V specification, also maintains the GLSL specification. This means that when a feature gets in SPIR-V, you get it in GLSL first, and you may get it in other languages later, someday maybe. So if you want bleeding edge VULKAN features, GLSL is your choice. If you look over the web for courses other than mine about VULKAN, I don't know what you would need, but you know, you will find only examples spelled out in terms of GLSL, because again, this is one of the traditional languages in graphics programming. Everyone uses it. That's another strong point for it. It's not that bad to learn. It's actually quite an easy language, in the same way as C is easy, you know, easy to learn, difficult to master. And it's purpose-built for GPU programming, which means that it handles stuff specific to GPU hardware that languages like C, C++, Rust have not been designed for. Like the fact that, for example, on GPUs, you have different kinds of pointers that point to different kinds of memory and are incompatible with each other. You cannot assign one to the other. GLSL being designed for this can handle this sort of mess. In other languages, it's harder. If you want to have some fun, you can look at the Horror Museum. That is the part of the CUDA documentation that explains everything they changed with respect to basic C and C++ to make it work. And as for Rust GPU specifically, I would like to say that it's ready, use it. It's still a bit young, not enough documentation. Uses an ancient nightly compiler release, which may cause problem with a newer code construct. Not ready for prime time yet, in my opinion. So GLSL it will be. Now we have two kinds of pipelines in VULKAN. We have graphics pipelines, which are about rendering triangles on the screen. And we have compute pipelines, which you can think of as CUDA and Chronos syntax. Obviously, for numerical computing, we want the latter. In GLSL, unlike in many other programming languages, and I think that's actually kind of a good thing, you must say early on, I use this language revision. It's not a compiler parameter. It's part of your program. And then you need to specify how your GPU program is going to interface with the CPU. And here you need to be careful, because this code on the GPU side will have matching code on the CPU side. And you need to keep them in sync. If they stop being in sync, your GPU program will try to interpret something the CPU gave it in a way which is not the one that the CPU expected, and you will get weird behavior. So be very careful about this part of your shaders. If you touch it, you need to touch the CPU side accordingly. Here what we are doing is we are declaring something called the shader storage block. That's a lot of syntax. Let's break it down. The first important part is the second keyword, because life is nice. It's the buffer keyword. What this tells you is the CPU code is going to bind to the GPU code a block of memory whose memory layout we control as a programmer. We can choose what's in it and how it's laid out. This memory block must have one name, let's say on the VULKAN API side, which, if we were doing graphics pipeline, would be used to attach different steps of the graphics pipeline with each other. Here in compute, basically, the driver, it's only going to be about error messages and stuff like that. But you know, the GLSL specification says we have to do it, so we will put a name, okay. Then we say what's in it. Here, it's a variable size array of floating point numbers, because we want to square a bunch of numbers. And finally, we give it a name on the GLSL side. This is optional. If you do it, then you can refer to this data in your GLSL code as data.data. If you don't do it, all interface variables will be at global scope, which I personally think is horrible. So I advise you to do it this way. For larger programs, it will make your code much clearer. Finally, we can look at the first part.
which is this layout clause. Remember, the ultimate purpose of this code construct in GLSL is to say we are going at some point to bind the memory resource from the CPU side. The CPU code needs to have a way to refer to this particular binding point. In VULKAN, this identifier is composed of two integers, a set number and a binding number. If some of you have done OpenGL before, you may know that in OpenGL it was only one number. So why do we have two in VULKAN now? Because it allows us to bind multiple resources in a single API call and thus reduce program overhead when you have multiple resources to bind. Then we need to specify something else, which is our work group size. This may be familiar if you've been listening during the SYCL course. If you've only been listening to the CUDA course because you have begun your training as an NVIDIA, unpaid NVIDIA employee, then in NVIDIA, in CUDA, we call that a thread block. The compiler, for optimization reasons, needs to know how large these blocks are going to be at the time where the GPU program is compiled. We can hard-code it, and we are actually forced to hard-code it. That's one stupid part of the GLSL specification. But we are later allowed to reconfigure it from the CPU side using a beautiful mechanism known as specialization constants. If you have been doing some C++, you may know about constexpr, which allows you to do things at compile time. Remember, on GPU, compile time is the application runtime, which means that you can set compile time parameters of your GPU program when your application is already running. And this is extremely powerful. Here, we will only be using that to control our thread block size so that the CPU and GPU code agree on it. Then finally, we have our program. As in OpenCL and CUDA, OpenGL and OpenCL, SYCL, CUDA, whatever, our program is like a parallel for loop, which operates on indices distributed on a three-dimensional grid. Here, we will only be using one dimension, the first dimension, because squaring numbers is a one-dimensional problem. We are going to query the position of what in GLSL is called a work item, and in CUDA it's called a thread. And we are going to check if it's in bounds with respect to our data set. Why do we need to do that? Because GPU hardware has made some sad life choices in an attempt to get more performance. And so it asks you to only use full work groups. You can't have a half a work group. So if your data size is not a multiple of your work group size, you need a trick. And that trick is to just mask out the GPU threads, work items that don't need to do work. And finally, we access our data from the data storage block at the index specified by our work item position. We multiply it by itself. That's querying. And altogether, it looks like this. Then we need to deal with SPIR-V, which is a bit of a pain. Volcano makes it easier by giving us a macro that will generate the SPIR-V for you and allow you to automatically check that your device can handle it if you use optional SPIR-V extensions. I advise that you put some constants on the CPU side on all these numbers you have declared on the GPU GLSL side so that you do not go insane later trying to figure out what this zero means in your code, because it could be several different zeros. Then we apply specialization constants to set our workgroup size. I show you a particularly cautious way to do it, which lets you catch some cases of CPU-GPU interface desynchronization, because again, if you don't catch it, the symptoms can be a little messy. You need to locate the entry points of your GPU program, because you could have multiple entry points if this were a graphics pipeline. You know, one for vertex shading, one for fragment shading, etc.
In compute, you will always have a single entry point, but sorry, the interface is consistent between graphics and compute. Then from this entry point, we set up a pipeline stage. If you use Intel GPUs, this is a point where you would say how wide you want your SIMD vectors to be, because Intel GPUs are magic and are able to pick SIMD units of different size at runtime however they like, which is great. Now, if only they had the performance to go with this. Finally, you need to specify something called the pipeline layout, which basically is the interface used to bind resources from the CPU side to the GPU side. It's a pain. Volcano automates it for you and saves the day. You can be careful if you're like me, a bit paranoid. And in the end, you can build your compute pipeline. And you have here a nice summary of all the steps. Yeah, VULKAN is basically about trading a kind of pain for a different kind of pain, sorry. After you do this, remember, we now have a program. We don't yet have memory to bind to this program. We need to fix that. And here we discover that GPUs are the seventh circle of hell, and they have many different kinds of memory. There is no single malloc. We have all the mallocs. Like this is a GPU of my laptop, and I have 2 different memory heaps from which I can locate, which altogether contain 7 different kinds of memory. And I can locate from all of this, because why not? And I explained in the chapter how these differ, but sufficient to say, to move data from the CPU side to the GPU side, you have many different options, and depending what you are doing, one or the other option will be better. Here, we are going to take the most general option, the option that works okay most of the time, even if sometimes other options will work better. And that's the option of having one CPU side buffer, where you put the initial data. Then you copy from this CPU buffer to the GPU on a buffer that's fast to access for the GPU. Then you do the GPU computation, and at the end, you download results back to the CPU. And this means that we need to allocate a CPU buffer and fill it with some contents. We are going to take random numbers between 0.5 and 2, because that's my favorite kind of random number. And we need to say that our buffer is usable as the source of a memory transfer. Because if you tell VULKAN all you know about the usage of something ahead of time, you can use it for optimization. And you need to say that, so this memory should ideally be on the CPU side, otherwise filling it is going to be very expensive. And it should be appropriate for sequential write, which means that basically you are disabling the CPU cache. And by doing that, you make this memory easier to access from the GPU at the expense of making any kind of access except for sequential writes extremely slow on the CPU side. You get this buffer, you fill it with random data. And then we set up a GPU buffer in a similar way, but now it has more usage flags because we need to be able to transfer memory from the CPU, data from the CPU to the GPU, run a GPU compute pipeline, and then get the data back on the CPU. Because I mentioned earlier, VULKAN has this ability to bind multiple resources at the same time to a GPU. There is a price to pay for that, which means that we need to create those groups of resources ahead of time. That's called a descriptor set. The API for it is a bit messy, but we can live with it. We've been doing system programming. We've seen the depths of the abyss. It's not something that's going to frighten us. Then we create a buffer on the CPU side. It can be used as a destination of memory transfer. It should be on the host because we are going to read it on the host. And this time, it should be suitable for random access, which means that, OK, we are going to enable back the CPU cache because for readout, we really want it. And too bad if it's a bit more expensive to access for the GPU as a result. That's it for memory resources. Then we need to execute stuff. And here you discover that VULKAN has tried to solve all the bottlenecks of GPU computing at the same time
and produce an extremely complex API as a result. In OpenGL days, you would send commands to the GPU one by one, which obviously became an API bottleneck for people who sent lots of commands. So we wanted to have a way to send batches of commands to the GPU at once. And at some point, even preparing the commands got so expensive that we wanted to do that on multiple CPU threads. The problem is we cannot do this in OpenGL because OpenGL was designed in the 1990s. And thus, basically, it's designed around the idea that there is a global state object that you manipulate through functions that don't take proper parameters. It's horrible. Don't use OpenGL. So now we want to have explicit state. We want to say, I am submitting command to this queue, which means we need to break all the APIs to account for this. While we are at it, we could expose the fact that hardware, again, has multiple command submission interfaces, and sometimes these are useful. And we also want, if we are Ubisoft, to have a way to let the GPU know that it's allowed to overlap the execution of consecutive commands because we are crazy people and we think we know what we are doing. And surely overlapping the execution of successive GPU commands is going to go fine, right? And then finally, before in OpenGL, when you wanted to wait for some work to be done on the GPU, you had one very, very big hammer, like think a Thor-size hammer to do this, which was GL finish, which says, GPU, please tell me when you're done with everything I said before. In real-world applications, usually you don't want something so coarse-grained. You want finer-grained synchronization, and so VULKAN introduced this. And so in the end, what it looks like is this. So we need now to set up some kind of object, which is called the command buffer. And if you are NVIDIA, you wake up after 5 years, discover that command buffers are a thing, call them CUDA graph, and become rich. And then you can submit commands to this to copy data from the CPU side to the GPU side, attach your GPU program so that you can later run it, attach data to your GPU program using the descriptor set we've built earlier, decide how many workgroups we are going to spawn using a great Rust standard library utility that I wish the C++ standard library adopted yesterday, which does integer division rounding up. I don't know why I need to code this over and over and over again in all programming languages. If someone in the room is in the C++ committee, please fix this. And then you can dispatch your workgroups. And this is an unsafe operation because Volcano is not able to check what the GPU code is doing. And finally, you can get back your outputs on the CPU side. This gives you a command buffer, which is like a recipe. It tells the GPU what it needs to do. So far, we have not actually asked the GPU to do the thing. And this is where our queue object is going to come in. Now we can take our command buffer, submit it to a queue. And then we are going to use a synchronization mechanism called a fence to have the GPU notify us when the command is done executing. And this is a granularity of individual command buffers. So now we have a fine-grained weighting, which is great. The API for Volcano that Volcano exposes for this is a bit weird. Basically, it has to be because they are trying to be memory safe. And VULKAN is anything but memory safe. So you need to trick a bit to get it to be. And finally, you get an executable that you can run, and it will square numbers. Sorry for going fast, but at least I'm only 5 minutes late. If you have any question that emerges about this, we can start taking them. So this is not a question, more of a comment. Someone says something is missing, but that person doesn't say what is missing. Okay, yeah, semicolon, perfect. This is why when you write courses, you really don't want to develop the source code and the course material independently. It's such a pain to keep in sync. Anyway. I will fix that one. Later, I think I may have more important questions to take care of.
More pause automatically closing. An announcement that at 1:30 we get a presentation from our satellite site at Senegal. If you're interested, please be there. And so I'm done with Discord. So again, do we have any last questions from either the room or the satellite sites or people connected from their computer? I take all the questions. If not, I would say it's time to have lunch. So see you back at 1:30 for the presentation from, sorry, I don't remember the name, Senegal, but yeah, but who is it called? CNA, right. See you at 1:30 for the presentation from CNA.
Hello, Adama.
Hello, Marie.
Hello. We're very happy you're here. Thank you for being there and being a satellite site of the Grey Scout School. I hope the experience until now is okay. Do you enjoy it in Senegal?
Yes, we enjoy it in Senegal. It's perfect here. So we have some participants. They are most online, and few of them are in our seat here, on our side.
Okay, great. Well, if you can share your slides, and we are here to enjoy your presentation.
Okay, no problem. I'll do it right now. Did you see my screen?
Yes, we can see them.
Okay. Should I go?
Let's go.
Okay. So thank you, everyone. Let me present. My name is Adam Okoli, and I'm actually the director of high performance computing here in Scenery. And I work in this presentation with some of my colleagues, which are Dr. Babacar Job, Sheikh Job, and Maudo Malik Mbaye. Those are my colleagues here in Scenery working on the direction of high performance computing. So here is the summary. So I will talk first about Scenery. I will present Scenery. I will talk about the missions of Scenery. I will present to the organizational chart of Scenery. I will talk about responsibilities of our direction, which is the high performance computing. I will present to our supercomputer, Tawe, which specifications and an aerial view of the supercomputer. And I will finish by the overall demand trends to show you how is oriented the demands in here in our side. So CNRS stands for Cyber Infrastructure Nationale pour l'enseignement supérieur, la recherche et l'innovation in French. And it's a general directorate under the Ministry of Higher Education, Research and Innovation of Senegal. And its function as a ministry technical arm supporting the development and implementation of national digital and scientific infrastructure. So it was established by decree in 2021 by the President Macky Sall, which created and set the organizational and operational rule of the national cyber infrastructure. So here are the missions. Here in Scenery, we are responsible to ensure the management of the supercomputer and the data center for higher education and research. We also are responsible to deploy and oversee the integrated system of governance for higher education and research. And we also have to participate in enhancing the value of research and innovation in both public and private domains. We also establish common infrastructure for academic and research purposes. We have to oversee the deployment and operation of the National Research and Education Network. And then we will ensure the effective operation and administration of the National Digital System for Higher Education, Research and Innovation. So we have to design and deliver digital services, offers for public and private enterprise here in Senegal. Here is a representation of the organizational chart of Scenery, which is composed of two brands with the administration council and the directorate general, the general directorate, which is composite of these directions. Maybe I will talk it in French. So, direction du calcul intensif, direction CGS, direction SNRS, direction data center, direction recherche et innovation. So, those are the, this is the presentation of our organizational chart. And here in this presentation, I will just focus on my direction, which is the direction of high performance computing, here in French, direction du calcul intensif. So the responsibilities of this direction is to provide training and guidance and assistance to researchers in computational environment, to provide user support to run jobs and optimize the HPC usage, to maintain the supercomputer by regularly managing its hardware, software network, and user resources to ensure it runs effectively, securely, and also reliably. And we also have to contribute to national and international HPC projects. So we have to ensure the management of the supercomputer dedicated to higher education and research, also with innovations. So here I will go to present our supercomputer, which name is Taoe. We acquired it in December 2019. When we acquired this HPC, it was ranked as the third most powerful machine in Africa. And the peak performance is 537.60 teraflops. The specification as follows. So we have 198 compute nodes with Intel Xeon Gold, which are the SYCL, Skylake. We have 36 compute nodes with Intel Night Landing processor. We also have 12 GPU nodes. Each one is composite of one Intel Xeon Gold processor and 4 NVIDIA V100 GPUs. So we have also one shared memory processor with a capacity of 6 terabytes of RAM. We also have a scratch of 1 petabyte of capacity. We also have 10 tera of home for users. And at the end, we use InfiniBand to really make the interconnection with more speeds. So here is an aerial view of the infrastructure, composite of 3 parts: the cooling system, the energy production, and the supercomputer. I want to mention that maybe it takes a little bit sometimes to be shown by users. I already go for user. Let me just stop this share and share again. Okay, it's okay now. Hope it's okay by your side. So here, I'll continue. So this is the aerial view of the infrastructure. I want to mention that it's an it's implemented outside. So we have containers and in which we have all the infrastructure. So for the last part, it takes time to be presented to people online. I don't know if I should continue with that. Mary?
Yes, it's perfect. We can see your slides, no problem.
Did you see the overall demand trend slide?
I'm sorry?
Did you see the overall demand trend slide?
Yes, yes, we saw it.
Okay, so this is the overall demand trends. So that we have more than 80% of access requests concerning projects in artificial intelligence, modeling, etc. And the frequently used words are data analysis and AI. Donc, what could illustrate the project and access? This is a word cloud to illustrate the project and access requests on Taoe. So thank you, everybody. This was a brief presentation of Scenery and talk about our supercomputer Tawwe. And we also have many projects on it. All projects are working, like they are still on the board, and we will try to present it maybe next time, inshallah. Here is our satellite seat with some users. Thank you.
Thank you very much. Thank you, Adama. Obviously, we are very happy to have you as a partner since last year. And
Yes.
we hope we continue our collaboration with you. Of course, if you have questions, as usual, you can ask Adama on Discord. And for the rest, let's meet at 2. Thank you very much.
Thank you.
Okay, so we are back for the last part of the Rust lecture on GPU, and then we'll move on to Julia. So last chance for you to understand all of this black wizardry.
I stared at the abyss, and the abyss stared back. That's the spirit of GPU programming.
So Adrien, it's yours.
Thank you for the introduction. So, you may not know, but actually in the teacher team, who also calls itself the Muppet Show, we have a saying that everyone has a very bad faith. And one of the essence of bad faith in programming is when you say, okay, my technology may look horrible, but you see when I put it on a more complicated problem, it scales better than the other one. This is exactly what I'm going to do here by showing you how VULKAN, which we have seen on a simple number squaring example, would scale to a more complex example, the Gray-Scott reaction simulation. Let me mute this for now, because it's always going to be annoying. So, earlier, I mentioned that when we say that VULKAN or OpenCL or whatever is verbose, it's also a bit of bad faith, right? We should differentiate two different things in those APIs. The setup that you can easily share between multiple applications versus the setup that you need to do for any new computation. And I claimed at the time that the instance and the context part of my VULKAN setup is relatively generic and will not need that many changes to handle other computations. This is where I show that this claim has at least some substance. By showing that the only thing we need to change to this entire code base to support our fantastic console progress bar, the only thing we need to change in this whole setup is to add the ability to support our textual progress bar. Because you see, we all love nice text user interface. They look beautiful, they make us look smart, but they come at a terrible cost that any programmer who uses them knows, which is that as soon as you start using them, you break the most important functionality of all programming language, which is the ability to emit text on stdout and stdr undisturbed. The indicative developers who handle these nice progress bar for us on the Rust side thought about it, or their users complain about it. I don't know the story. And so they provide a nice utility that we can use, where we take a progress bar, we call the suspend method, we provide a callback, and we say, okay, I want this callback to execute as if there were no progress bar, and then magic happens, and the rendering is interrupted, text goes nicely below the previous progress bar, and then the progress bar resumes, and the rendering is perfect. And what we need here is to integrate that into our VULKAN logging code on any other textual diagnostic we may want to insert in our application, so that whenever we feel like printing something to stdout and stdr, we call this utility. I show how that's done. I have two versions of this exercise, one for Rust beginners, ooh, I need to fix this, and one for people with more experience in Rust. The idea is in one case, I give a pretty strong hint. If you think you know the language already, you may want to try the other version, which has less hints. And then I move to the first meaty part, which in the interest of time, I will have to cover orally right now as well. And that's how our compute pipeline infrastructure is going to change when we move to the Gray-Scott reaction. Here, we will not attempt to deduplicate code between the number squaring computation and the Gray-Scott reaction computation, because this is the point where we start using the language genericity features too much, and then people who are not familiar with genericity get lost. So instead, we will accept some degree of code duplication
in the interest of accessibility. So we create a pipeline module, register it, and we get started again with GLSL, our friend, our only friend. As usual, we need to say which GLSL version we are using. But now our data interface is going to look a little bit different. Because remember, in the gray Scott reaction, we now have 2 inputs and 2 outputs. The inputs are the former version of the concentration of the U and V chemical species. And the output is going to be the version of the concentrations after the next simulation step. We can do this in GLSL. Because we have multiple inputs, we should be nice to our compiler. Since it's not a Rust compiler, it expects us to be nice by saying that our inputs and outputs are not going to alias one another, which means that lots of interesting optimizations become possible at the hardware level, at the compiler level as well. And we are also going to use GLSL feature, which should not improve performance for any self-respecting compiler, but which will make our code a little bit easier to maintain. And this feature is read-only and write-only. So in most programming languages, you have a base case, which is for Rust read-only, for most functional programming languages as well. And for most imperative programming languages, it's being readable and writable. And in either case, when you want to go away from the default case, you need to add a keyword. GLSL, at least for buffer inputs, tries to be symmetrical. So if you want to only access data for reading, it's read-only. If you want to only access it for writing, it's write-only. So far, so good. The last thing we are going to need is we are going to need 2 inputs and 2 outputs. And now you may be wondering why I am not able to put 2 different array members inside of my buffer. You know, why I need to have 2 storage blocks, each containing a member called data. And the problem here is that GLSL inherits a limitation from C because, let's be honest, this design is mainly copied over C, which is that in a data structure, you are only allowed to have 1 member of variable size, and that member must be the last member. So because of this, unless we are ready to store both the U and V species in the same buffer, which I would not recommend because it makes debugging harder in case you access this buffer out of bounds. It's better to have 2 different buffers, and as we will see, because we have descriptor sets, it will not be expensive anyway. I personally, as I mentioned, don't like to have hard-coded zeros and ones flying around in my code, which is why I will also be defining a pair of constants that let me remind myself that when I'm accessing the first buffer, it's the U concentration, and the second, it's the V concentration. After the memory inputs and outputs, the next thing we want to manage as the CPU-GPU interface are specialization constants. As I mentioned, these can serve 2 different purposes. One, software quality purpose, and one, performance optimization purpose. From a software quality perspective, specialization constants allow us to have less duplicated logic between the CPU and the GPU parts. In particular, we do not need to duplicate our constants because we can just have the constant defined on the CPU side and then set it on the GPU side using the specialization constant mechanism. From an optimization perspective, specialization constants allow you to tell the GPU compiler about information which is only available at the time where the application is started. As we are going to see for gray Scott reaction, one example of this is the reaction parameters. We can tell early on, before the GPU code is compiled, by the way, my reaction rate is this, and my etc. And then
it will be able, the compiler, to optimize our code based on knowledge of certain spatial values. Like, for example, if the time step is 1, as is the case in all of our Grayscale implementations, then the compiler will see that we are multiplying by 1 and helpfully remove the multiplication. So here I got a bit wild with specialization constant because they are so great and I put a bunch of them. So as before, we have our workgroup size. This time it's 2-dimensional because our problem is 2-dimensional and intuitively it makes more sense. If time permits, we'll discuss how this affects performance. It's still configurable from the host side because specialization constants are unfortunately limited to scalars. This means I need to have 2 specialization constants, one for the horizontal dimension, one for the vertical dimension. One thing which the GLSL buffer mechanism does not tell my GPU code is how wide our images are. We know how many elements they contain, but we don't know how these elements are split into rows. So we need to somehow send in those information to the GPU, and specialization constants are another way to do that. We have the reaction parameter. The stencil, so this, since we mostly agree among teachers to use the stencil at last, the same stencil at last, I could have not made this configurable, but it just felt better, to be able to switch between the stencil that is most accurate overall and the one which has the best rotational invariance. I will let my colleague on the back remember the names of each, because I don't. Unfortunately, again, because specialization constants are scalar, it's a bit of a mess. I need to define one specialization constant per element of my stencil. This is fine for interfacing purpose, in the dog sitting in the fire way of this is fine. But for my GLSL code, I don't want to see this. So the first thing I will do is to turn this into a 3x3 matrix, which is much easier to use. And then I have the diffusion rate, which tells you, when you have more spaces of U and V in one place, how quickly does it diffuse in space. And I play the same trick of turning it into a 2-dimensional vector. We have vector types in GLSL. Let's use them. One thing we should decide before writing shader code is what our data layout is going to be. During the CPU course, I mentioned that we have 2 ways to handle stencil computations at the edge of the simulation domain. One way is to adjust the size of our stencil so that, when we reach the edge, we shrink it, and then we don't access out-of-bounds elements. The other way is to add a bunch of zeros around our simulation domain. In the previous course, I show you the first strategy, at least until I introduce the crazy Cindy layout from Pierre. So this time, I'm going to show you the other strategy by adding a bunch of zeros, and this way we can see a bit the trade-offs involved in each case. So to visualize, the idea is that what I want to be able to do is to compute each cell of my concentration table by doing a weighted mean of the neighboring concentration value. And at initialization time, I have set up a bunch of zeros that I will not change anymore. And this allows me to have a regular stencil logic that is the same everywhere. So simpler code, more complicated data. As I mentioned earlier, stencil, pick your poison. While I say simpler code, we do pay something in terms of code simplicity, which is that now anytime we manipulate a 2D position in space, we need to remember to add 1 in the right places. And whenever we manipulate a size, we need to remember to add 2 because we have padding elements on both sides. Because this is a bit annoying, I prepare a bunch of utility constants and functions, which will later allow me to have a nicer, higher level logic in my shaders. Such as, for example, the ability to read U and V at a certain position or write U and V to a certain position. And then I move on. There is something new that I did also in this version of the Grace code computation. If you remember my numbers query program, at the time I said I would like to initialize data from CPU data because this is the most general way to do things. There are some cases where you will have to do this. This is not one such case. In our Grace code simulation, the initial data pattern is very simple and is totally within the realms of what a GPU program can easily generate. If we generate it on the GPU, we save ourselves from the trouble of handling the CPU to GPU data transfers and expect overall better performance. Our logic is going to be that we have one GPU work item per cell of the concentration table, including the outer 0 elements. And we are going to spawn work groups that may not evenly divide the size of the image, which means we are going to need to be careful on the edges. Overall, it looks like this. I bring back the saturating sub utility from us because it's cool. And I start, as before, by asking GLSL where I ended up on the simulation domain. So this part is the same as before. I use one GPU work item per output data point. After this, I check if I'm out of bounds, if I'm outside of the target image. If I am, this particular GPU work item will not be doing any work. It will exit early. Then I check if I am on the zeroed edge. And here I use some fancy GLSL Boolean vector logic, which I also did earlier, by the way, which makes this a bit less ugly than it would be in a language that doesn't have vectors at all. But frankly, I still wish we had an inside rectangle function in GLSL. If anyone here is in the Chronos committee, pass the word. Finally, if I am not out of bounds and I am not a 0, then I am a regular data point. And here we find the same logic we had on the CPU side. Couple things worth noting. I cannot share this version directive between multiple GLSL programs. I don't know why, if it's a GLSL bug or a bug in the compiler I use to compile GLSL into SPIR-V. Need to spend a bit more time looking into this. That's not a big deal though, because the amount of duplicated code remains tiny. I can still share my interface declaration and my constants and so on, and that's the most important part. I would really not want to duplicate this code if I can avoid. Then I write the main simulation task. And here, I want to have you think about something, which is that for simulation, the mapping between GPU work items and data is not as obvious as it was for initialization. I could do this in two different ways. One way is to have one GPU work item per output data points. That's kind of the logic I had in the CPU code. And then for each of these output data points, I will compute the stencil, looking neighboring elements, and so on. The problem with this is that I am going to read the same element multiple times because I'm looking at neighbors. And unless the hardware saves me from myself, this is going to be costly in terms of memory access performance. So I could do it another way by having one GPU work item per input data points. Now, each GPU work item is in charge of loading the corresponding inputs. And then these work items need to communicate somehow, the technical term is synchronize, to compute the stencils. Generally speaking, GPUs are better at handling ill-behaved memory accesses than they are at handling lots of synchronization. So my experience as a GPU programmer tells me that most likely the first solution is going to be most performant, especially after I implement an optimization that I have not written in this course yet, unfortunately. But I don't know. So I leave this around as something I would like to get back to later. Assuming I use the strategy of having one work item per output data point, if I use the same schematics as before, it looks like this. So the purple squares represent my GPU work groups. They all have the same size. I need to spawn enough of them to cover all the data points I need to compute. And this will compute a bit too many work items, but yeah, I cannot work around that. I will associate each GPU work item with one data point, one output data point, which means one part of the central region of my data. And this means, I should not start at coordinate 0, 0. I should start at coordinate 1, 1, because that's the first active cell in my table. So I will need some kind of shifting, as I mentioned earlier. And after that, it becomes the same. Each of my GPU work items will be like the red square in this schematic. It will be computing one value at a particular location by loading the input value at the same location and the surrounding value represented by the blue square. Overall, it looks like this. So I start by asking, as usual, GLSL, where am I? GLSL tells me where I am in the grid of work items. That's not quite what I want. I would like to know where I am in my central region, so I add an offset to correct this. Then I check if I am out of bounds with respect to my central data region again. The work items that are indeed out of bounds will need to be discarded. They cannot do any useful work. I load the central value. And then I do a stencil loop where I start from the top left corner, prepare my weights. This will be computed at compile time due to the magic of specialization constants and inlining. And I prepare a place to integrate my Laplacian term. I will also need, for a reason that will later become apparent, to compute the sum of the Laplacian weights. Then I iterate over the 2D stencil. First in vertical coordinate, then in horizontal coordinate, because that's how memory is laid out on GPU. And I read the value at my current position. So starting from the top left corner, I add the offset associated with my 2D loop. I get the corresponding value. From this, I also get the weight that corresponds to my particular stencil location. And I add to my sum of weights the current weight times the value that I'm looking at. So Laplacian as usual. If you remember some previous versions of this computation, you may remember that here I was not just looking at the stencil value. I was looking at the stencil value minus the central value. I don't need to do this. I will end up subtracting my central value over and over again with different weights. It's more effective to just compute the sum of weights and subtract it once. And because floating point is a pain, it's very likely to be more efficient even after compiler optimizations. The rest is quite similar to what you've seen before. I will not comment it further. On the CPU side, I'm going to use Volcano shaders again. Here I'm using a feature which allows me to load two different shaders with one call to the macro. If I needed to set common parameters, like setting an include path and so on, it would allow me to deduplicate these parameters. Here it's just for the sake of concision. I did not really need this. As usual, I prefer to have human readable names for all the magic numbers in my GLSL. It will not prevent them from getting out of sync, but it will make my CPU code much easier to read and adapt later on. And then I can move on with specialization. So remember, before we need to add a command line parameter to set the one-dimensional workgroup size. In VS Code, we are going to need one for the horizontal side, one for the vertical side, because this is a 2D workgroup. I will need to add these options to the main command line option struct of my simulation. And once I have done that, I can set up all my specialization constant. Here, I did it in a way that is less paranoid by the previous one, because the previous one, had like one specialization constant. This one has 17. It would get a bit tedious after a while. Then I will basically copy and paste my setup compute stage function from the last time. It's the same, We need to get an entry point. It's always going to be a single one because we are doing compute pipelines which only have one entry point. And then we need to configure it, and I'm not touching the configuration here because basically it will only benefit Intel GPUs and only if the automatic SIMD width selection logic gets something wrong, which is not that often. There is one thing, however, which I will want to do differently from before, and that's the pipeline layout setup. Earlier, what I did was I said pipeline layout setup is a lot of pain, repeating a lot of stuff that I have already said in my GLSL code. It's good to let Volcano infer it from my GLSL so that I do not need to repeat the same logic on the CPU side. Here, if I do this carelessly, what this means is that each of my compute pipelines, the one for initialization and the one for simulation, will have a different pipeline layout, which means that I will need to create different versions of my resource descriptor set for each pipeline. That does not sound like something I would like to do, especially on a wider scale with many more GPU compute pipelines. So what I will be trying to do here is to set up a common pipeline layout, which is shared between my two GPU programs. And thankfully, I can do that without giving up on the convenience of Volcano, because the pipeline descriptor set layout create info, mouthful, that I'm using accepts an array of pipeline stages, not just one. Someone thought about this. That's great. And then, I can check my layout. If it sounds right, single descriptor set, two bindings, one input binding, just, being paranoid as usual, because I don't like the kind of bugs you get when the CPU and GPU code get out of sync. And in the end, I build my pipeline layout and I call it a day. Do we have questions about this? If not, then what I'm going to do is to let you work on this as you see fit for half an hour. As I mentioned, in my opinion, in this sort of course, quality is more important than quantity. If you think you need to spend more time on the previous chapters to understand them better, please do so. It's okay, the material is designed such that you can get back to it later. And you will learn more if you fully understand the previous chapter than if you try to get everything the first time. I see I have no other comments on Discord. So if there are no other questions, I will let you work a bit.
Is there a non-Christian way of saying Messi? Do you have like another word for it? Because in Germany you say Gesundheit, and in Swedish I wish you health. Because whenever I say bless you, I feel like I'm
the same problem.
Yeah.
In English, I only ever say Gesundheit or blushing.
Okay.
That's actually the main reason that I use Gesundheit in English is that like I felt like it's
Yeah.
yeah.
Especially towards non-native English speakers. I feel weird saying blessing. I feel like they might not know it and think like I'm a language.
Is there what do they say in French?
I think nothing.
Interesting. Okay.
Me too. Anticipate. Wait. I think I'm gonna do it.
Could I for your brain can I'm gonna have to wrap my head around this. So the purple square is gonna be what is on the G2 that's computed, right?
Yeah, it's like CUDA blocks.
Okay. This is the square that you want to start with so that you load this once, right?
So to compute the value at this position, I'm going to need the input value at this position and the input values at all the blue positions.
Okay. And so this is the idea is that you want to load from the next square down, so you only read it once, and you don't have to read it multiple times.
And there's a way to do it, but I probably won't have the time to show it.
Okay. And then the padding, the zeroing is just so that you don't have stencil problems at the
Yeah,
borders.
you get regular logic, same everywhere.
And then what's the red again?
It's the whole region we are computing.
Oh, okay. And then,
We are not touching the zeros. The zeros will stay zeros forever. But we are going to update the central region of the dataset.
got it. Okay. And then the last thing is and this is the stencil itself.
Yeah.
Okay.
Yeah, it's a bit loaded because I don't know how to do it with less colors.
Yeah, no, that makes sense. Like you have a lot of information on that. Okay. Yeah, that makes sense. Okay, thank you. Is it when you wrote this? What did you use to write your GLSL code?
My text editor.
Yeah.
I use Sublime Text, but I think Visual Studio Code will be just as fine.
Okay.
There is an extension, I believe I put it somewhere in the environment setup, that you can use to get syntax highlighting for GLSL, which is really nice.
Okay. Let's have a look up then.
I think it's slevesk.shader or something like that.
It's a VS Code extension, you said?
Yeah.
I just tried to Google, but I got the wrong one.
I think it's shader or something like that. Yeah, it looks like it.
Okay, we get rid of the other one.
Well, I mean, they may be useful, but for syntax highlighting, that's not very, this one is good.
Yeah, I need to. I'm like slowly wrapping my head around it. So we get rid of this one. Okay.
Yeah. As I mentioned, it's one of those things where I'm really not sure if I made the right choice and will keep making the right one. It's a big trade-off which language you pick for the GPU side code. There are many sides to it.
Yeah, I mean, I think for me, I know so little about this that I need to start with one and then, to take my time with that one. Okay. Okay. Yeah, thank you. I would say that this is the best way to do remote, which is to report it to multiple and not to CPA.
What?
You say this is one of the best ways to do.
Depends what you call best. In my opinion,
Balanced performance versus
heterogeneity of
You
architecture.
do sacrifice quite a bit of ergonomics to get there. But my experience with VULKAN is it being a smoother ride than any other GPU portability API I've tried. You know, I spend more time fighting with VULKAN and less time fighting with the GPU driver and portability layer. So pick your poison, I guess. Yeah, VULKAN is nice. I don't have many bad things to say to it, except for one thing which they are aware is a bit broken and they are going to fix, which is the whole GPU future concept that I show at the end of the previous chapter.
Is there like a specific implementation of a future that's specific?
Yeah,
to
they
GPU?
did the whole future implementation and it's
They redo
not
the
quite
whole thing,
right.
they did? Okay.
Yeah, it's not so nice. They can do
What's
it better.
different about it? Or I should look that up.
Yeah, I'm not even sure if they shouldn't tap into async support if they were to do this identically. But async, as we know it, did not exist when Volcano was developed.
Oh, shit.
But what the directions they are going nowadays is a bit different. They want to have more of a task graph architecture like StarPU, if you're familiar with that.
Mm-hmm. Okay, and yeah, and that's also because the GPU itself, it runs asynchronously, basically.
Yeah.
So they modeled the.
Yeah, basically you want GPU APIs to be asynchronous because you know your CPU should not be waiting for the GPU when it doesn't need to.
So right now, the way they model the execution is through futures.
Yeah.
Okay.
Well, at some point, you know, you need to wait. You are done sending all the work you had to send. But the idea is to wait as late as possible. Yeah.
So they're thinking of trying to update it so that it's compatible with the async.
No,
ecosystem?
that's not the direction they're currently going for. They want to move to a more task graph design.
More like the promises and not.
Yeah, many languages these days have done the similar idea.
It's also basically in simple with the.
Yeah, that's what they are trying to do with the buffers and accessors. It's not a bad model for HPC. I mean, you can do nice things with it. Oh, I saw the name before and I only know the name. Please enlighten me.
Framework rules are how it's called. Just for automatic like dependencies.
Mm.
It can be
Yeah.
Python or Python.
Yeah, task graphs are one of those ideas that keep popping up, and I hope someday find their rightful place. If you ask the person on the back, he may have less positive ideas about it, but task graphs.
It seems less opinionated.
Oh, okay, more supportive than I thought for HPC programming.
I mean, yeah, may have that pre-existing kernel. I mean, I did a lot of reservoir simulation. You do a lot of LU decomposition, and then you have the LU staff, but you don't write them anyway because the LU kernel is specified already.
Yeah.
And you just have, I do this, and then I do this, and then I use that. I never felt the need to have something more than that. I'm all ears to have an actual use case where if you don't have that, it's bad or whatever. A lot of HPC workflow are just, I'm doing some pre-computation with a very specific operation on a bunch of data, then I do something, and then I do some post-processing, and you have to do it this way anyway, you don't have, thing. Now, the fact that you want to say, I have this pipeline with the actual. Then I have a distributed system and I want to replicate the pipeline, but that's a different kind of
Yeah, replicate the distributed system.
I mean, you have algorithmic skeleton for that, you have a bunch of abstractions that do that, but unless you are writing a very specific kernel for a very specific class in which you know that if you are on core or whatnot, can actually take the sub parts of it and, you know, like do something clever. Or you have some kind of massive workflow, but the workflow is distributed over a massively distributed system. But I may be wrong.
Yeah, I also thought that like most of the things we mentioned here are not so dependent.
Yeah. You have, it's more or less complex massive data paradigm where the core, you know, operation is very, you know, non-trivial. More than, you know.
I was just thinking about comps.
Yeah.
Yeah, but of course,
like a comp? That's the question.
COPS.
Ah, yeah, like a comp.
Yeah. Here's asking how it spells.
Yeah, not a P.
It's here,
But they were showing some like very complicated stuff. Like you take them and you visualize it in your browser. They were using it for even detecting some dependencies you're not even aware of.
so you basically it builds like cat scrap for you.
Yeah, it doesn't that for you. And then also like besides which stuff we're not so much into programming.
C'est la partie pratique, il faut quand même qu'à un moment, ils s'expliquent un peu des trucs, quoi.
Maybe
Bon,
other people.
moi, je peux leur expliquer des trucs aussi, mais s'ils n'ont pas envie.
Yeah.
L'entraide, c'est bien aussi.
Does this look like a cube? Yeah. Oh, it's a lifesaver actually. Every time I travel, I always want a second screen so badly.
No, right. I'm not. It's not citing my number.
PSP? Oh, okay. Yeah, so I guess this is more like, I guess it tries to take the tasking and move it up to like a, yeah, exactly, for like basically on a node layer. Very interesting. Huh.
You would just like define some functions as tasks. And then it can tell you, okay.
Yeah, why would you not? I would always think that if you want to like understand something like this, you would have like someone who cares to do like a, what is it called? Like a TLA plus, you know, mathematics. Yeah, yeah, basically you try to like a formal specification. I just figured someone would come in and try to describe it, like for distributed systems, and try to mathematically prove it ahead of time.
Maybe, yeah. But I think this is.
Yeah, I've only used it a handful of times, but like, you know, I often see people use like.
Oh my God, I'm not gonna need.
I just figured if it gets like crazy enough, you would, you know, use something like this to like basically try to show exactly how it works before you, especially for a distributed system.
Yeah, it was a very big.
Well, I only say that because when you mention this, it reminds me of like a similar like.
But I think this is more of a also just a sandwich for not much in parallel programming to business project.
You say this is.
For certificates, they
Yeah, exactly. Well, you are best friends with the cluster administrator, right? Yeah. You just make sure that you buy a beer for them and.
not sure they are that easy.
Or you find the use after free bug in some little utility that they don't know about if you try to get root access.
said like I had a disagreement with some of the people who installed software. The guy there said, I only install software for supported by the company. Otherwise I don't touch it. And he wants to try this software from this researcher and this software.
Yeah.
Like, no, I don't know.
The struggle is real. I know. Oh, I just went to a conference and I just saw this new thing with this person made. I'd like to try it out. Heck no. Yeah. Absolutely not. That's funny, yeah. Yeah, where did you hear about this? Were you at a HPC conference, I guess? Or?
Oh, I was studying at the UPC.
Oh, okay.
Just is partly owned by
Okay.
like
Mhm.
they get all of these seminars about
Interesting, okay. Very, very interesting. Yeah, I never heard of it.
a lot of tools in research plus
Yeah, exactly. Yeah, your flavor. Interesting.
Oui, dans les refactors que j'ai pour Edition N+1, il y a coupé mes lignes de bash. Elles sont un peu longues des fois. Je crois que c'est toi qui avais un pilote NVIDIA qui n'avait pas de VULKAN. Est-ce que tu as réussi à résoudre ça? Pour l'instant, travaux de voir. Ok. Si à un moment tu t'énerves un peu dessus, tu trouves, comme là, je vais bien des infos parce que derrière, ça va dans la nouvelle version des instructions. Je pense que tu peux revoir aussi. Merci. Ok. C'est marrant qu'il ne l'ait pas directement. Normalement, il y a une option qu'on passe container pour que ça marche. C'est peut-être pour ça que le problème. Ok, donc il râle un peu. Alors en fait, le problème qu'il a, c'est que mon image de conteneur est en Ubuntu 22. Et en fait, si ton système hôte il est plus récent, il voit des extensions VULKAN qui viennent du futur, des résolutions meilleures et ça te perturbe. Mais du coup, une extension, je ne sais pas trop ce que c'est, ça me perturbe, et après il s'affolait, il fait des gros messages bizarres. Donc c'est pas méchant, parce que je me sers de plus de ces extensions, donc ça va pas poser de problème. Ça pourrait, ouais. Bah, disons que le problème, c'est que voilà, il te dit en fait c'est une erreur, mais non fatale, parce qu'il a d'autres devices VULKAN à disposition. suis pas d'accord avec la classification, je suis d'accord avec toi si ça devrait être une erreur, pas un warning, mais je vais pas leur faire un patch pour ça. J'ai pas le temps, j'ai un cours à donner. Ça va être mieux. Essentiellement, il y aura un petit peu de choses qui vont se passer dans Benches aussi. Mais... Ouais. Bah, l'idée, ouais, c'est qu'en fait, comme c'est beaucoup trop de code pour que vous l'écriviez en live pendant une demi-journée, en fait, la façon dont j'ai expliqué le truc, c'est je vous explique, je vous donne des bouts de code, en vous expliquant comment il marche. Et bon, du coup, les exos ne sont pas très inspirés, c'est un peu du copier-coller, mais j'essaye de mettre de temps en temps des petites variantes. Et du coup, essayer de tourner un petit peu autour et voir ce que ça donne quand ça s'y prête.
C'est cool que toi, tu n'as pas gagné du temps.
En une journée, j'ai plus de temps.
Donc là, vous faites ça directement.
Donc, alors lui, je l'ai mis en privé parce que j'avais pas envie d'exposer le côté persistent qui va sur disque dur et tout. Donc à la place, ce que j'ai fait, c'est que j'ai mis une méthode là, qui permet de récupérer directement l'objet VULKAN dont tu as besoin pour 90% du boulot. C'est cette méthode dont tu auras besoin pour récupérer ton pipeline cache.
Can I see something, John?
Yeah, kind of just built a, dependency chain.
That's a good remark I just heard. So if you are using containers and you see gigantic warning messages from the validation layers, let me explain where it's coming from. The container images are built on Ubuntu 22, which is not so new these days. There are newer versions of Ubuntu available. And the validation layers that are in it are state-of-the-art with respect to VULKAN versions that existed at that time. Now you are mounting your GPU from the host. And the host has potentially, depending on your system, a more recent VULKAN driver, which has newer VULKAN edition support with newer extensions. The validation layer from Ubuntu 22 sees the new VULKAN extension. It cannot make sense of them because they are from the future, so it complains. But fortunately, the complaints are harmless. It will not do any bad thing because we are not using these extensions. It's just one of the nice sides of using containers.
Kind of like a pointer. When you pass this,
yes,
you're passing the actual object. Like, yeah.
So then the
Est-ce que je peux bouger ça? Moi, c'est un petit réfactoire, ouais, pour montrer un peu comment ça marche.
Mais au final, that would be another syntax.
Well, like, and where this is called, because this is just like memory allocated on a struct. This is a struct. So you could, so actually you use this a lot when you have like a, you have something called like an atomic.
Alors c'est à quel endroit et qu'est-ce qu'il
atomic reference counter. Well, it's used to pass around a reference count to something, but that's like you can pass
qu'est-ce que c'est
between
qu'Argoron
threads, right? So you're cloning the reference count, like you're passing the memory that is this object that's called an arc, but like it's a reference inside of it. So like when you have like when you pass some type of object here that has no reference to it, you're basically just saying like
simulate, par exemple, ou square sera mis à ce stade.
And then you have ownership of that entire thing because
mais je suis surpris que ça marche intéressant. J'apprends des trucs tous les jours.
you're saying, I'm getting in a reference to an item, and then if you use like a
Alors
move,
Cargo, il est
basically say,
intelligent,
I
il s'en
wanna
fiche d'où
make
tu
this,
es, il te
and I
laisse faire les
wanna
mêmes commandes de
like
partout.
push it inside as another certain thing. And then if you
Si
try
tu
to
fais le
implement it, there's an issue because now you
il sert à dire, je veux exécuter la cible binaire, donc en fait l'exécutable qui s'appelle simulate, qui correspond à ce fichier-là. Instance n'est pas un exécutable, c'est un morceau de la bibliothèque qui est commune à tous ces exécutables.
Yeah, there's different use cases.
Alors,
as well,
en fait,
but
tu
yeah,
peux pas
you-
exécuter une bibliothèque.
I think one of the
Ça,
main,
c'est pas
one
légal.
of the other reasons why you want to use a reference is you don't want to
Une
reallocate
bibliothèque, ça
memory.
n'a pas de point d'entrée, ça n'a pas de main.
You know, you say,
Donc,
give me
tu
the
peux pas faire
reference
de
to
cargo
this,
run
and
sur une
instead I
bibliothèque.
just, yeah.
Je pense que c'est pour ça, ouais. Cargo run, moins bin square, ce serait une commande correcte, par exemple.
Moi, j'ai cru que le moment
Non, c'est
Yeah, that's why
un
I
flag
said
de cargo.
the two
En
hardest
fait, ça
things
porte le même
when
nom
you're
pour te
first
dire que
coming
ça
to it
désigne
is,
les mêmes choses. En fait, quand tu dis bin, tu veux un des trucs qui est en dossier bin.
ownership and lifetime are two concepts that haven't.
Si tu veux juste tester le code pour voir s'il y a des erreurs, mais pas le lancer,
In lifetimes, I don't think you have
dans ce
this
cas-là,
anywhere
cargo
in the
check
code,
devrait faire le boulot.
but it's the idea that you want to
Bah,
define how
là,
long the
c'est comme tu veux. Tu peux check une bibliothèque.
You
Mais,
define this, if you want to change the lifetime of the object, you define it
je
via
pense
syntax.
que...
And what you do is
mais
when
en fait, je ne sais pas ce que ça veut dire avec un fichier source sans paramètres. J'ai jamais essayé de faire ça.
you have a lifetime associated with this
Mais
object.
cargo check sans argument, déjà, ça devrait tester la bibliothèque.
Déjà, il y a
One of the
point
arguments that are passed into it.
Mais tu peux commencer comme ça, déjà.
This struct
Et
lives
pourquoi il n'est
as
pas
long as
content? Qu'est-ce que j'ai
this
mal fait?
parameter is passed into it.
Oui, du coup, tu n'as plus l'argument portability vu qu'on
It's
exécute rien du
ugly
tout.
though. The syntax
Dans Run,
itself is kind of ugly, but it's
C'est ça, parce qu'en fait, c'est un argument pour le binaire que tu vas exécuter à la fin. Là, on n'exécute pas de binaire, on dit juste au compilateur, vérifier si mon code il a l'air OK. C'est que de l'analyse statique. Ah, mais c'est pour ça que c'est cool, check. Il y a toujours le passage de Volcano qui est un peu dur. Alors en fait, le problème qu'il y a là, mais il te donne l'explication parce qu'il est gentil, c'est que quand tu construis ce callback, tu as envie qu'il emporte avec lui une copie de la barre de progression pour pouvoir de temps en temps l'utiliser. Mais par défaut, c'est pas ce que font les lambdas en Rust. Les lambdas, ils prennent les variables de l'environnement par référence. Et du coup, si tu as pris une référence, tu n'as pas le droit de le sortir de la fonction parce qu'après, ta référence, elle sera plus valide. Et c'est à ça que sert le move dont il te parle plus en message. Le move dont il te parle un peu plus en message d'erreur.
Ok.
Non, je pense que... alors, le gros, là, j'ai expliqué ce que c'était tout à l'heure, c'est que tu as des extensions VULKAN du futur et ça le perturbe. Ouais. Les plus petits, il faudrait que je regarde qu'est-ce que c'est pour... C'est un peu le truc avec le validation, c'est il a pas mal de faux positifs. Il ne faut pas être très impressionné, très facilement impressionnable. Bah parce que le validation layer, il existe qu'à l'exécution en fait. Il est lancé quand ton appli est lancé. Cargo check, c'est que de l'analyse statique, c'est géré par le compilateur Rust et VULKAN n'a rien à voir là-dedans. C'est pas grave, c'est juste, il te dit que tu as deux bouts de ta pile logicielle qui ont des versions qui vont pas bien ensemble et il va se démerder. Ouais. Ouais. Et donc toi, tu n'es pas un conteneur, mais tu l'as quand même. Alors c'est peut-être que tu as une vieille version du paquet validation layer par rapport à ton driver VULKAN ou qu'ils n'ont pas encore packagé une nouvelle version.
Ah non, parce que le validation layer, c'est natif dans Ubuntu.
Ouais, alors c'est natif.
En 24,
Bah, on espère, parce qu'on a vu tout à l'heure que ça n'avait pas été le cas de ton driver.
Ah, mais driver check with.
On espère que ça a été mis à jour, en tout cas. Mais autre problème, c'est que des fois, les paquets de distrib, ils ne sont pas forcément ultra frais en termes par rapport au projet logiciel sous-jacent. Et donc, si NVIDIA, de leur côté, comme ils distribuent leur logiciel eux-mêmes, ils ont décidé de mettre des extensions VULKAN toutes neuves et que le paquet est distribué par Ubuntu 24 Il est encore un peu trop vieux par rapport à ça, tu auras quand même ce problème, mais tu l'auras moins parce que tu as moins de nouvelles extensions.
Comment on check un file en particulier?
Tu peux pas checker un file parce que l'unité de compilation en Rust, c'est la crate.
C'est là?
C'est la bibliothèque ou le binaire, si tu veux.
Donc, je suis obligé de. Là, quand je suis en source, il regarde tout ce qui est dans source.
Il va regarder tous les trucs qui sont directement à la racine de source plus ce qu'il y a dans le grayspot. Il va pas regarder ce qu'il y a dans bin et dans benches.
Ah, ok.
Ça, c'est le comportement par défaut. Et après, avec moi moins bin, tu peux lui dire de regarder un binaire précis.
Ok. Avec check aussi. Pas run seulement.
Avec check, ça marche avec pas mal de choses.
C'est une bin,
Tu as une option qui est assez pratique, mais qui ne marche pas dans mon cours, qui s'appelle All Targets, quand tu as envie de tester tous les binaires à la fois, tous les trucs à la fois. La raison pour laquelle ça ne marche pas dans mon cours, en fait, c'est que j'ai un peu truandé avec les benchmarks parce qu'il y a pas mal de code compliqué dedans. Donc, je vous file d'avance la version qui marche à la fin du cours. Et donc, elle va jamais type check parce qu'elle demande des trucs qui ne sont pas là, en fait.
Ok, this is fine at the beginning. Thank you. Okay.
But yeah, anyway, that's the reason why.
Yeah.
All right. So let me maybe cover one more chapter before the coffee break. This way I get a bit more time after the coffee break to get into something. I would like to show you a little bit of GPU profiling so that you know what it looks like because I didn't do it last time. So earlier we saw what it takes to take our Grayscott simulation and turn it into a bunch of compute pipelines based on GLSL. But we have the same problem as before. We have a GPU program. We do not yet have data to feed into this GPU program, and that's something we need to fix. Here I'm going to use VULKAN descriptor sets, the way they are meant to be used, which is to say that ideally, whenever I run a GPU program, I would like to only need to bind one descriptor set, and in an ideal world, in a sufficiently complex application, 0 descriptor sets. Here, I cannot easily get to 0 because I have a set of inputs, a set of outputs, and it's changing every iteration of the simulation. I could actually work around this, but at the expense of losing the convenience of the read-only and write-only in GLSL and making all my buffers read-writes. I decided against it because I measured the actual CPU overhead of an implementation, and binding one descriptor set is not going to kill my performance. And if I can have cleaner code, I prefer the cleaner code. Thus, I will have two descriptor sets that I will alternate between. One of them will use a pair of buffers. Treat one of them as the input U concentration and input V concentration, and the other pair as the output U and V concentration. Let's call the first ones U1 and V1, and the second ones, which serve as output, U2 and V2. What I will do in my second descriptor set is that I will flip the roles. So now U2 and V2 become the inputs to the simulation, and U1 and V1 becomes the outputs. With this, I can bring back the double buffering pattern that I already had on the CPU, but this time it's on GPU. There is just one problem with this, is that it breaks a lot of logic that I wrote back in my CPU simulation, because basically back in the day, I assumed that I had a full vision of my data structure and that I could handle inputs and outputs separately, and descriptor sets in VULKAN break this. What I will do then is to introduce a new abstraction that I call the UV set, which represents one VULKAN descriptor set. So pair of inputs, pair of outputs. And it contains two things: a VULKAN descriptor set that I can later use when executing my compute pipelines, and the raw underlying buffer that are used as inputs, which I will need by the time I download my GPU data towards the CPU. Actually, this information is already present in this one. The problem is that descriptor sets are very generic abstraction, as they can contain a lot more than buffers about many obscure GPU memory resource types that you've not heard of. And this means that fetching a particular set of buffers from a descriptor set is a bit of a pain. So considering that Volcano uses reference counting everywhere, you know, I can just have another copy of my buffer reference counted pointer. It's not going to ruin my memory, and it works. The setup is going to be tricky as well, because remember, I have 4 buffers, and they play different roles in the 2 descriptor sets that I'm going to build. Which means that now I cannot build buffers in the constructor of my descriptor sets, because they will need to be the 4 same buffers, right? Which is why I need to do something a little dirty here by having 2 different constructors, one that builds 4 buffers, one that takes 4 buffers and put them together into a descriptor set. And then I leave the rest as a concern to the caller, which is going to be my concentration struct that does the double buffering. Not the best software engineering in the world, gets the job done. The buffer allocation looks like this. I can get from my command line option how big my simulation domain is. Because now I have 0 padding, I need to remember to add the padding to this for the rows, for the columns. Then I can use a new slice constructor from the Volcano buffer abstraction. By default, it builds GPU buffers because that's what you use most of the time. So I have less parameters to tune. But what I do need to tune is to tell Volcano early on the ways in which I'm going to use these buffers. There are 2 usages here that should be obvious to you and one which should be more surprising to you. I need the storage buffer usage because eventually I'm going to take these buffers and bind them to my compute pipeline as a storage buffer. Okay. And I also need the transfer source usage because at some point I'm going to take my GPU data and download it to the CPU. So far, so good. But if you have been following what I've been saying earlier, you may be wondering where this one is coming from. Because I have a GPU side initialization, so I should not need to transfer data from the CPU to the GPU. We will get back to this, but essentially the reason why I need that is that one of the buffers that I'm building, I'm going to set it to a bunch of zeros using an optimized VULKAN routine called the clear command, which is basically a memset for GPUs. And for some reason, the VULKAN API designers, in their great wisdom, decide that this was kind of a memory transfer destination. Then, you know, I need to have this number of elements, which is the product of my rows and columns, the usual stuff. At this point, I have my 4 buffers. Now, magic is going to happen into the caller. We'll get back to this. And at some point, the caller is going to build the descriptor sets. And what we are going to do is we are going to start from the pipeline layout, which gives us the layout of our descriptor sets. And we are going to say now in this descriptor set, we will write to the first binding, which is the binding of input buffers. And we are going to write an array of buffers into this binding starting at position 0, which is the first position. And here we are going to put our input buffers for U and V in this order. Then we are going to do the same thing for the second binding, which I call the output binding. Again, starting at position 0, but this time for the output buffers. And remember again that what constitutes an input and output buffer is decided by the caller of this function, which means I will later be able to call this flipping the roles of the buffer. Once I have decided how I want to write into my descriptors, I can build the descriptor sets, and the building part is done. Now I mentioned that because I'm doing something a little nasty here, I need to offload some of the concerns to my caller. So let's go look at the caller. Remember that in the CPU simulation, I managed to decouple the concerns so that the concentration struct only took care of double buffering a pair of concentration and alternatively treating one as input, one as output. Here, unfortunately, it will have to do a bit more work. The beginning of the adaptation is easy. Before we had UV pairs, now we have pairs of descriptor sets, which, thanks to reference counting, is not as expensive as it may sound. But now we have this small function called create and schedule init. What it's going to do is it's going to create the 4 buffers, the associated descriptor set, and it's going to enqueue in a VULKAN command buffer the commands necessary to initialize the data inside of our various buffers. So we start by allocating our buffers, 4 of them. Here I need to play a dirty trick because arrays are hard, essentially. We can go more into detail of this if you want. And then I build my descriptor sets, flipping the roles of U1, U2, V1, V2, as I mentioned. So far, so good. Now I want to prepare to initialize my data. For the data that's going to serve as the first input of my simulation, I'm going to use the initialization compute pipeline that I mentioned earlier. So I'm going to perform GPU-side initialization so that I do not need to do a copy from the CPU to the GPU. So I bind the pipeline, I bind the resources that it's going to use, which is going to be the second descriptor set, because the output of the second descriptor set is the input to the first descriptor set, which is the first one we're going to use later on. I need to compute my work group, my number of work groups correctly. And again, I'm thankful to use a programming language that has diffcil. Every programming language should have this. So it's the padded number of elements divided by the user requested workgroup size, rounding up because we need to handle the trailing elements, even if they do not fill an entire GPU workgroup. Once that is done, I am ready to execute my initialization pipeline. And this is unsafe because Volcano cannot check for us that our GPU code is not going to have any undefined behavior. It tried to help us at the previous steps, but the GPU kernel parts, we are no, sorry. Maybe something for future GPU APIs built on top of VULKAN. What about the second set of buffers? You may think that we do not need to initialize them at all, but that would be forgetting about the 0 boundaries. We still have those to take care of. We could have a dedicated GPU kernel which only sets the boundary to 0. But your GPU driver has a very fast memset-ish implementation. It does not cost a lot to generate zeros that we don't care about. Especially since we are only going to do the initialization on the first simulation run. And in a real-world simulation, we should be doing many simulation steps. So all this will be amortized. Also, it saves us from the work of writing one more GPU compute pipeline. So I will take the lazy route here and just treat my buffers, which contains floating point data, into a buffer that contains integer data, because for some reason, VULKAN only supports filling buffers with integers. But 0 in integer is the same as 0 in float. Life is nice. And in the end, I am ready. Well, at least I will be ready after this command buffer has been executed. The rest will be similar. We drop the shape accessor because, as you will see later on, we are not going to need it anymore. The current accessor is easy to adapt. The update part actually becomes simpler because before we used to decide which buffer is the input, which is the output. No, we don't. We are using descriptor set, which contain both inputs and outputs, and we just take the current descriptor set and flip the descriptor set each time. We do have, however, a new GPU-specific concern to take care of, which wasn't there before, which is that in the world of GPU, every single operation is fallible. And this includes whatever we are going to do with this descriptor set. So we need to handle the possibility of this user function returning an error, and if there is an error, propagate it to the caller. Finally, we do not need to send input from the CPU to the GPU, but we do still need to get the outputs back from the CPU. Here we could have adapted the UV struct that we used to have before, which contains a pair of concentration for U and V synchronized. But we actually need to think about what we want here. Our main goal is to write down the concentration of the V species to HDF5 and the V species only. We are not using the concentration of the U species. If we start building now abstractions around the pair of species, it means that to be consistent with ourselves, we are going to need to download twice the volume of data, of which we will only be using half. So as long as we are very confident that we only need the V species concentration, it's better to switch to an abstraction which is specific to the V species only. Well, I could make it more generic by saying it's any species, but since I only care about the V species right now, I do the simplest code that will possibly work. And here I need the buffer as usual. And much like on the GPU side, I do have a problem, which is that I have a buffer, but I don't know how its elements map into rows and columns. So I will play the same trick as I did before, which is to keep around the length of my lines so that later I can do 2D computations without asking users to pass me the parameters of the simulation over and over again so that I can discover it again. So how is it set up? This looks very much like the buffers we have set up previously. If this were production code, I would consider duplicating the code. I need to, as usual, compute the full size of my buffer, including paddings. I mentioned, padding compared to variable size stencils, you win in one area, you lose in another. Pick your poison. I need this buffer to be suitable for downloading data from the GPU to the CPU. That part is hopefully obvious. And I ask the memory to be, if possible, allocated on the CPU side, because I'm going later to access it from the CPU side or to do the HDF5 writing. And to be suitable for random access, because I don't know what HDF5 is going to do, but it will most certainly not be a sequential write. The rest is as before, so I don't think it's worth commenting. I then add a method which allows me, starting from this buffer, to schedule an update to it. This is part of a strategy which I mentioned in the previous part of the course, where before I used to have this huge function that did everything with command buffers, and it ended up being a quite complex function with many parameters, and I would like to break it down into smaller GPU transactions in the interest of keeping code intelligible. So here, it's just a buffer copy. We start from the V part of our set of resources, which remember is the input part. And we download it to our internal CPU buffer. Finally, we want to allow users to access this data as a two-dimensional array. You know, one-dimensional array are something we have to do internally because VULKAN does not know any better. But we don't want to expose this to our user. We want them to think that the world is 2D and memory is 2D and everything is nice. So we have this function, which has a bit of a weird interface design. You would expect maybe this function to return an array, a two-dimensional array, which actually it cannot do, or at least not without going through some very dirty tricks. Because Volcano is trying to protect us from data races between the CPU side and the GPU side. And the way it does that is that it gives us RAII objects that allow us to acquire a kind of read lock from our buffers. The idea here is when I want to read a buffer, I ask Volcano to read from it. It checks that I didn't mess up by trying to read to something that the GPU is currently writing to. If it's all good, it gives me an accessor, and as long as this accessor is active, Volcano will not schedule any command that writes to this buffer on the GPU side. And this way, memory safety is achieved. Once I have this temporary, it has a destructor. In Rust, we use the drop trait for that, which will ensure that once I'm done accessing this data and it's not reachable anymore, the lock will be released, and I can use this with a GPU code again. I will then proceed to do the same computation that I have done too many times already. Again, some candidate for later code refactoring to have this in less different places until I know how many rows and columns I have. And then I can use NDArray to turn my one-dimensional data set into a two-dimensional view. Once I have this view, remember that view still includes our 0 elements on the sides. That's an implementation detail, right? We don't want to expose that to the user. The user shouldn't care whether we chose to have irregular stencils or 0 padding values. So what we will do is we will slice this two-dimensional array to only take the center part and only expose that to our user. So the user doesn't need to care that we have 0 padding. And once we have done all this, we can finally call the user callback, which will accept this two-dimensional array view, do whatever the user wants with it, and at the end, return some result that we are going to forward to the caller. There is one last step, which I wish didn't exist, but currently it does. The AZA5 binding that I am using will not allow me to write to AZA5 data which is not contiguous in memory, which is not the case here because remember, we have hidden the 0 padding elements. So I'm not fully up to date on my AZA5, but I'm pretty sure that's a Rust binding limitation, not an AZA5 C library limitation, so it should probably be fixed. But in any case, we can work around it in a dirty way, like all workarounds, by just making a contiguous copy of our data for now. If this becomes a performance problem, we'll fix it later on in the optimization section. The rest is as before. Are there any questions on this part? If not, I propose that we conclude for now, have a coffee break. We will get back at 4 p.m. for more, the last word on this story. And have a nice break. And we are back. So the last session of today's journey on how to move from bad GPU APIs to a different kind of GPU API, to a different kind of bad GPU API. So in the previous steps, I've shown you what is involved when we start implementing the Gray-Scott reaction on GPU. We saw that the basic VULKAN context logic can stay almost the same modulo some logging tweaks. We need new compute pipelines, obviously, because we are doing different computations. And we are going to need different memory resources to bind to those pipelines. And I attempted to show what kind of challenges get involved when we try to port CPU application to a GPU application, and how the specifics of GPU hardware will affect our abstraction design as software developers. Finally, we now have GPU programs, data. It's time to put them together and get a full working simulation. So what are we missing? One thing we are missing is a way to schedule our actual simulation steps. And that will be the job of a new function called schedule simulation, which is basically all that remains of our former huge build command buffer function once we extract everything we can and make it focused on running the simulation only. We start with yet another computation of our workgroup size. Remember, the design we have used for the simulation is that we will be spawning one GPU work item per active cell of the simulation, not including zero padding around the data set. So here we do not have the addition of the padding, but we still have a division by our workgroup size. This is GPU, we won't get around it. After this, we can bind the compute pipeline associated to your simulation. And then we will do a bunch of steps. We will basically do all the simulation steps that happen in between two output images. For each of these steps, we are going to call the update method of the concentration double buffer, which will take care of the double buffering for us, and give us each time the descriptor set that's associated to our current inputs and outputs. We will then proceed to bind this descriptor set and schedule one simulation run. One thing which is important to remember here is that at this point, we have not actually asked GPU to perform any work. We have just prepared a recipe of sorts called a command buffer, which is a list of action that the GPU will take as soon as we send it this command buffer. And here we are using a design where we assume someone before us allocated a command buffer, maybe put some commands in it, and we are going to put more commands at the end. The reason why we are using this design is that this will allow us to handle the initialization of our data set a bit more elegantly later on, as you will see. The optimization-minded among you may be shocked or hurt even by the fact that we are computing the number of workgroups every time we call this function. I can assure you that your compiler is totally able to optimize this repeated computation into only one computation. And even if it doesn't manage, compared to the cost of everything else we do, dividing a pair of integers is not the worst thing in the world. There is, however, something that I would like to point out, even if I have not yet written the course part that will go into more details on this, which is that here we are building a command buffer which can get really, really large because the size of this command buffer is dictated by a user control parameter. This can become a problem because while we are building this command buffer, our GPU is potentially doing nothing. And the longer it gets, the more likely it is that we are starving the GPU of work. So in a more realistic simulation, what we would most likely want is to have some kind of internal granularity where at some point, if we have enqueued too many commands, we send the current work we have to the GPU so that it can start working, and then we start enqueuing again. We are not doing this yet because this is version 1. We want to be as straightforward as Vulkan will allow us. Then we rework the run simulation. And here I played a bit again with software abstraction design. What I wanted here is to fix one slight defect of my CPU simulation, which is that the run simulation was part of the common library, but actually it could only be used by the simulation binary because it did things that only the simulation binary should be doing, like writing data to an SDF5 file. I wanted to address this with a slightly better abstraction design, which here takes the form of a pair of callbacks. One of these callbacks will be run after we have scheduled the simulation steps in the command buffer, and it will allow the caller to enqueue extra work in the command buffer. And this callback will also be provided with the knowledge of the current simulation input, which is the output of the previous step. And the second callback will be run after we have waited for the GPU to do the work. And by combining these two callbacks, we'll be able to schedule a download of our GPU data to the CPU in the first callback. And then later, once the data is downloaded, get the data, write it to SDF5, and update our progress bar. And now we get a better separation of concern, and everything is nicer. In terms of the rest of the code, it looks like this. So now we have GPU pipelines to set up, one for initialization, one for simulation. That's why now the struct is called pipelines. They share a common layout because this allows us to have common descriptor set, which makes everything easier. I have this small utility in there which allows me to spawn as many command buffers as I like. I will always create them in the same way. I do not need to fine-tune this. I create an initial command buffer. And in this command buffer, I will schedule the initialization of my simulation dataset. Then I will do a loop over the simulation output steps that I need to perform. So the number of images that I intend to produce and write to SDF5. In this loop, I will call my schedule simulation method, which you have seen earlier, whose goal is to enqueue all the commands needed to run the simulation steps we need to run. Then I will invoke the user-specified callback so that if the user of run simulation wants to download stuff to the CPU, for example, they can. And at this point, I consider that my command buffer is complete. So I will build it, send it to the GPU, and for now, synchronously wait for it to be finished. This could be improved later on. Once this is done, I can notify the caller that the data, if they ask for it, should be ready, and they can write it to the SDF5 file and whatever. And then, because I have used up my command buffer, I have submitted to the GPU, I will create a new one and repeat the cycle for the next loop iteration. As I mentioned, the SDF5 logic is now inside of the main simulation binary instead. What happens there is after parsing command line options, setting up a progress bar, setting up a Vulkan context, this part has not changed. I will set up a CPU buffer for download. This is now the responsibility of the main simulation binary only, since we may not want to do this in the benchmark. Then I will set up my SDF5 file output. Again, this is now the responsibility of the binary, not the library. And I will run the simulation with, as I mentioned, two callbacks that allow me to schedule my optional data download and saving to SDF5 and updating of progress bars. Once the simulation is done and I run all the steps, I will close my SDF5 file. This could be done by the destructor, the drop implementation, but doing it manually allows me to handle errors explicitly, which I would not otherwise be able to do. And finally, once I have written all my SDF5 data, I can declare that the computation is finished. This will make my progress bar disappear, and I'm happy. Beyond that, I have actually sneakily, in the code base that you have been provided with, prepared the benchmark in such a way that it can now benchmark this version of the simulation in many different configurations, so that you can see how the performance depends on the various available tuning parameters. We could be studying this further, but benchmark runs will take a while. So if you want them, you can maybe check out the solution branch and start them. Meanwhile, I will tell you about the one optimization that I managed to implement before this course, which is an optimization that you will not be seeing in other courses because, this is a compute school. We like to focus on stuff which is compute, even if it doesn't matter to a particular use case. In this particular case, it doesn't matter, because our simulation, by the time we have GPU levels of computing power available, actually is not limited by the speed at which we compute data anymore. It's limited by the speed at which we write it to disk. And this is the case even if you have fast flash storage. And there is a simple way to prove this, which is to run the simulation twice, once in its default configuration, which will put the file in your local directory, and another time sending the output to something which is a bit of a Linux hack called devshm, which is backed by RAM, so much faster. If when you run a program that performs any kind of I/O in these two configurations, you see a big performance difference, and I would call the difference between 2 minutes and 20 seconds rather big, what this means is you are bottlenecked by the speed at which you're writing data to your storage. And this is the thing you should be working on first, actually, not the simulation part, because it really doesn't matter. So how do we take care of it? We have many, many different ways. It's I/O optimization. We don't do it in this school, but it's cool. Study it. The first thing we should do is make sure we are using the fastest storage device that we have available, which meets our engineering requirements. For example, one very common mistake in HPC centers is to run programs in your home directory, which is typically backed by a distributed file system that has extremely bad I/O performance. HPC centers are aware that distributed file systems are performance challenged. They are not here for performance, they are here for consistency. The idea is that all your nodes can see the same data at a price. And so what you should do if you need a very high throughput I/O is to use something called a scratch file system, which all good computing centers have, which is basically a disk on your local machine that other nodes in the supercomputer don't have access to. And then you get much better performance. The RAM disk I showed you earlier is a cool trick when you are not too tight on RAM, which can allow you to get even faster performance in situations where you do not actually to keep the output after the simulation run, because it's going to be part of a pipeline where the next stage will take this output and do something else with it and produce the result you're actually interested in, for example. Second thing you can do, as always in hardware, if you have money, use it. Okay, not that much environment friendly, but sometimes more hardware can be the solution to the problem at hand. In particular, if you know your application is very sensitive to I/O performance and your server is using a spinning disk, it may be a good idea to have an SSD for those I/O intensive workloads. It will give you a big I/O throughput boost at almost no application costs. Then we can start storing less data. This is what the other courses have been sneakily doing. So you increase the number of simulation steps you do between two writes. So you write less images, but you do more work between images. You can make the eyes of Vincent bleed by storing lower precision data. You know, half precision, all kinds of lossy compression. People have been getting really creative with this. The point here is often the precision at which you need to store data is not the same as the precision you need during a computation. Because during a computation, you have things like accumulation, cancellation, and this sort of stuff require you to have more bits of data available than the actual precision of the inputs you are getting and the outputs you are producing. When you reach this point where I'm done with my computation, I should store the results, it's a good time to ask yourself again, how many significant digits do I expect on my results? And what is the appropriate storage type for this number of significant digits? But let's say you have an annoying physicist colleague who will not tolerate any form of lossy compression because they don't know what their precision requirements are. It's more common than you think. Then what you will do is you will turn to lossless compression. It used to be the case that algorithms like gzip were effective. That was on spinning disk. On modern flash storage, the storage is so fast that if you try to use some format like gzip, you will spend more time compressing your data than storing it. And it's better to use those algorithms like LZ4, LZO that do not compress very much, but compress very, very quickly at very low CPU costs. There is another optimization that you can do. Again, this optimization, by the way, I sorted in the rough decreasing order of decreasing expected effectiveness. So on the top, you have the stuff that should give you the biggest benefit. The more you get to the bottom, the more it's a cherry on the top, you know. At the bottom, so on number 6, I suggest that if you have some kind of I/O-heavy operation, but the time you spend in I/O remains relatively close to the time you spend computing stuff, it's a good idea to offload your I/O to a different thread, because this will allow you to have I/O and computation that occur in parallel, and an I/O thread that spends as much of its time as it can writing data to disk. For a few selected file formats, you can actually even do better than this and have multiple threads doing I/O at the same time, but that's not an option for many I/O libraries, so I will not get into details of this here. And finally, once you have done all that, you can start thinking about the stuff that makes sysadmins happy, like you know, tuning the block size of your writes, comparing whether HDF5 and FITS is faster. Spoiler, they have both been optimized enough. This is the small gain region, but you know, if you want to get the best of the best, we need to do that too. So here, just to put what we've done so far in perspective, what I've done above by using RAM disk is actually an example of strategy number 1. For my benchmarking purpose, maybe I don't need actually to store my outputs to a persistent non-volatile storage device. I can put it in RAM, it will be much faster. Because the spirit of this school is not to teach you all about I/O, I will show you another optimization which is easy to do, even if it's not the most effective, which is to make I/O asynchronous. And then we'll switch to the extreme version of the store less data strategy, like everyone else, where we just store no data and then everything becomes faster. So how do we actually do this asynchronous I/O thing? The general idea, at least the simplest design you can use, and most of the time it will be very effective, is to have 2 threads. One is in charge of handling the computation, another is in charge of handling the I/O. And in between the 2 threads, you will put a shared data structure, which is a queue in, first out order. The fact that it's first in, first out will allow you to get the same result as if you ran the program sequentially. One very important property of this queue is that it should be bounded. That is to say, it should accept up to a certain number of elements. And if the number of elements gets bigger than this, it should reject elements and have the calling threads block. Why do you want this? Because otherwise, in applications like what we've seen above, what will happen is your compute thread is faster than your I/O thread. So the I/O request will pile up, and your memory usage is going to explode. You don't want this. Assuming you have used a bounded FIFO queue, then you will get two scenarios. If the compute thread is faster than the I/O thread, then what will happen is, the compute thread will quickly fill up the buffer, start sleeping. At some point, the I/O thread will be done writing its current image. It will fetch the next one. This will wake up the compute thread, which will prepare another one, while the I/O thread is writing. And what you will effectively get at the end is an I/O thread that spends 100% of its time writing images continuously, because it's basically the limiting factor. Again, for this to go well, you really want to have a bounded queue. If you are interested, look up the notion of back pressure. This is a very central concept in any kind of network programming, distributed systems. And yeah, anytime you want asynchronous I/O, usually you want bounded queues. Now let's say that we actually did not see this coming, but maybe the I/O thread now is faster than the compute thread. Maybe we are doing lots of compute. This is actually the case of our CPU simulation. It's fast, but not fast enough to saturate my SSD, because SSDs are really fast as well. What will happen then is that the compute thread will be the one that's working 100% of the time, furiously pushing images through the queue as fast as it can, while the I/O thread will be fetching an image, writing it, and twiddling its thumb, waiting for the next image to arrive. I would argue that this is not a good scenario for asynchronous I/O, because we will pay a few extra costs linked to the fact that we have two threads, communication, and so on, and we will not amortize them with faster I/O because we are not actually limited by I/O. So this is a special purpose optimization, know when to use it. In the real world, applications may not fall neatly into this dichotomy. You may have variable compute performance, variable I/O performance, which means that sometimes the I/O thread will be fetching lots of data quickly, and sometimes it will not fetch data for a while. That's typically the case if your operating system does some batching under the hood. If you are in this sort of situation, then what you will want to have is a bigger queue with more storage capacity. A larger queue will not allow your program to get faster if it's limited by the I/O device. What it will allow you is to get more tolerance to variation in compute and I/O speed. So what does it look like? Well, first, as I mentioned, the number of elements in the queue is a tuning parameter. So like all tuning parameter, we will expose it on our command line, because we are nice people, we don't do hard-coded parameters. Then we will write a function which sets up an I/O thread, which accepts images from an I/O queue, and then writes them down. And it looks like this. So first of all, we set up something called a sync channel. That's a primitive from the Rust standard library, which is basically bounded FIFO queues with some tweaks. Then we set up the AZF5 writer, because this is not going to be the responsibility of the I/O thread. We want to get this off the main thread. We are going to make a copy of this. I will get back into why we need to do that. And then we will call the standard library function called std_thread_spawn, whose purpose is to start a thread and give you back a handle called the join handle that you can later use to wait for this thread to be finished. Inside of this thread, our thread will be repeatedly getting new images from the other side of the queue, writing them down, and when it's done writing, it will increment the progress bar so that we can still see some progress. At the end, we will close the SDF5 file, say your progress bar is finished, and we are done. When we've done all this, we get two things: a join handle, which is something we can use to wait for our IO thread to be done, and a synchronous sender, which is one of the sides of the FIFO queue that we can use to push images into the IO thread. And that's all we are going to need. But to get back to the thing, so here's the reason why I need to do this, is that this parameter comes from the option struct. And the option struct, if you look at it, is something I get by reference. And because Rust cares about memory safety, it does not let us send references to threads by default. Because then we need to be careful about keeping the data that's referenced alive as long as the thread is. So what we're doing here is we are making a copy of this tiny integer, which is the only thing we care about. And we are moving this copy into the thread, and then it's an independent copy. The thread can have fun with it, and there's no risk of reference invalidation. Another thing you will notice is that my FIFO queue does not take array views as we had before. It takes owned arrays of data. The reason why that is the case is that, if you remember, our array views are borrowed from the CPU download buffer. And as soon as we are done with this buffer, the general computation logic is free to use it again to download more results. So we don't want to send our thread references to a buffer that will be overwritten later on. It won't work. So what we do instead is we are going to send own copies of the data, which means that we can get rid of our hack in the SDF5 writer because we don't need it anymore. We have own arrays with contiguous storage. The main function then becomes this. So we parse our command line option, set up a progress bar. We start an IO thread. Before we used to set up SDF5 here. Now we say this is a responsibility of the function that starts the IO thread. We get back a way to send tasks and a way to await the thread. Then we set up the VULKAN context as usual, the download buffer. This part has not changed. And in our second callback here, after the data has been downloaded from the GPU to the CPU, what we will do is, instead of processing it right away and writing it to SDF5, we will send an own copy of this data to the IO thread for further processing. And then here we have something nasty. This combines multiple ergonomic flow of the Rust standard library into 2 lines of code. It's those sort of lines of code that are written in pain. So we want to wait for our IO thread to be done. And the reason why we want this is otherwise we cannot handle errors that are linked to the IO thread crashing, like maybe something as panics, for example. But here we hit the first ergonomics roadblock, which is that when we do this, we get something that does not implement the standard error trait, because panics in Rust are weird. So we need to handle this in an unusual way by crashing if the thread is crashing. Okay, that's not nice, but it's fine. And when we await the IO thread, we need to take a second precaution, which is that we need to drop the IO channel before we do that. Otherwise, what's going to happen? Let's walk back a bit into our IO thread. What it does is it waits for data coming in from the receiver. And when there is no data coming anymore, it will close the file and stop. But how does it know that there is no data coming anymore? It knows because the main thread has dropped the IO channel. So if we don't do it explicitly, we will get something called a deadlock, where the main thread is waiting for the IO thread to finish, while the IO thread is waiting for the main thread to drop the IO channel, and then nobody makes a move and your program is stuck. So yeah, couple of nastiness from the standard library that I'm not too fond of, but now you know. And what you do get at the end is about 2 times speed up. But what I find most interesting, and did not get the time to analyze, unfortunately, is that if you look at it, the user CPU time goes up. This is expected. We've created a bit more workload due to the fact that we have 2 threads now, and we need to transfer data between them. But the system overhead, which represents the amount of time we spend in the kernel, has gone down. And this I don't have a good explanation for yet, but I will be investigating later on. Do we have questions so far? Maybe on Discord I see some stuff. Someone trying Python and having problems. Yeah, environment is hard for everyone, sorry. Yeah. Maybe, peut-être on en reparle après, parce que si c'est spécifique à ta machine. Okay. This is about machine-specific debugging, so since I only have half an hour left, I prefer to do something else with the rest of it. So now I would like to show you a bit a glimpse of what GPU,
So if you would use the other strategies you listed before, the 7 ones, would it theoretically be even faster, or?
Yes, you could get faster. I mean,
okay.
As you saw, we got a huge improvement by using a RAM disk. As I mentioned, this is great. The best storage device when you can afford it is DevNull. It's extremely fast. Yeah, faster storage. I only have 1 SSD. You know, that sounds a bit pretentious when said that way. I could have a RAID of SSDs that each have much better performance than my limited laptop budget will allow. There used to be some SSDs that are basically RAM sticks on a PCI Express slot. I don't know if you can still buy them. Less data. As I mentioned, the ordering is not strict. It's just a rough idea of how much you can get in realistic situations. Obviously, less data is better. Smaller data is better up to a point where the data is meaningless because it's not precise enough.
Okay, thank you.
How does this async I/O compare with direct storage? That's a good question. I would need to look up the direct storage part to answer this. But I put it in my to-do list for later. So maybe let me show you a bit GPU profiling on something other than NVIDIA hardware. Lets you think that only NVIDIA has nice tools. Personally, I've been burned by NVIDIA drivers one too many times, so I decided that as much as I can allow it, I would not have any NVIDIA hardware on my computer ever again. And this is a choice which had consequences, as you can imagine. But I think it was the right one.
What do you use?
AMD. If you want performance and it's not NVIDIA, it has to be AMD. Performance is not, GPU performance is not something that anyone else I know of does well.
And your CPU is not crashing?
No. You know, there are 2 things on AMD actually. There is the graphics stack. No, but let me show the profile first and then I will zoom. There is a graphics stack and there is a compute stack. The graphics stack is the VULKAN driver. This part is extremely stable, has been for many years, and it has even been tightly optimized by people from Valve, the authors of Steam. And then you have the compute stack, which is called VULKAN, which is one of the worst pieces of software shit that I have ever been exposed to. The nice part of doing VULKAN is that I only need to touch the good part of AMD software and not the bad part. So this is a profile of the live simulation that I have been showing you earlier, and it seems it does not support Zoom, so you will need to trust me when I point things on the screen. Sorry. So what do we have? We get a set of frames, which are images that get shown by the window that I put on the screen. For each frame, I can see what the GPU has been doing. So here it's been processing a big command buffer, then a smaller command buffer. I can zoom in a bit. And then another command buffer that involves something called VKQPresent, which, if you knew about parts of the VULKAN API that I have not shown you, would tell you that this is the part that actually renders stuff in a window. So what this program does, and it's not optimal because I never got the time to optimize it properly, is it does all the simulation steps. Then it downloads the results to the CPU side, and then it uploads it again. I need to fix that at some point. I will someday. The reason why it does that is that this allows me to render data both from the CPU side and the GPU side. I can switch between all the different implementations of the Grace code simulation. So here already, if I didn't know this profiler would tell me that I have something fishy going on. But it tells me other things. It tells me this application is CPU bound. And the reason it tells me that is that you can see that the GPU is not working all the time, which from the perspective of GPU manufacturers is bad. You should be getting the GPU to work all the time, doing hopefully useful work. The reason why it's not working all the time is that, remember, we are doing 32 simulation steps per image. And as it happens, this GPU is so powerful that it can do all the 32 simulation steps in less time than a screen frame. So at some point, you've done your steps, send the image, and you are waiting for the screen to display the next image. If you paid attention earlier, this is another instance of the bounded FIFO queue pattern that I mentioned. Again, for any kind of asynchronous I/O, you will want this sort of pattern. I can get more information, like I know that in each frame I do 3 submissions to the graphics queue, which is the main queue of my GPU. And all 3 are command buffers, and I'm using 3 wait operations. I don't remember why 3, I will need to look it up. And I can look at the barriers, and I see that I have many barriers because Volcano is not perfectly optimal in terms of how many barriers it inserts. But thankfully, that doesn't matter because as the profiler tells me, I'm spending 0.04% of my GPU time in API barriers, and frankly, this is not the kind of performance I care about. I can see that the most expensive event is the dispatch of a specific command buffer. And I can tell you, because I know my application, that this is the buffer that does the simulation and not the one that does the drawing. We saw that a bit in the earlier timeline. But if I didn't know, this is the place where I could check. I can see that I have 2 compute pipelines, and I can have some statistics which will tell me, if I have something like overly complicated GPU code that the GPU hardware struggles with handling, resulting in worse performance, and some system information. And then I have the events screen. And what the event screen will tell me is how one GPU frame looks like. So here I have this timeline. And at the top, I have the graphics queue, which for this GPU is the main queue that can do everything, as in OpenGL. And at the bottom, I have the asynchronous compute queue, which is something to which I could send extra jobs when there are already jobs running in the main queue. Here, I am not using this capability at the moment. Maybe I could somehow restructure the application to use this extra hardware resource. If my GPU were not a laptop GPU, but a bigger GPU, then I would also have a dedicated transfer queue, also known as DMA queue, which allows me to transfer data while other stuff is going on. And this would allow me to get even greater performance by overlapping data transfer with computations, as David mentioned. I can see that my GPU, even on the graphics queue, is not fully utilized. It's like half utilized. This is something we've been telling you over and over again now. Full HD is not enough to saturate your GPU with a Grace code computation. You need more. At least with this particular kernel, I intend to eventually implement a trick that Pierre did, which allows you to get a bit more utilization. Then you can copy back, and copying is always a lot more efficient than computing. You know, we should have a GPU programs that only made of copies. Everything is so much better from this perspective. And here you get some statistics about how we are using the various layers of caching in our GPU, you know, how effective it is and so on. This could be used if we suspect a memory bottleneck, and we could actually tell with those statistics if we do have a memory bottleneck or not. Here you can see that our first level of level 0 cache has lots of hits, but when we go out of it, the level 1 cache is not that well utilized. Maybe there's something we could do here, but I would need to get some hardware schematics first to know what the level 0 cache corresponds to. Profilers give you info, but you need hardware specifications to know more about what the information means. I could see other things, but I will just show you a different view. So this shows you how the execution of the command buffer is decomposed into individual commands. So here you can see that we have compute dispatch commands separated by no less than 4 pipeline barriers. That's 3 too many. We need 1 because we don't want the simulation steps to overlap, as they cannot, because the result of the next step depends on those of the previous step. But yeah, Volcano is not doing something very optimal there. That's why they are currently reworking their command buffer building process. It's not yet as good as it should be. And then you see that the final copy is a bigger thing, which is perhaps why it has better utilization. And you can look more into the statistics of each pipeline and see how well it utilizes the hardware. And you can do better than this. You can actually look at the instructions. So let me first look at the simulation shader. And here I have annotated GPU assembly, which I can study because NVIDIA, AMD has documentation for their internal assembly that I can peruse to see how the various instructions work. And I see how much time I expended on particular operations. And here you see that there is an image sample operation that seems particularly expensive. Maybe something I should try to improve upon. Spoiler, this is the access to the center element of the stencil. But this I know because I have looked at the GLSL source code beforehand. You see that after this, the second sampling is not perfect. It's also spending a bit of time, and then the next ones are very fast. And what's happening there is that you get all your GPU work items hitting the central location, and then they will start using the other location, and some of these locations will be in the first level cache, and so you will get fast access. But because your GPU work items are not executing at the same time, they are executing concurrently, it will take a while for all the data to have reached the cache. So the second element, you do not get perfect cache locality. We could improve upon this with manual caching using shared memory. And then after that, it does its job as you would expect. You get perfect caching. Then you get this sort of weight CNT. I have no idea what this is. I would need to look the manufacturer documentation because it looks interesting. I spent some time on it. And then at the end of the program takes a while. So this tells you that you don't want your GPU kernels to be too simple. You want them to contain enough work to amortize the cost of running a work item. So that will be it for the profiling overview. Are there any questions? If not, I will ask myself a question. Why am I showing you a profile of the live simulation and not of the code that we've been working on? Remember, earlier I told you that there is one problem with VULKAN Profiler, which is that they assume that VULKAN is for graphics, even if I have hopefully proven to you that you can use it for other things than graphics. In particular, one thing this means is that they are very tightly centered on the notion of frame that gets displayed on some surface. And this particular profiler cannot work when there are no frames displayed on any surface. And that's a shame. If anyone from AMD is listening, please fix this. It's a shame. So to be continued when I find the time to write the other optimization section, getting this, to competitive performance with the other implementations. Otherwise, it's a bit, people will be like, yeah, Rust is slow. No, Rust is not slow. It's just, I spend too much time fighting with all those GPU environments, broken containers, broken drivers, broken GitLab runners that I did not have enough time left to actually write the course. That's what DevOps was supposed to save us from. It has failed. I wish it didn't. I wish those Discord screenshots were not so tiny. So where is the borrow checker? I'm happy. Borrow of move value progress. What are you doing here? Yes. So the problem here in the screenshot that Matthias is showing is that when you set up the VULKAN context, you are moving in the progress bar, which means that the VULKAN context now gets exclusive access to the progress bar, and the rest of the program doesn't have access to it anymore. That's the basic rule of moving in Rust, unless copy types are in. But here, after moving it, you're trying to use it again in this callback. And that doesn't work. In C++, it would be called use after free, or use after move to be more specific. We don't have use after move in Rust. It's a C++ and C specific feature. So what you need to do here is simply to remember that progress bars are reference counted and clone this progress bar here. So you send another reference to whatever code needs it, and then your program will work as intended. Are there any other questions? If not, I think we can end it early, and then either Nabil takes over a bit earlier than expected, or you continue the practical, but I think you prefer this option, right? So, Nabil, floor is yours. J'ai pas mal de choses à récupérer. Ce truc-là, je suis pas encore.
Okay. Je vais chercher mon chargeur. Voilà. Ah, c'est bon? OK. Ça passe? Parfait. So hello everyone. So in this last session, okay, to stay here.
I like to move in the. So for the last this last session of the day, we'll be talking about an introduction to Julia, which quite recent programming language compared to all the others that you saw, except maybe for Rust. But compared to C++, C, Fortran, or the other languages, Julia is a rather young language. So I will follow the following plan for today. So it will be a primer with a general history and why Julia is interesting for scientific purposes. We will speak about variables and types also because there is a specific aspect in Julia for this. Some functions, and for the last item, we'll open up a notebook on Colab, and you will see how we can manipulate variables and how to make a matrix multiplication in GPU on Julia. So the Language Foundation was in 2012. It started from a work for 4 persons. Jeff Bezanos, Alan Edelman, for the most known ones, Stefan Karpinski, and Vida Plas, and it was an association between Yale, MIT, and Berkeley. Also now there is a French group working on Julia also. French people have been very active on the language, especially the École Normale Supérieure at Paris, who were some teams that worked on the Julia parser. We will see that in details later on. The key date for Julia from 2012 to 2019 is about the version 1.0, which set actually the background and the usage of the language. So at this time, actually, Julia got more and more interest from academic people, from industry also, as a stable language. And was actually the real date of the kickoff of the language. Actually, today we are at this version 1.11.5, and you can find a lot of documentation on Julia Hub and also the Julia language discourse with the links just below. So Julia is a high-level programming language, similar to Python or MATLAB, actually, but with the aspect that it was aimed actually to be fast. Okay, so the target of Julia, the aim of doing this language, is to make a high-level, easy, between brackets, programming language, but that computes, that executes, that infers very fast, like C, C++, and Python. So of course, this target is not reached all the time, because you need to do a lot of optimization to do that, and especially because these 3 languages, Fortran, C, C++, has been optimized for a long while ago. So it's very hard to reach these performances. But we still get there. The only thing that you will get more in Julia over these languages is the maintenance easiness. Okay, so the readability of the code is easier. It reads like Python, actually. And the Python community and Julia community are very close one to the other. So Julia is just-in-time compiled. So there is an example in Python for this, is the Numba library, which is also a JIT library. So you can optimize it very easily on different platforms. It has a memory garbage collector implemented natively in the software. It's dynamically typed, but it's different than Python. We will see a very harsh example on this, on how you can do these types in functions, actually. So this is very, very tricky in Julia because it's more static than dynamic in some way, but it gives the easiness of dynamic programming. And also it's object programming like Python. So just-in-time compiled, Julia is composed on two big flow rates, let's say, the runtime and the compile time, actually. And what you see here is something tricky, is that you don't have to execute your code. You don't have always to go to the compile time, to the compile one, okay? So this is very important. The parser, so before this layer, there is what we call the parser, actually, that reads your code and sets up the variables and sets up the memory and all the stuff. The parser decides whether to go through runtime, and where to enter the compile time and exit from it, okay? That's why we will see that in an example also. When you execute Julia for a function, for example, first, you will always go to the compile time, okay? But if you don't change the typology of the function or the typology of the variable of that function, actually, what will happen? You can go directly to the runtime. So the parser work is to do this, to analyze whether you have to go to the runtime directly or whether you have to go from the runtime to the compile time and back to the runtime. Okay? So this is one of the advantages of the language. So this is very complex, of course. We will not get into these details. But I put you here a link to one of the founder of the parser of Julia. That there's a video there that explains very well, actually, how this works. And you will see it also through the dynamic typing of Julia in the example we will see later on. Okay. So some comparison of Julia with other languages. So this has been micro benchmarks. So on specifically targeted small algorithms, not on big codes, on all the stuff. So usually we are close to the half of what we can do on C. We can get close to C, but not that much. Sometimes we are below C, but these are very specific optimized codes. So this benchmark has been done 4 years ago. Okay, there has not been another article speaking of this recently, but still it gives you an idea of how fast Julia can go actually if you code it correctly. Okay, so these are very known algorithms. So this is one of the classic benchmarks that we use for benchmarking codes. Okay, so we're not all the time as fast as C, but we're getting there more and more. C, by the way, C is the reference for speed. It's not C++ or other language. Okay. So it's a general purpose programming language, okay, but not as Python. You cannot do easily web interfaces with Julia. You cannot do finance as easy as you do it in Python. You cannot do, I don't know, network programming or all this stuff. So it's more, how to say it? It's a language done by scientists for scientists. So it's more an academic work. The only external usage to academics that has been used in CUDA is for finance, for trading, for example, because it's fast and easy to maintain. So this is the only use case, very known use case, but I don't want to cite it very much because it's not my field. Okay, but what you have to keep in mind, it's more an academic software, so it's done by scientists for scientists. It's a high level and high performance programming. It offers actually generic programming and polymorphism also. You can have a lot of easy data model extension for operation of use, so ease of operation. The packages are starting to be very, very rich. Not as rich as Python, of course, because the Python community is much larger than Julia. But you have all the deep learning and IA libraries available. You have a bunch of packages to solve differential equations, like the one we are solving here in Grayscott. You can do algebraic computing, and the advantage here is you have integrated parallelism with multithreading and GPU support. So this is multithreading was natively done in the language. GPU has been added afterwards. So developing in Julia is easy. You have many ways to develop under Julia. So you have the interactive text interface, the REPL. You can launch it by the command line. Just type Julia, it works. There is a package manager also. You can use it with Visual Code, with Emacs, Vim, and also for Jupyter Notebook. That's the case we will see today. So something to notice, Julia was a native language with Python and R for Jupyter Notebooks, actually. So there was 3 native languages supported by Jupyter, R, Python, and Julia. And since March 2029, so this is quite recent, 3 months ago, you have a direct integration in Google Colab. So if you want to access a GPU for free, for example, you can use it directly on Colab, Google Colab, and that's free of charge, of course, for half an hour or an hour if you use a low-level GPU. So this is what we will do actually later on Colab. So this is to say that the language is extending its use, but still it is in the scientific community. Another advantage is the multiple dispatch. So we will explain this later on actually with a specific function. I will give an example of this. Julia offers dynamic dispatch actually for all function arguments, and this is called multiple dispatch. So you can change the function and the arguments. Okay, so this is very useful. So if you develop a complicated function for certain type of variables, actually you can easily reuse it actually for other type of variables. So extremely effective in allowing reuse of code developed by others. So this is for code shariness. There is an example here of multiple dispatch actually. And why, actually in this video, it's explained why this multiple dispatch is very, very powerful actually. And it's a kind of unique something in this language. The types. So this is the architecture and the graph of all the Julia variable types. So they are very well determined. So the tree is very specific, starting by any and ending to all the types that we use in usual programming. So the multiple dispatch of function actually is closely related to this. So we will see later on a tricky example of this in the notebook. Okay. Debugging and profiling tools. So Julia provides a rich set of debugging and profiling tools, as does the Python environment, as exactly the same. But the other advantage is that you can add macros in your code. For example, in the Jupyter notebook, we will see this later on. And you can see actually what has been compiled specific to your function or what you did. So this can be very, very easy actually if you want to optimize some function or to see what's the best way to write a function actually, and to see how the compiler actually will execute it. So the code type and the call LLVM actually are very useful for this kind of purpose. So debugging is easy with interactive languages. You have a debugger that is included also in Julia, which is the library debugger.gl. There is a profile that is native in the language, but you can use actually profilers from CUDA or from other actually specific libraries. That also works. So you have for GPU. So this is the example we will see later on for matrix multiplication. So there is almost 300 Julia packages using GPU. So it's a massively. There's a lot of libraries that are handling GPU natively, so you don't have to do it, they do it for you. One of the most famous libraries in Julia for GPU is the CUDA.gl, but there is also support for one API and AMD and macOS with the Metal language actually that specific to their new computers. So I don't use it, but I know people are working on that, so that seems to work, getting some advancement on it. So there's two kind of programming options. You have the array programming, so this is the easy path. That's what we do with the other languages. So it exploits Julia power of code reusability. So when you do this, actually you can reuse code very easily. But you can also develop custom kernels in Julia to allow best optimization. So it's a balance between reusability of the code and optimization, as always, actually, let's say. Okay, but this library is really working well, actually, for the NVIDIA support. Julia is also compatible with other languages, like C, like Python, C, and Fortran. So these are wrapped very easily. The only issue we have is for C++, which is always harder to wrap for other languages. So there is some work with some colleagues, like Philippe Gras is working on this, on automatic wrappers for C++, but this is not optimum yet. So if you want to wrap an existing code, So for Python, it should be flawless. For C also. For Fortran, it works. I didn't use it myself, but for the other language, for C++, it's still, I don't advise you to do that, actually. So going from C++ to Julia is not an easy task. You have to spend some time on it, which is sad for the moment, but that's specific to C++. But in any case, the advice here is if you want to really optimize your code, actually, you have to recode it in .gl, in the Julia native language. Even if you can optimize code in C, in Fortran, actually, the best way for the parser, actually, and the runtime and the compiler time, specific use, actually, of the parser is to recode your program in Julia. It's always advised. So you will always get better optimization, actually, without the wrapping. So it is possible, but it's not the best way to optimize code. This has been done also actually to get people from the other communities getting easily from Julia. But, okay, so for the installation, actually, it's quite easy. So it supports many kinds of OSs, Windows, Mac, Linux, ARM, whatever you want, GPUs on NVIDIA, AMDs, Metal for macOS also. So very easy to install. So you go to this web page, actually, julialanguage.org/downloads, and you just choose the version you want, actually. So for Linux, it's very easy to install through just one command line, and you get Julia working. So when you have this, actually, it depends also in what IDE you want to use. So there is some specific documentation for every IDE, okay? So the documentation is very rich and very well done, and that's regularly updated. So you will not have much problem actually getting the information on how to install Julia and make it run. You can look it through Jupyter kernel, actually. So this is the procedure of the install. So you have to add the package, which is iJulia, and you can run it from there, actually. You can also add the Julia package manager to this command line, actually, and it's very easy to import packages in it once it is installed. So what you have to do is just always keep the package manager updated so it can link the version of the libraries very easily. Okay, I had one of these bugs lately, actually. So for this tutorial, actually, we will be using GPU and Google Colab because I checked it worked very well. It will be not depending on your machine. Okay. So and in the case you want to use it with Jupyter, so in case when you type this command, in case Jupyter Lab is not found, actually, it will prompt you to install it automatically. Okay. So either use it on a web interface with Google Colab on a Jupyter on your machine. But you have to make sure that you access correctly to your GPU and that your NVIDIA driver or whatever you are using as a GPU works correctly for Julia. So we have a test to do this, to check if the GPU is accessible. If you want to do some GPU computing, it's mandatory, actually, to get it to work. So for easy of work today, we'll do it actually through Google Colab. So for getting help, so you type something and you put a question in it, actually, and the REPL, and you get the help automatically. So that's very easy. You have the Julia manual, actually, and you have various channels on Discord, on Slack, on Zulip. The Julia Hub is updated quite often, actually, for all the libraries that you can be associated with Julia. And you have also the discourse page where people interact together, actually, to solve problems in Julia. Okay. Also, there's a lot of documentation, of course, on the internet through your best AI or your Google or whatever, actually. So it's a well-documented language. You usually not have a lot of problems to get help on it for debugging, of course. Some example of large Julia codes, actually. So since 2019, there is a big collaboration in the US, which we call the Klima code, actually. And this is a huge work actually of recoding climate code from scratch, and without using the old climate code that had been developed. So you know maybe that climate codes worked on Fortran mainly. Okay, so these codes have been developed by a lot of researchers and scientists, like for 50 years or 40 years. So they're very hard to maintain, and there's also very hard to benchmark. So there is a lot of work done by Julia community for this. So the two libraries are ClimaCore and ClimaMachine, and they are benchmarking like any function of a climate code one by one. So for example, here you see the convection between an ocean interface and the atmosphere. So they take it, they recode it, they compare it to a previous Fortran code that is doing the same thing, and then they validate if the code is correct or not. So the only advantage you get, the main advantage you're getting by recording this is the maintainability and the readability of the code over time. Okay, so thank you for listening to this small introduction to Julia, and special thanks to Philippe Gras also, who did this introduction in 2023, so 2 years ago for Julia. So now I will switch to the Jupyter Notebook to see some examples. So this is not the page. So is there any discourse question yet or no? No. So this was for Adrien. No? Okay. Okay. So Jupyter Notebook on Collab. So I'm connected to runtime. So as I said previously, since March 2025, so 3 months ago, you have a direct Julia support in Collab. So how to do this? You go to execution runtime here, and you click on modify the runtime, and you'll see all the languages that's supported here. You have Python 3, R, and Julia. So Julia was not present before. You had to install it manually in the notebook itself. Now it's present automatically with the latest version. And you can associate it with any parallelization support you want. So you can do it with TPUs, with GPUs, with processors. So for myself, I tried it with GPUs only. I didn't try Julia with TPUs on other accelerators. I don't know if it works or no, but these are specific to deep learning or AI libraries, okay? But for matrix calculation or parallelization or this kind of work, you can use all the present GPUs you have. And if you have a large problem also, you can ask for a bigger memory access, okay? So for the first parts of the notebook, we'll be using the CPU, okay? Just to use the basic language. And after we will switch to GPU for specific problem on matrix multiplication. The idea here is not to give you all the recipes, but to give you one example actually on how the type statism or dynamism works in Julia, and what's the difference between dynamic function, static variable, and dynamic variable, and also how to make very easily multiple matrix multiplication on GPU. So moving data from CPU to the GPU, make the multiplication, and get back the data, okay? We will not use profiling here because it's out of the scope of this presentation. So first here we define a variable, okay? We can get its type. So it's an int64 here. We can ask him to print a string with a random number. So the random libraries are the same that are used with Python. You can use stride actually with them to make sure that the numbers are the same. These are really, for Python users, are flawless. I mean, it's the same, almost the same syntax, okay? Here we will define a function. So there's many ways to define a functions like as Python. So here we define a function square, okay? We make the computing, square of 2, makes 4. And here actually we'll try to get into inside, yes? You can see from there, okay, sorry. Okay, better? Okay. So here actually, if you type this micro here at code typed square 2, you can access to the code that compiled actually to see what happened. Yes.
I see when you define a function, you use end at the end.
Yes.
Do we have to put the return with a...
Good question. It's an example that will follow in few lines, actually. Okay, so I did, yeah. You can use it without the return, but you will see the difference. Okay, so here we put the return, actually. Okay, we see the generated code here. Okay, and here I type the function without the return. Okay, so we will execute it. We will see what gives us in this line. Okay, so this is the code generated by square of 2. Now I use the same function without the return. Okay, I execute it. Normally I should get the same result, but if I see what the code generated is exactly the same. So this is the job done by this parser. Actually, it understands that you define the function and that the x square is a return without you having to put it manually. Okay, and the best way to compare this is to see what has been compiled early. Okay. Sorry?
Does it understand always the last line of the function as a return?
If it's not clear for it, it will ask. It will give you an error or ask for it. Okay.
Yeah, but how does it figure out? Is it the last line of the function?
No, it can be actually, you can return many variables, not the last line. Okay, so it will interpret what are the inputs and what are you returning. Okay. So we will have an example with variable types later on. We will see a specific example for this, for multiple dispatch actually. Okay. So you can type it also like this. It works the same. So I didn't generate the code generated by this, but gives you the same result. So just a way to say that there's many ways to write function in Julia, and this is the same thing that you find also in Python. Go ahead.
Is the indentation necessary?
Yes.
As long as we have
best.
an end.
It's better. Actually, I never use code without indentation, so I don't know the answer for this question. But if you want people to read your code, do the indentation.
Yeah, but it is necessary in Julia.
Normally it is, yes, like Python.
Okay.
Actually, I think I didn't try it, but it's a good exercise. You can take the notebook, delete the indentation, and try to execute it. But for myself, I never did this actually. Okay, so if you share codes, you do the indentation. Okay. Yeah, so we're not beyond best practices of writing code, of course. Okay, it's not because you have a good parser that you have to write anything anyway. Okay, so you have to keep also in mind that your code may be taken by other people and to make the code correctly. So when you define a function like we did here, you don't need to specify the arguments. It will try to guess it actually. So this is somehow the Python way of working. Okay. Except for code specialization when you need a different implementation for a specific set of arguments types. So we will see an example of this. So it's not always recommended to specify the types. But if you do, so in this school, actually, you saw a lot of compiled languages. You saw also some interpreted languages. You know that for compiled languages, it's always better to specify the type and to control it yourself. Okay, and this is also the case for Julia somehow. Okay, so you can have other types than the simple variables. You have structures actually here. So in this example, we don't define the type, but we can also define it with the type. Okay, so to keep the performance, the type must be concrete. So if you go back to my slides, so say there is some abstract types and there is some concrete types. So for performance, it's better to keep the types concrete. Yes.
So here, writing the type of your different variable is useful for performances.
Yes.
Okay, so
yes.
It's not like Python.
No.
Okay.
But you can do it also on Python.
Yeah, but it's just like
okay.
for documentation and,
Yeah.
and legibility. And here it's used by the compiler to optimize.
Yes,
okay.
to allocate the memory also.
Okay. Okay.
So yeah, it's important. In the case of Julia, it's important. Yes.
Okay.
Otherwise, it's waiting.
Sorry?
Otherwise, it's waiting to know what.
No, otherwise it will take the maximum.
Okay.
Okay. So it's not the good way to do it. Always specify your variables, actually, unless you really don't know what will be the output or something like that. Okay. Try to reason with it like a compiled language. Maybe it's the best way to do it. For Pythonists, Python users, when you go to Julia, try to use it as a compiled language because you will get the better performance. And actually, it's not specific to Julia. For all other languages, actually, try to specify your variables. It's always good. We can also choose another type of variables that you define yourself. So this is as specific as all the other languages. You can define actually dimensions and arrays. This is an example here. So we defined an array with 3 floats, 64 floats. Okay, very easy to do. So this is all Python-like. You have the fill function here, which we are testing. Okay, so just we define the array and we say fill it with 3.4, but with pi actually on the x size, y size, and z size. So all this is flawless right now. Okay. You have the, like I said before, the random generators also that can use actually to fill matrices. So this is useful also in many cases. So float 64 and you fill all the matrix with it. Okay. And you can also use undefined if you don't know what variable you want to put in something. So it will allocate some space. And it also works very well. And you can actually fill this variable later also. Okay. Okay. You can also check the compatibility of types of variables. So here we have a vector of float 64. Is it same thing than an array of float 64.1? And actually, Julia will interpret it as the same thing. So it's smart somehow to do this. And this also works with vectors, but it works also with more complex types like matrices, actually, to see if you are working on the same object. And you use actually, the word vector actually is an array of 1. And you can use it in a function. You can just give a vector, okay? Or you specify an array. And Julia would understand it as the same thing. So the function will work with the two because the parser of Julia will check this automatically. If you define a function with a vector, for example, but you decide instead of running it with a vector, you want to run it with an array. If the array is the dimension 1, it will be accepted. If you put the dimension 2 to array, it will not be accepted. You see the difference or no?
All the matrices assumed as 2Ds?
Actually, yeah, that's a good question. Matrices are maximum 3 dimensions, mathematically. After higher than 3 dimensions, we call that tensors.
Yeah.
Okay? But in the absolute, tensors are matrices with higher than 3.
How can we know matrix of float 64 is 2D or 3D?
I mean, because it knows the dimension of the matrix when you define it, actually.
But here you're checking if matrix.
Yeah, I'm stating that the matrix is something that an array is the same type of an array of 2 dimensions.
Okay.
Okay. And that also works with tensors. Okay. So there is another way also to define big dimensions or big other type of data. It's using the data frames. Actually, this is very easy also. You just have to import the library. And you can define a data frame. So with bigger data frames actually will lead you to tensors anyway, okay? In this way, actually, and it works like an array, or like a vector, or like any other object. So there is, how to say it, there is an intrinsic compatibility between types of variable in Julia. This is what we want to say. Okay. You can do also some broadcasting on a matrix or on a vector, whatever you want. So if you define a matrix like this, 3 by 2, you can do the square of this matrix. Actually, automatically, Julia will understand that you want to broadcast all through the matrix. Now for JIT compilation. So here I give you an example of how to monitor time. Yes, go ahead.
Yeah, sorry, I just have a question about the functions that you used before. Do you
Yes.
have to import some libraries like in Python to use like square or random, or is it standard function in Julia?
No, in Julia. It's,
Okay.
No, it's recorded in Julia, actually. They have, yeah, so this is misleading. All the, almost all the Python functions have been recorded in Julia, but in the Julia language itself.
Okay.
So they keep the same name, but they are not native Python.
Yeah,
They are really, it's not a wrapping. It's really, actually the real extension is dataframe.gl.
Yeah, no, well, my question was like, do you have to import Julia libraries to have access to random, to rand, for example?
No.
Okay, so
No.
it's natively inside.
Yeah,
Okay.
yeah. Rand
okay.
is natively in the.
Okay,
in
it
the
was my
language.
question.
Yes,
Thank you.
yes.
Yeah.
But not all the functions are okay. Yeah. Okay, so where were we? Square. Okay, so we go through the JIT compilation here, and after we will have an exercise on the typing and the statism of functions and variables also. So here actually we try to monitor the time that it takes to make the sum. Okay, so I run it first. You see, okay. If I click back to the on the play button here, you will see that the time changed. So the first time you go through the compiler and the runtime. Okay, but the second time, if you don't change anything to your function, you go directly to the runtime. And here that we will see that the time actually changed a little bit for the second time, but not that much. Okay, so if I run it again, it's almost stable now. Okay, so always the when you run a function the first time, that's not the real time of its execution. You have to run it twice for that. So this is quite weird in Julia, but with time you get used to it. The first run, you go to the compiler and to the runtime automatically for the first time. The second time, if you didn't change anything to your function, you go directly to the runtime. Okay? Sorry? Yeah, for the whole cell. Yeah. It checks the function actually. This is mainly for function actually, the runtime and the compiler. So for function, if you didn't change the type or the topology of your function, the parser will analyze it and will say, no, this is not modified. I can execute it, run it directly. Okay. This is the schema I gave you in the presentation when you see where you go into the runtime and when you go to the compile time. Okay, so this at time macro is native in Julia language, so you don't have to import it. There is another package which is called benchmark tools, okay, which is more performant because here when you measure, actually you measure a lot of variables that a lot of processes that are in the environment itself, okay. The benchmark tool is much more precise, so I have to import it in this case. So it takes a little while, but it will give you the runtime actually just for your process, just for the function you run, okay? You have just to wait like maybe 20 seconds so it installs. And you will see that where is the difference between the upper one and the second one. So if you want to go through precise profiling of your functions or your executions actually, it's better to do it through this library than the native Julia one, okay? So with this one, if you have the same environment, normally you don't have a lot of variability, which is the case for the other one. Okay, so now we'll do it here on this line. So instead of using at time eval sum, I use b time eval sum. Okay. So I just run it. Weird. Okay, so if I run it again, normally I should have a stable time this time. And after we will double the number of items of the sum. So I had 69 microseconds in the first run. This time it's 78. So it doesn't move that much. So it's tagged really to the compiled part of this specific code. So if I take off the commands here and we do it again, so the more time that you'll see is because of the library itself for the profiler, actually. Okay. So almost no difference. Okay. So if you want precise profiling for your functions or multiplications or whatever operation you do, it's longer, but it's always better to use the benchmark tools library than the native actually timer that is set up in Julia. Okay. So this is feedback from the community, let's say. Okay, now let's get some harsh example. Okay, we spoke about dynamic typing and static typing in Julia. So here, I put you a function here, a loop, okay, with two variables, n and r, and that is defined out of the function. Okay, and the question is, what is the type of n? So does anybody have an idea? So when I say what is the type of n, what is the type of n at the variable step of the function? Okay, so here n is still an integer. Okay, I go here, r is 0, so let's say r is an integer also. And we say while n is superior to 1, we add 1 to r, so we increment it, okay? And we divide n by 2, okay? So at the beginning, Julia says n sees n equal 5, basic, so it's an integer. Why put it in as a float? We put it as an integer, okay. Okay, so the function returns here r only, all right? So the function is static. We give it an integer in the input, and we have an integer at the output. The function is static, but are the variables static or not? Does anybody has an idea? Wait, think. It's a tricky problem that you have. So in compiled languages, in compiled languages, we don't have this issue because you have to define the type of your variable. And if you put n as an integer and you divide it by 2, if it's not pair ou impair, I don't know how to say that in English. Yeah, that's it. Actually, you have to change the type and you will have an error here at compilation, okay? Well, Julia doesn't give you an error, but what happens behind the scenes? So the function is static, so we respect that, okay? Because we are turning r as an integer. So, but now tell me what happens with n. Does anybody have an idea? Okay, so we'll do it step by step. So the indiv function, so I call this because we divide an integer, so that's why I call it this way, okay? So here, n is an integer. We enter the function, we define r as an integer also. So when we enter the while, n is still an integer, okay? We increment the r, okay? And we see n equal n divided by 2. What we do, actually, what will Julia do, it will make a union type between an integer and float 64, okay? Easy. We say, okay, we're not sure of the type. We change the type of n. And at the beginning, it wasn't an integer, but in the loop, it becomes a union between, so a mixed type between an integer and a float 64. Let's say we decide later, actually. Okay. But so the function is type stable, but internally, the function is not type stable, actually, right? Internally, it's not, because there is a variable that is changing type inside. And you will tell me, okay, if Julia was clever, we will stay in integer, okay? No, if Julia was smart, we will choose only float 64 as a variable type. But this is not true, because why we cannot rely only on float 64? Does anybody have an idea here? Because suppose you don't enter the loop function. N stays an integer in that case, okay? If you don't enter the loop, N will stay an integer. N becomes a float only if you enter the loop, okay? And this is the job of the parser F of Julia, actually, when it compiles, to decide actually what is the best variable type you have to choose depending on your function. So normally, if you come from the compiled language world, actually, the easy way is to put it as float 64. So there is no choice, there is no thinking, no choice to do for the parser itself. In this case, you have a stable type for the function and a stable type for the variables also. Okay? So this is optimization. And optimization only on the variable type, because the parser here will have to think a lot. So you have this on a simple function here that increments r to r plus 1, okay? But in many complicated functions, actually, the parser have to do this work. And if you want to optimize your code, actually, you have to think of the type of your variables and also the type of your functions, okay? So if we had n as a return, so in the first example here, what we didn't put an n as a return. We did only r, okay? So if I put n as a return, my function will not be stable anymore, okay? So this is the tricky thing about having a dynamically typed language, but who's seeking for stability in behind the scenes. Is it clear for anyone? Sorry? Does it make a copy of n? Yes, it does make a copy of n. Yeah. I don't know. It's a good question. I didn't deepen the thinking to this. But this is a good example of what is actually typing for function and variables is. Yes, go ahead.
If the function always went to the loop, and it knew that it would always return a float, would the JIT make sure that it was a float every time?
Yes, 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 yes. But here you're like, let's say it in familiar words, you're tiring the parser and the JIT, okay? Because it have to think, so it's more a recursive word. And this is a simple function. If you have a recursive function, for example, it's like, it's a mess, it's awful, okay? Is it clear for everyone? Let's make sure that this is very specific to this language, actually, because you don't have this. Python won't ask you for this. It will do the job. It will put as many types if it wants for the variable, and it will give you an answer anyway. Julia will think a little more to optimize, okay? So this has to be very clear for you. What are the types of the functions and what are the types of the variables, and how these variables will, the parser and the compiler will modify the variable type, actually, during the runtime of the function, okay? Yes, go ahead.
Can't we define n as a float in the argument of the function instead of convert into a float inside?
Repeat the question.
Can we define n as a float in the function arguments instead of convert n as a float inside?
That's a possibility.
It's better, I think, no?
Yeah, you can convert it inside the function, yes.
Okay.
And make sure that after, when you exit the function, it is correctly typed.
Yes.
But it's, I mean, that's not done by the parser, it's done by you.
Yeah.
It's like defining the types of the variables correctly.
Okay.
Yes, go ahead.
Yeah, you said that we should treat it like a compiled language, like a statically typed, I guess.
Exactly.
Then why were we seeing this?
That to explain you, for people who don't see it as a compiled language, because a lot of people, I did this mistake once, okay? Because I consider it as a Python way of coding. But
yeah, I mean, it's good to know what's happening. But
sorry?
It's good to know what would happen.
Yeah.
But this is not the recommended way to use it, as you said.
Yes, but it's a very good way for me to explain actually what is the static type of a function and the static and what happens to the variables actually, independently one of the other.
Okay.
Okay.
Thanks.
Just to see actually when you exit a function, it doesn't mean that your functions is static for types. It doesn't mean that your variables are static for types. It's not the same thing because people associate type of function with stability of the type of variables, okay? This is not always the case in this kind of languages. Yes?
Maybe this defeats the point, the design decision of the language, but is there like a lint or a rule that you can turn on to give you a warning if you're not defining types in places?
No.
Okay.
Not to my knowledge, at least.
Mm-hmm.
Yeah. Okay.
If you define the type, it's static always.
Yes.
Mm-hmm.
Yes. Okay, so this is the conclusion of this part, actually. Much faster for the parser to optimize the compiler time at the runtime. So change the type inside the function. So that's what the solution of your colleague said. So you do it yourself. You change it from int to float 64 to make sure it outputs the right variable. So, sorry? Not to my knowledge. Union for types works for 2 only, I think. I didn't see the case with three types, actually. In that case, if you go to the tree of the Julia variables, actually, it will go from bottom to up. You will go to any. So in that case, you don't know what type you have. But it always goes like that. So you go from the bottom to the tree to the up to the tree. So you always get you want to always to get far from abstract types. Okay. So on the variable trees that we saw before, you want to stay at the lowest point of the tree. So Julia, the parser, we go from there to up. So it's kind of a decision tree for the parser, actually, for the variables. Okay. So we go to next part. So here, actually, we'll be switching to the CUDA part for the multiplication of matrices. So we have to change my runtime up, and we will get for GPU T4 up. Okay, so here we will bring the package manager in the notebook with CUDA.
Can we use GPU with Julia only for NVIDIA GPU?
CUDA is for NVIDIA GPUs only, anyway.
Oh, yeah, but my question was, can we add other packages to use Julia and GPU on AMD or Intel GPU?
I don't know if CUDA will work on AMDs, maybe colleagues. Nope.
No, but
good try.
So
can we use another thing than CUDA on Julia to work on AMD GPU, for example?
Yes.
Okay.
There is some library specific for AMDs. Yes, of course. Sorry? Metal is for Apple, actually. So Metal is for Apple. It runs with Metal. So, but it's not the CUDA. The most used one is CUDA. Let's be honest about that. You will find much more examples of usage of CUDA for parallel computing than AMDs or Metal. Okay, but we don't know what will be the future actually. So, okay, so here we insert the CUDA library. So what is the CUDA.gl? So remember here, I didn't put CUDA.gl. Okay, although it exists in Python, if you said just CUDA, expects CUDA.gl behind the scenes, okay? Because all these libraries actually has been recoded in Julia itself. So this is one of the most used one actually for parallel computing. It includes a lot of kernels and other second-hand libraries like cuBLAS, cuRandom, cuFFT, cuSparse, and cuSolver. So these are native in the library itself. You don't have to call them by yourself. They're there. And for deep learning and AI, you have the CUDA-NN and the cuTensor actually that are implemented in CUDA.gl. So it's a very rich library, very well optimized. So now what we did, actually, we installed CUDA, but it doesn't mean that you have the library, that you have access to the GPU. You need that your runtime sees the GPU. So the first thing you have to do is to type device, okay? And here you have a Tesla T4 that is available for you. So you can do get some more other information about your device to make sure that it's available, actually. So this is one of the biggest issues you have sometimes on Linux environments, is the CUDA drivers, okay? Everybody here knows the NVIDIA SMI, okay, which is a nightmare because once it runs, you do something, it doesn't run again, and okay, so Julia actually have a native system to check this for you. And if I name this device, so this device, I can use it as an object itself, okay, with some methods. I call it the V, okay, and I can check the memory available. So this is why this is important, because you always need to know what is the available memory of your GPU actually before using it, okay? So the idea here is not to overload the GPU and to send data only on the available memory. Otherwise, you have to stream and to do some lines to actually to handle the memory during the computing time, okay? And you can also know the maximum threads that you can send on the GPU. So this is information, the information is called attribute, and it will give you the number of threads that you can send in your GPU. So this is very important also when you generate your kernel, actually, the number of threads. Okay, so creating a variable on a GPU is very easy. You just put A equal cuArray. So we have the array function. We add just the cu extension before, and it's automatically created on the GPU. Okay. So I don't do this way. Okay. I always create my variables on the CPU. I handle the transfer to the GPU. I make the computing, and after I handle back to the GPU, to the CPU. Okay. Everybody has a way to work, because when you do this, actually, you never know where you created your variable. Yes, go ahead.
Do we have to put CU before everything native from Julia to?
It's a method, actually. So
okay.
It's in the documentation. You have to use that.
And
so normally there is a logic behind. So you take all the words that came from the Python libraries. You add CU before, and you can do. But it's not always the case. So.
But wouldn't it be better for the parsing to just put CU point? And
you can do that also.
Okay.
Okay. So just as we are running out of time, I will get into the matrix multiplication actually, but I will do it this way. So we will not create the matrices on the GPU directly. We will create them on the CPU, handle the transfer, because this is the job you will have to do actually when you're doing your program. You don't send data to the GPU directly. You have to create them on your CPU first. And after, actually, you send them to the GPU. So all this work of data transfer between the computing steps is done by you for the optimization purposes, actually. So here we define a dimensional matrix of n equal 10. So we create two matrices, A and B, on the CPU. So we use the random function to do this. Okay, so to answer once again your question, you have the cuRandom. So if I wanted to create this on the GPU directly without passing by the CPU, I use cuRandom on the GPU directly, and it works. Okay, it's faster, of course. Okay, but it's the same way to do it. So there is two ways to do it. So this is specific to the developers and how you want to make your code. So here we make a transfer of the variables to the GPU. Okay, So now all the variables are on the GPU. So we make the computing of the C matrix, which is the multiplication of A and B on the GPU itself. Okay. And after we did this, we transfer back the data from the CPU to the from the GPU. Sorry, so look, I did the mistake. From the GPU to the CPU again, and we display the results. So quite simple example, okay, on how just by well identifying your device, checking its memory, actually you can create easy matrices. So what you can do after this, actually you can modify n to 100, for example. Okay, and you can run it again. And you see it will not change a thing on the computing time because you're doing it at the GPU, on the GPU. Okay. That's easy as it is, actually, as you see it here. Okay. So I didn't give a CPU example because it's like Python is very, very basic, and you saw it last week, I guess, if I remember well. For the CPU, it was thoroughly flawlessly like Python. For the GPU, it's quite different. You have to use this specific CUDA library developed in Julia to do this, actually. And always be careful where you create your variable and what you're doing on it. So there is some, so the CUDA library gives you a method which is Q events that will allow you to monitor actually the computing only on the GPU. So it doesn't take into account the memory transfer, okay? If you want to do that, you have to use much more developed, complicated profilers to see all the transfer, because what you need to see is the computing time, but also the transfer time actually for it, okay? So the Q events method doesn't allow you to do that. Q events computes only the time, monitors only the time that you use on the GPU. Doesn't integrate the transfer of memory with it, okay? So you have to use the Julia profiler for that, and you can use also the add time and the B time that we used before actually to make the profiling, time profiling. I'm finished. Do you have any other question, Julia? So this is a rather quick introduction. Yes? It deals with, there is a specific library for that. Matrix sparse, I think it was. Yeah, somebody told me about this a few days ago. So yes, so if you want to deal with this kind of problem, yes, it can handle it.
Linear servers?
Sorry?
Linear servers?
There is linear servers also integrated in the native library. It's really completely, all the libraries that you find in Python, you find them in Julia also. It's really, it's the only thing that is, so we didn't see the example here because we are in collapse. But for example, if you don't use any parallelization library in Python, like Numpy or whatever, you will be running on one processor, one thread, okay? Natively, Julia actually will use all the cores available, okay? So if you run it on your computer, you run Julia process or Julia code, you will see that it will use all the cores at the same time. If you do it with Python without any specific library, actually, you will be using one core only. This is the main difference, on the CPU at least, okay?
Okay, thanks.
So for Python, you have to use a multi-threaded library to get use of all the cores. In Julia, you don't have to do that. It uses all the cores natively.
Does it have something like matplotlib?
Matplotlib, so this is the weakness of Julia. Plotting graphs, that's why I didn't do it. It's very, very slow. Let's be honest. That's why a lot of teachers don't use Julia, because if you take 2 or 3 minutes to make a plot, you lose all your students, okay? And I lived through this. That's why teaching with graphs and Julia, so something weird, if you wrap the plot library of Python, it's faster than Julia's. Okay. so Julia community has some work to do on the plots. I completely agree with that.
We can inside there just wrap it in Python and it's okay.
Yes, yes. A lot of people do this behind the scenes because the plot.gl is rather slow. And there is, if you go to the discourse link, there is like a debate like since 5 years on that. Why is it so slow? Why is it so slow? And it doesn't get faster. We don't know why. I think it's related to the runtime and the compile time, actually, for the plot library. And we think the slowness for the graphs are native to the language. So I don't think it want to go faster. So if you want fast graphs, wrap the plot library of Python and go with it. Don't use it with Julia. But this is an issue. I have one colleague that used to teach at Dauphine, and he abandoned Julia because of the problem of the graph of the plot function. So yeah, we have to be honest on this. This is not the best thing that Julia can do, making graphs.
Does it have HDF5?
Sorry?
H5? Does it has?
Yes.
Can we do some H5 writing?
Yes. Yes, it's native to the language also. Yeah. Like Python, actually.
Does it have, like, for example, multiplication between a regular and a sparse matrix? Or you don't know?
I don't know.
Okay.
Very specific use case. I don't know why people are speaking a lot of sparse matrices these days. People from the finite element community use this. We had these problems like for 20 years now. And it went under the carpet for like 5 or 10 years since the rise of AI. And now everybody is speaking back about sparse matrices. Why? I don't know. Is it a fashion or is it a hype? I don't know what is about sparse matrices. I think Vincent spoke about these sparse matrices. Sparse matrices, you find this problem actually in multiphysics finite element modeling because you have a lot of empty rows in your matrix. But now it arises another problem. Maybe Vincent will give some example.
Yes, so when I was asked in the winter, I was young and I wouldn't know. But now that I've taken some wisdom, we can use it for all kind of tessellation. When you have a space and you want to solve some equation,
yes,
you have to fill your space with simplexes, and then you will have the relation between each of the vertices of your meshing, and it will be represented by a sparse matrix.
Okay.
They are also used in sparsely connected neural networks.
So look, if IA is based on sparse matrices, it won't work, for sure.
If what?
If IA is being based on solving sparse matrices, it will be rather slow. But like in math, the sparse matrices problem is a problem we have like since 20 years right now. And every community has a way to solve it. There's no specific recipe to solve sparse matrices because it's really physics related. So I use it personally. I used to solve this through COMSOL multiphysics, which is COMSOL is a subsidiary of MATLAB actually. They separated like 20 years ago, 10 years ago. But yeah, sorry?
It's private.
Yeah, it's commercial use. Yeah. But it solves very well sparse matrices. I don't know how they do. They have, I think, patented solvers for this. So it's not open source. That's what I want to say.
No, it's a finite element commercial stuff.
Yes.
Yes. It uses some.
Yeah, actually, finite elements comes to matrix solving problem actually, and matrix inversion. And there you have a lot of sparse matrices, especially if you don't work on one physics, you work on multiple physics. So if you combine fluid dynamics with induction, for example, or Maxwell equations, you have a lot of sparse matrices. And you need a solver that works well with these. And these are commercial ones, and are not, they're really patented. There is patents about this, so you cannot use them actually. So you have to pay for these actually. Unless you take the standard ones made by the open source, but you have to wait a lot. So it takes time. Okay. So I hope this gave you a small insight of what you can do with Julia rather quickly. And if you want some more details, so I go back to my presentation very quickly. There is, in this link here, there is the presentation done by Philippe Gras 2 years ago, when you have the implementation of Grayscott on Julia, on CPU and GPU. So it's all on this link. So you can have a very good example here of solving the Gray-Scott equation on the CPU and the GPU with all the memory transfer, the computing, and getting the data back, and generating the video, all the stuff. So if you want to see a good example, there is one already present. Actually, and it's open, so it's open to everyone. Any other question? I didn't check this course. Oh. So do you see, I may maybe make a zoom. I have to take some time to read all this, sorry.
I think it's just the answer to Adrian's question.
Ah, okay. Okay, thank you, Adrien, for answering. So, bah, merci. Thank you.
Is this a presentation and call-up available somewhere?
I can share it, yes.
So we'll write you an email, or?
Sorry?
We'll write you an email, or what? Where?
No, I will send it to the organizers.
Okay.
I will share. They will share it with everyone. So I will share the PDF and also the Jupyter notebook if you want. No problem. Okay. Bon, tu peux rentrer plus tôt aujourd'hui.
Well, just some time.
Huh? Yeah.
For
the conclusion.
Second time of the school. That's,
Tu vas dire quelques mots là?
Yeah.
J'enlève ça du coup?
Yeah, just to. So it's all for today. So I hope you learn lots of stuff on Rust, on Julia, on VULKAN, on all the GPU horrible stuff we can do. And tomorrow is the Python day.
Yes.
So don't miss the Python day.
So there will be Alice, Jean-Marc, and me.
Yeah,
together.
for the GPU, so
Yes.
PyPy with PyTorch, with
JAX,
cunumerics,
also.
so lots of stuff.
Yeah.
So don't miss this day. That's all for today. So see you tomorrow and bye.